Hello and welcome back. I'm glad you're here. Maybe you had a long day. Maybe your mind is still turning over all the small decisions and conversations, the little puzzles that don't quite resolve. That's okay. Tonight we're going to let all of that go, and instead we'll drift through something different, something bigger, yet somehow more peaceful. We're going to explore mysteries, not the kind that demand answers or create anxiety, but the kind that invite us to simply wonder. Tonight's journey takes us through 100 unexplained mysteries that baffle scientists. These aren't conspiracy theories or wild speculations. These are real phenomena, observed and documented, that sit at the edges of our understanding. They're the questions that make researchers pause, the puzzles that remain unsolved despite decades, sometimes centuries, of investigation. And there's something oddly comforting about that, isn't there? The universe still has secrets. Science, for all its power and precision, still finds itself standing before locked doors, wondering what lies beyond. Before we begin, if you enjoy these journeys into the peaceful unknown, consider leaving a like. It helps others find their way here too. Subscribe if you'd like more nights like this, and feel free to leave a comment about which mystery resonates with you most. But there's no pressure. Those things can wait until morning. Now, let's begin. We'll start with something familiar, something you're probably feeling right now, that gentle pull towards sleep. It's curious, isn't it? Scientists still don't know why we spend a third of our lives sleeping, despite it being universal among animals. We know that sleep deprivation is deadly. We know that every creature with a nervous system, from jellyfish to elephants, spends time in something resembling sleep. But the fundamental reason our brains demand this nightly shutdown remains one of biology's deepest puzzles. Think about it for a moment. Sleep is expensive, evolutionarily speaking. When you're asleep, you can't find food. You can't reproduce. You can't flee from predators. For millions of years, natural selection should have favored creatures that needed less sleep, or perhaps no sleep at all. Yet here we are, surrendering consciousness for hours every single day, as if following an ancient instruction written into the very fabric of life itself. There are theories, of course. Some researchers believe sleep allows the brain to consolidate memories, transferring important experiences from temporary storage to long-term archives. Others point to the glymphatic system, a kind of cleaning crew that flushes out metabolic waste products while we sleep, including proteins that might otherwise accumulate and cause neurological damage. Still others suggest that sleep is when the brain prunes unnecessary neural connections, refining its networks like a gardener tending to overgrown paths. But here's the thing. None of these explanations feel complete. They describe what happens during sleep, perhaps even some benefits of sleep, but they don't quite answer why sleep evolved in the first place, or why it takes the specific form it does. The cycling through stages, the dreaming, the absolute biological imperative that makes prolonged wakefulness eventually fatal. Maybe sleep is doing something so fundamental that we can't even recognize it yet. Maybe it's not just one thing, but a constellation of processes so interwoven that separating them would be like trying to explain why water is wet by examining individual molecules. The answer might be hidden in the question itself, waiting for us to ask it differently. For now, though, sleep remains mysterious. which seems fitting somehow as we drift toward it. Here's something that shouldn't work, but does. The placebo effect works even when patients know they're taking a placebo, defying our understanding of how belief shapes biology. Your brain can trigger real healing responses from sugar pills you know are fake, a phenomenon that challenges the very boundary between mind and body. For decades, researchers assumed the placebo effect was all about deception. Give someone a sugar pill, tell them it's powerful medicine, and their expectation of healing activates real biological processes: reduced pain, lower blood pressure, even measurable changes in brain chemistry. The trick, everyone thought, was the belief. The patient had to believe the treatment was real for it to work. But then came the studies that changed everything. Researchers began telling patients explicitly, "This is a placebo. There's no active medicine in these pills. They're made of sugar and cellulose." And then something strange happened. The patients got better anyway. Not all of them, not always, but at rates significantly higher than those who received no treatment at all. People with irritable bowel syndrome experienced reduced symptoms. Patients with chronic pain reported meaningful relief. Even depression scores improved in some trials. How is this possible? If you know the pill contains nothing therapeutic, what is there to believe in? The current thinking goes something like this. Perhaps the ritual of treatment itself triggers healing pathways. The act of taking a pill, the routine of care, the attention from medical professionals. These might activate learned associations between receiving treatment and getting better. Your body has experienced real medicine before, and maybe it's learned to respond to the context of treatment itself, independent of the treatment's actual contents. Or maybe it's something deeper. Maybe the conscious knowledge that you're taking a placebo doesn't matter as much as some unconscious part of your mind that responds to care, attention, and the implicit message that you deserve to feel better. There's something almost philosophical about it. The idea that healing might have less to do with what we consciously believe and more to do with how our bodies interpret being cared for. The boundary between mind and body seems less like a wall and more like a gradient, a place where thoughts somehow become chemistry and intention becomes biology. We're still trying to understand that translation, that mysterious place where the abstract becomes physical. Let's step back now, way back, to the very structure of reality itself. We don't understand why there are exactly 3 dimensions of space and 1 of time in our universe. The number 3 seems arbitrary, yet it's fundamental to everything from atomic structure to the stability of planetary orbits. Imagine trying to explain to an alien intelligence, one that exists in a universe with different dimensional rules, why our universe has 3 spatial dimensions. Why not 2? Why not 4 or 17? The question seems almost meaningless until you realize that the number of dimensions isn't just a detail about space. It's a constraint that shapes physics itself. In a 2-dimensional universe, for instance, gravity would work differently. Instead of following an inverse square law, where gravitational force decreases with the square of distance, it would follow an inverse law. Orbits wouldn't be stable. Planets couldn't circle their stars in predictable paths. Even basic things like digestion would be impossible. A 2-dimensional creature with a complete digestive tract would fall apart, sliced into separate pieces by its own digestive tube. The universe would be simpler, perhaps, but also dramatically less capable of supporting complexity. What about more dimensions? 4 spatial dimensions would create its own problems. Orbits would again become unstable, but this time because gravity would fall off even faster with distance. Atoms might not hold together properly. The electromagnetic force binding electrons to nuclei would behave differently. String theory proposes that our universe might actually have additional dimensions, 10 or 11 or even more. But these extra dimensions would need to be curled up, compactified into spaces so small we'd never experience them directly. And even if they exist, the question remains, why 3 large dimensions and the rest small? Why this particular configuration? Some physicists invoke the anthropic principle. We observe 3 dimensions because universes with 3 dimensions are the ones capable of producing observers. It's a bit like rolling 100 dice and finding that they all came up 6. Not because there's anything special about 6s necessarily, but because you only exist in the version of reality where it happened that way. Other researchers wonder if the number 3 emerges from deeper principles we haven't discovered yet. Some mathematical beauty or physical necessity that makes 3 dimensions inevitable or at least preferred. For now, we live in a 3-dimensional space, moving through 1-dimensional time. And it's the only reality we've ever known. But sometimes, in the quiet moments before sleep, it's worth wondering, what does a universe feel like when it has different rules? And why does ours feel like this? On August 15th, 1977, a radio telescope in Ohio detected something unusual. The WOW signal remains the strongest candidate for an alien transmission we've ever received, but it never repeated. For exactly 72 seconds, a narrow-band radio signal, strong, focused, coming from the direction of the constellation Sagittarius, poured through the telescope's receivers. The astronomer reviewing the data was so startled that he grabbed a red pen and circled the printout, scrawling "Wow" in the margin. What made the signal so compelling? Several things. First, its frequency, 1420 megahertz, right in the middle of a quiet zone, where radio transmissions are internationally protected because it's the frequency hydrogen naturally emits. Any civilization that understands radio astronomy would know this frequency. It's one of the most fundamental in the universe. Second, its intensity. The signal was strong enough that it stood out dramatically from background noise, showing a clear, narrow band characteristic that natural sources rarely produce. Third, its duration. It lasted the 72 seconds you'd expect if a fixed telescope was sweeping past a distant, stationary source as Earth rotated. But here's the mystery. We've never heard it again. The telescope pointed back at that same patch of sky dozens of times. Other telescopes have searched. We've listened with better equipment, more sensitive receivers, across wider frequency ranges. Nothing. Just silence from that corner of the cosmos. What happened? Maybe it was a one-time beacon, a cosmic lighthouse beam that swept across Earth for a moment before moving on to other parts of the galaxy. Maybe it was a brief transmission that happened to align perfectly with our listening window. Imagine someone trying to call you, but only letting the phone ring once in a lifetime. Maybe it was something natural that we haven't identified yet. Some rare astrophysical phenomenon that mimics an artificial signal. Or maybe, just maybe, it was exactly what it looked like. A deliberate transmission from something not of Earth. A momentary acknowledgement that we are not alone, transmitted across distances so vast that another signal might not reach us for years, decades, or centuries. We're still listening, still watching that patch of sky. The wow signal sits in our records like an unanswered question, a cosmic knock on the door that came just once. And perhaps that's perfect in its own way, a mystery clear enough to be tantalizing, but ambiguous enough that we can't quite close the case. The universe has sent us an enigma, and we're left to wonder. Here's a mystery about existence itself. Nobody knows why the universe has matter in it at all, since matter and antimatter should have annihilated each other after the Big Bang. There's a tiny asymmetry, about one extra matter particle for every billion pairs, that allowed everything to exist. Let's slow down and really sit with this one, because it's profound. In the first fractions of a second after the Big Bang, the universe was a roiling soup of energy so dense and hot that particles and their antimatter counterparts spontaneously materialized and destroyed each other in an endless cycle of creation and annihilation. For every electron that appeared, a positron, its antimatter twin, appeared alongside it. For every proton, an antiproton. When matter meets antimatter, they annihilate completely, converting back into pure energy. It's nature's most efficient form of erasure. If matter and antimatter were produced in exactly equal amounts, which the known laws of physics suggest they should have been, then the universe should have annihilated itself completely. Every particle should have found its antiparticle partner, and the entire cosmos should have resolved into nothing but light, photons carrying the memory of a universe that tried to exist but couldn't quite manage it. There would be no stars, no planets, no atoms, no you. But that's not what happened. For some reason, and this is the mystery, there was a tiny excess of matter. For every billion matter-antimatter pairs that destroyed each other, there was apparently one extra matter particle left over. Just one. One in a billion. And when all the annihilation finished, when all the antimatter found its mirror partner and disappeared in a flash of gamma rays, that leftover matter remained. That tiny, almost negligible excess became everything. Every atom in your body, every star in the sky, every planet orbiting in the darkness. All of existence is built from the survivors of an ancient cosmic lottery, where the odds were stacked 1,000,000,000 to 1 against matter. Why was there an asymmetry? Physics doesn't have a complete answer. There are theories involving CP violation, subtle differences in how certain particles and their antiparticles behave during decay. There are ideas about conditions in the early universe that might have temporarily favored matter over antimatter. Some researchers look to exotic particles that might have appeared briefly in the universe's first moments, particles that decayed unevenly and tipped the scales. But none of these explanations feel entirely satisfying yet. None of them fully account for why the universe chose matter over antimatter, or why the asymmetry was exactly 1 part in a billion, not 1 in a million, not 1 in a trillion, but that specific ratio. You exist because of an imbalance so subtle that it almost wasn't there at all, and maybe that's something worth contemplating as you drift towards sleep. That all of this, everything we know and touch and experience, is here because reality somehow, for reasons we still don't understand, decided not to cancel itself out completely. The Fermi paradox asks a simple question with profound implications. Why, in a universe so vast and old, haven't we found any evidence of intelligent alien life? Either we're extraordinarily alone or something prevents civilizations from spreading across the stars. Both possibilities are unsettling. Think about the numbers for a moment. Our galaxy, the Milky Way, contains somewhere between 100 and 400 billion stars. Many, perhaps most, of those stars have planets. Some of those planets orbit in the habitable zone where liquid water can exist. Life on Earth emerged relatively quickly after the planet cooled enough to support it, which suggests that life might not be particularly rare. And our galaxy is 13 billion years old, which means there's been ample time for intelligence to arise, develop technology, and spread. So where is everyone? If even a tiny fraction of stars harbor intelligent life, and if even a small percentage of those civilizations develop technology and feel the urge to explore or expand, the galaxy should be teeming with evidence of their presence. Even traveling at a fraction of light speed, speeds we can almost imagine with current physics, a civilization could colonize the entire galaxy in just a few million years. That sounds like a long time, but it's nothing compared to the billions of years the galaxy has existed. We should see megastructures, engineered stars, deliberate signals, artifacts, something, but we don't. The sky is quiet. The cosmos seems empty of voices other than our own. This silence has prompted dozens of potential explanations, each one more thought-provoking than the last. Maybe intelligent life is extremely rare, and we're the first or nearly the first in our region of space. Maybe civilizations inevitably destroy themselves before they can spread. A dark filter waiting somewhere in every species' future. Maybe advanced intelligences lose interest in expansion and turn inward, exploring virtual realities or to transcendent experiences we can't imagine. Maybe they're here, but we can't recognize them. Their technology so advanced that it looks like natural phenomena to our instruments. Or maybe, and this is the loneliest possibility, maybe we truly are alone. Maybe the universe is vast beyond comprehension, filled with planets and stars and galaxies, and yet somehow empty of other minds. Maybe Earth is an anomaly, a statistical fluke where conditions aligned in just the right way to produce not just life, but consciousness, intelligence, curiosity about the cosmos itself. There's something both terrifying and oddly peaceful about this uncertainty. We look up at the stars and we don't know if they're watching back, or if we're speaking into silence. The Fermi paradox isn't just a scientific puzzle, it's an existential meditation on loneliness and connection, on whether intelligence is common or precious beyond measure. For now, we keep listening, keep searching, keep sending our own signals into the dark, and the universe, for its part, keeps its secrets. Let's bring things back to something familiar now, something you probably interacted with today. Water behaves differently from every other liquid in dozens of ways, and we still can't fully explain why. It expands when it freezes, has mysterious memory effects, and exhibits properties that shouldn't be possible. Yet life depends on these anomalies. Water is everywhere, so common that we barely think about it. But if you were a chemist encountering H2O for the first time, you'd be baffled. Based on its molecular weight and structure, water should be a gas at room temperature, like hydrogen sulfide or ammonia. But instead, it's liquid. It has an unusually high boiling point, an unusually high surface tension, and an absolutely extraordinary heat capacity, meaning it takes a lot of energy to change its temperature. This last property is why oceans moderate Earth's climate, why coastal regions don't experience extreme temperature swings, why your body can maintain a stable temperature despite external conditions. But the weirdness goes deeper. Most substances become denser as they cool and solidify. Their molecules pack together more tightly in the solid phase than the liquid phase. Water does the opposite. Ice floats because frozen water is less dense than liquid water. This seems trivial until you consider the implications. If ice sank, every body of water on Earth would freeze from the bottom up. Lakes and oceans would become solid blocks of ice, with perhaps a thin layer of liquid on top during summer. Life as we know it probably couldn't exist. But because of water's anomalous expansion upon freezing, ice forms a protective layer on top, insulating the liquid below and allowing aquatic ecosystems to survive winter. And then there are the stranger properties. Water has multiple liquid phases depending on pressure and temperature, not just ice, liquid, and vapor, but different structural arrangements of liquid water itself. It shows signs of what researchers call memory effects, where the structure of water molecules seems influenced by previous conditions, even after those conditions change. Some experiments suggest water can retain information about dissolved substances, even after they've been diluted away. Results so controversial, they've sparked decades of debate because they brush up against the boundaries of chemistry as we understand it. Why is water so strange? Part of the answer lies in hydrogen bonding, the way water molecules attract each other through electrical interactions between their oxygen and hydrogen atoms. But hydrogen bonding exists in other molecules too, and they don't behave like water. There's something about the specific geometry of H2O, the angle between its hydrogen atoms, the distribution of its electrons, that creates emergent properties we're still trying to fully understand. Water molecules can form complex networks, temporary structures that break and reform trillions of times per second. The liquid seems almost alive with molecular motion, constantly rearranging itself in ways that pure physics can describe but can't quite predict. Life evolved in water. From water depends absolutely on water's strange properties. Maybe it's not a coincidence. Maybe life could only emerge in a solvent weird enough to support the kind of chemistry that leads to complexity. Or maybe we're just lucky that the most common molecule on our planet happens to be the most unusual. Either way, water remains mysterious, familiar and alien at once, essential and inexplicable. Not a bad thing to contemplate as you drift off, floating perhaps in your own way through the darkness. Now we come to something truly intimate, something happening right now as you read these words. The hard problem of consciousness asks why physical brain processes create subjective experience, why there's something it feels like to be you. We can map every neuron firing in your brain, but science can't explain why those signals produce the sensation of tasting chocolate or seeing red. This isn't about how the brain works. We're making remarkable progress there. We can watch neurons light up when you see a face, identify networks that activate during memory recall, trace pathways that process pain or pleasure. We can predict some of your decisions before you're consciously aware of making them. We understand a great deal about the mechanics of cognition, about information processing, about the computational architecture of thought. But here's what we can't explain: why any of that feels like anything at all. Imagine a philosopher's thought experiment, a being that processes information exactly like you do, responds to stimuli identically, behaves in every observable way like a conscious person, but has no inner experience whatsoever, no sensation of existing, no awareness, no light on inside, just darkness all the time, despite perfect function. This philosophical zombie seems conceivable, which raises an unsettling question. If we can imagine a universe where all the same physical processes occur without producing consciousness, then consciousness itself must be something extra, something beyond the purely physical arrangements of atoms and electrical signals. Why should the specific pattern of neurons firing when you taste strawberries create that particular experience? The sweet tart sensation, the redness, the memory of summer. Why should electrochemical cascades in your visual cortex produce the subjective quality of blue, that specific feeling of blueness that you can't describe to someone who's never seen color? There's an explanatory gap between neurons are firing in this pattern, and it feels like this, and we don't know how to bridge it. Some philosophers and neuroscientists think consciousness might be fundamental to the universe, like mass or charge, a basic property woven into reality itself, rather than something that emerges from complexity. Others believe we're asking the wrong questions, that consciousness will dissolve as a mystery once we understand the brain deeply enough. Still others suggest that subjective experience might be an illusion, a trick the brain plays on itself, though this seems to dodge the question rather than answer it. After all, even an illusion is experienced. Someone has to be fooled. Perhaps the mystery runs even deeper. Perhaps asking, why does consciousness exist, is like asking, why does existence exist? We're inside the phenomenon trying to explain it, using consciousness to understand consciousness, like an eye trying to see itself without a mirror. Maybe the very fact that we can ask this question can wonder about our own wondering. Is itself part of the mystery? Consciousness recognizing itself, reality becoming aware of itself through us. As you lie there, aware of being aware, consciousness contemplating consciousness, you're participating in perhaps the deepest mystery of all. The universe has somehow arranged itself in such a way that parts of it can experience being, and we don't know why. We don't even know how to properly ask why. But the question itself is beautiful, isn't it? The fact that matter can wake up and wonder about itself. Let's drift now to something planetary, something that shapes our world in ways we barely notice. Earth's magnetic field has reversed hundreds of times, and we don't know what triggers these flips or when the next one will happen. The field is currently weakening at an accelerating rate, which might mean nothing or might signal an imminent reversal. Imagine holding a compass and watching the needle suddenly swing around, north becoming south, south becoming north. That's essentially what happens during a geomagnetic reversal, though the process takes centuries or millennia rather than seconds. The Earth's magnetic field, generated by churning liquid iron in the outer core, thousands of miles beneath your feet, periodically weakens, becomes chaotic, sometimes splits into multiple poles, and eventually settles into a reversed configuration. The geological record preserves these reversals beautifully. As volcanic rocks cool, iron-bearing minerals align with the magnetic field like tiny frozen compass needles, creating a permanent record of the field's direction at that moment. By studying rocks of different ages across the planet, scientists have reconstructed a history of reversals going back hundreds of millions of years. The last one occurred about 780,000 years ago, the Brunhes-Matuyama reversal. Before that, they happened more frequently, sometimes every few 100,000 years, sometimes separated by millions of years. There's no predictable pattern, no regular cycle. The Earth's magnetic field seems to flip when it feels like it. What triggers these events? We don't really know. The Earth's core is a turbulent, chaotic place. A sphere of liquid iron and nickel, heated by radioactive decay and residual heat from planetary formation, spinning along with Earth's rotation, but flowing in complex patterns we can barely simulate. This flow generates the magnetic field through a process called the geodynamo, essentially turning the planet into a giant electromagnet. But the details are fiendishly complicated, involving fluid dynamics, thermodynamics, and magnetohydrodynamics, all interacting in a pressurized, superheated environment we can never directly observe. Sometimes the flow patterns shift. Maybe a plume of hotter material rises from the inner core boundary. Maybe convection currents reorganize themselves. Maybe the solid inner core, which is growing slowly as the planet cools, affects the flow in ways that destabilize the field. Whatever the cause, the magnetic field begins to weaken. It might drop to just 10% of its normal strength. The field lines become tangled, chaotic. Multiple magnetic poles might appear simultaneously in odd places. And eventually, if the reversal completes, the field reorganizes with opposite polarity. Here's what makes this relevant now. The Earth's magnetic field has weakened by about 9% over the past 170 years. The rate of weakening is accelerating. There's an area called the South Atlantic Anomaly, a region between South America and Southern Africa, where the field is particularly weak, and it's growing. Satellites passing through this region experience higher radiation exposure and occasional glitches. Does this mean we're heading toward a reversal? Maybe. Or maybe the field is just fluctuating as it does. During the actual transition, which could take anywhere from a few centuries to several thousand years, the magnetic field wouldn't disappear entirely. It would just be weaker and more complex. Life would continue. The atmosphere would protect us from most radiation, but satellites might struggle. Power grids could be vulnerable to solar storms. Migrating animals that navigate using magnetic fields might become disoriented. Or perhaps nothing dramatic will happen for another 100,000 years. The Earth keeps its own schedule, flowing and churning in the dark beneath us. Magnetic field shimmering and shifting according to rules we're still learning to read. It's oddly comforting in a way, a reminder that we live on a dynamic planet, one that's still changing, still alive in its own geological way. Here's something that sounds like folklore, but has been documented by credible witnesses for centuries. Ball lightning, glowing spheres that float through the air during storms, has been reported for centuries, but remains unexplained. Witnesses describe it passing through walls and windows, sometimes even appearing inside aircraft, yet we've barely captured it on camera. The descriptions are remarkably consistent across time and culture. A luminous sphere, anywhere from golf ball to beach ball sized, appears during or shortly after a thunderstorm. It glows in colors ranging from white to yellow to blue or red. It hovers or drifts slowly, seemingly unaffected by wind. It lasts anywhere from a few seconds to several minutes. Sometimes it disappears silently. Sometimes it explodes with a bang. Sometimes it passes through solid objects, windows, walls, even metal aircraft fuselages, without leaving damage. And sometimes it leaves behind a smell, often described as sulfurous or like ozone. For a long time, scientists dismissed ball lightning as an optical illusion, a retinal afterimage from regular lightning, or perhaps misidentified St. Elmo's fire, that eerie glow that appears on pointed objects during electrical storms. But the reports kept coming, from pilots and ship captains, from physicists and engineers, from people with no reason to fabricate such stories. And occasionally, physical evidence appeared: scorch marks, small holes in glass, electromagnetic interference with equipment. So what is it? Theories abound, but none fully satisfies the observations. One idea suggests that regular lightning strikes the ground and vaporizes silicon in soil, creating a floating ball of energized silicon vapor that glows as it slowly oxidizes. Another proposes that ball lightning is a kind of plasma vortex, where ionized air rotates in a self-sustaining configuration. Some researchers think it might involve exotic forms of matter, Rydberg atoms with electrons in highly excited states, or even microscopic black holes, though this last idea ventures into the speculative. The passing through walls part is particularly puzzling. How could a physical object made of hot plasma or silicon vapor pass through glass or metal without leaving a mark? Some researchers speculate that what witnesses perceive as ball lightning passing through barriers might actually be the field generating multiple instances on either side, essentially creating a new sphere that appears connected to the first. Others wonder if we're dealing with some kind of electromagnetic phenomenon that creates the perception of a physical object without there being a discrete thing to track. The frustrating part is that ball lightning is rare and unpredictable. You can't summon it to a laboratory. You can't study it under controlled conditions. A few researchers have created things that look somewhat similar, using high-voltage electrical discharges or microwave beams. But whether these recreations are actually the same phenomenon remains unclear. In 2012, scientists in China accidentally captured ball lightning on video during a routine thunderstorm observation, along with spectroscopic data showing its light emission. The data suggested it might indeed involve vaporized silicon and iron, but one observation isn't enough to close the case. So ball lightning remains in that uncomfortable space where the phenomenon is almost certainly real. Too many credible witnesses, too much consistency in the reports, but the explanation remains frustratingly out of reach. Nature has created something we can barely capture on camera, let alone understand. And maybe that's okay. Maybe it's fitting that thunderstorms, those primal displays of atmospheric power, still hold a secret or two, the sky keeping a bit of mystery for itself. Let's travel back in time now, way back, to an event that shaped everything that came after. The Cambrian explosion saw complex animal life suddenly appear 540 million years ago, and we don't know why it happened so quickly. In just 25 million years, a blink in geological time, most major animal body plans emerged from simpler ancestors. For billions of years before the Cambrian period, life on Earth was mostly microbial. Bacteria, archaea, eventually simple eukaryotic cells. Around 600 million years ago, the first multicellular organisms appeared. Soft-bodied, strange things that looked like quilted fronds or rippled discs pressed into the seafloor. The Ediacaran fauna, they're called, and they were unlike anything alive today. So unlike modern life that some scientists wonder if they represent a failed experiment in multicellularity, a different way of being complex that ultimately didn't persist. Then around 540 million years ago, something extraordinary happened. In a geologically brief span, the oceans filled with animals. Not just any animals. Animals with hard shells, with jointed legs, with eyes and mouths, and predatory behaviors. Trilobites, those iconic fossils with their compound eyes and segmented bodies. Anomalocaris, a fearsome predator as long as your arm. Early ancestors of mollusks, arthropods, echinoderms, chordates. The major groups of animals we see today all appeared during this period. It's as if evolution suddenly shifted into high gear, experimenting wildly with different body plans, different ways of moving and feeding and sensing the world. Why then? Why so fast? There's no shortage of theories, and the truth probably involves several factors working together. Some researchers point to rising oxygen levels. Photosynthetic organisms had been slowly oxygenating the atmosphere and oceans for billions of years. And by the Cambrian, oxygen might have reached a threshold that allowed larger, more active bodies to evolve. More oxygen means more energy available for complex metabolism, for building tissues, for powering muscles. Others focus on ecological factors. Perhaps the evolution of predation created an evolutionary arms race. Once one animal developed the ability to hunt and eat others, prey species were pressured to evolve defenses, which in turn pressured predators to evolve better hunting strategies. This feedback loop might have driven rapid diversification. The appearance of hard parts, shells, exoskeletons, teeth might have been a response to predation, armor, and weapons emerging together. There's also a genetic hypothesis. Maybe the Cambrian explosion reflects the evolution of certain developmental genes, Hox genes, and others that control body plan development. Once these genetic toolkits emerged, they allowed evolution to tinker with body structures more easily, creating variations on basic themes. Small changes in developmental timing or gene expression could produce dramatically different body forms, accelerating the pace of evolution. Or perhaps environmental changes played a role. The breakup of supercontinents, changing ocean chemistry, shifting climates, all of these might have created new ecological opportunities, new niches waiting to be filled. Life might have been poised to diversify, held back by environmental constraints that suddenly lifted. Whatever the cause or combination of causes, the result was a creative explosion that defined animal life for the next 500 million years. Almost every major animal group traces its origins to the Cambrian. We're living in the aftermath of that ancient burst of innovation, surrounded by variations on body plans that first appeared when the world was young and strange. And there's something almost poetic about it, isn't there? The idea that life spent billions of years as single cells, then millions of years as simple, soft-bodied creatures, and then suddenly, in a relative instant, discovered complexity, as if the universe had been practicing, learning the rules, and then all at once remembered how to be creative. Now let's venture into the quantum realm, where reality behaves in ways that seem more like magic than physics. Quantum entanglement allows particles to instantly affect each other across any distance, seemingly violating the cosmic speed limit. Einstein called it spooky action at a distance and never accepted it. But experiments prove it's real. We just don't know how. Imagine two particles that have interacted and become entangled. You can separate them. Send one to New York and the other to Tokyo, to opposite sides of the galaxy if you want. And they remain connected in a way that defies our intuitions about space and distance. When you measure a property of one particle, such as its spin, the other particle's spin instantly becomes determined, even though there's no signal traveling between them, no information in the normal sense being transmitted. This isn't just theoretical. Experiments have confirmed entanglement with increasing sophistication for decades. Scientists have entangled photons, electrons, atoms, even small diamonds. They've tested for hidden variables, secret properties the particles might carry with them that predetermine their behavior, and ruled them out. They've closed loopholes that might have allowed for subtle communication between particles at light speed or slower. And every time, the results come back the same. Entanglement is real. The particles genuinely seem to coordinate their properties instantaneously across space. Einstein hated this. It violated his principle that nothing, not even information, can travel faster than light. He proposed that quantum mechanics must be incomplete, that there must be hidden variables we hadn't discovered yet that would restore locality. The principle that objects are only influenced by their immediate surroundings. But experiments, particularly those testing Bell's inequalities in the 1980s and onward, have strongly suggested that Einstein was wrong about this one. The universe really does allow for these non-local correlations. But here's the subtle part. You can't use entanglement to send information faster than light. When you measure your particle, the result appears random to you. Only when you compare your measurements with the measurements from the distant particle do you see the correlations. The message, if there is one, can only be read when you bring the information together through classical means, phone calls, radio signals, things that travel at or below light speed. So causality is safe. You can't send a signal to the past or violate relativity's constraints. But the correlation itself, that strange coordination between distant particles, happens instantaneously. What does it mean? How does it work? We don't really know. Some interpretations of quantum mechanics suggest that entangled particles aren't really separate. They're parts of a single quantum system described by a unified wave function, and distance doesn't mean what we think it means at the quantum level. Others propose that we need to rethink the nature of space and time, that perhaps locality is an approximation that breaks down at fundamental scales. Still, others venture into more exotic territory: multiple worlds, pilot waves, retrocausality, interpretations that trade one weirdness for another. For now, entanglement remains one of the strangest confirmed phenomena in physics. It's being used in emerging technologies: quantum computers, quantum cryptography, quantum teleportation, but the underlying mystery persists. Reality is fundamentally non-local, in some way we don't yet grasp. The universe connects distant things through invisible threads that don't diminish with distance, don't require time to act, and yet somehow don't violate the speed of light. It's the kind of mystery that rewards thinking about obliquely, not forcing an explanation, but letting the strangeness wash over you. Two particles, separated by an ocean or a galaxy, dancing in perfect correlation, neither leading, neither following, just moving together in a way that transcends space. Maybe that's what the universe is. Not a collection of separate things, but a unified whole that we perceive as separate only because of the limitations of our senses and instruments. Or maybe it's stranger than that. Maybe it's something we don't have words for yet. Here's a mystery from our own explorations of space, a subtle anomaly that hints at missing pieces in our understanding. The Pioneer spacecraft are slowing down more than they should, pulled by an unknown force that defies our equations. This Pioneer anomaly might be simple thermal radiation, or it might mean we're missing something fundamental about gravity. Pioneer 10 and Pioneer 11, launched in the early 1970s, were humanity's first emissaries to the outer solar system. They visited Jupiter and Saturn, sent back stunning images, and then continued outward into interstellar space. Their trajectories carefully calculated based on our understanding of gravity, orbital mechanics, and the forces acting on spacecraft in the void. But as they traveled farther from the sun, something strange appeared in the data. The spacecraft were slowing down, decelerating more than they should be. The effect was tiny, about 8.74 x 10 wards 10 meters per second squared, which is roughly the width of an atom per second squared. At that rate, it would take years to notice any significant deviation. But over decades of tracking, the anomaly became undeniable. The Pioneers weren't where they should be. Something was pulling them back toward the sun, or at least slowing their outward journey, by an amount our models couldn't explain. At first, researchers checked for known forces. Solar wind, too weak at that distance. Gravitational influence from planets or the Kuiper Belt, already accounted for. Gas leaks from the spacecraft systems. The Pioneers used radioactive thermoelectric generators, not rockets, so there was no fuel to leak. Errors in the tracking data, meticulously ruled out. The effect was real, consistent, and puzzling. For decades, the Pioneer anomaly tantalized physicists. Could it be evidence for modified gravity at large scales? Perhaps a hint that Newtonian physics, or even general relativity, needed adjustment. Maybe gravity doesn't quite follow an inverse square law at astronomical distances. Maybe there's a subtle additional force, something like a cosmological acceleration or a drag from the quantum vacuum. Some researchers even wondered if it could be related to dark matter or dark energy, those mysterious components that dominate the universe's mass and energy but remain invisible. The most mundane explanation, however, turned out to be the most likely. Detailed analysis in the 2000s, using recovered telemetry and sophisticated thermal modeling, suggested that the anomaly could be explained by something beautifully simple: anisotropic thermal radiation. The spacecraft's radioactive power sources generate heat, and that heat radiates into space. If more heat radiates from the front of the spacecraft than the back, perhaps because of how the components are arranged, how heat conducts through the structure, then the spacecraft experiences a tiny recoil force pushing it backward. It's essentially a very, very gentle rocket thrust created by infrared photons. The calculations worked. The magnitude matched. The Pioneer anomaly appeared to be solved without invoking new physics, just careful accounting for how heat behaves in space. But here's the thing, we're not entirely certain. The thermal explanation is compelling and probably correct, but it required extensive analysis of engineering details from spacecraft built half a century ago, with some assumptions about material properties and heat distribution. There's still a small possibility that something else is at play, or that the thermal effect is only part of the story. And that's where the mystery settles now, probably solved, but with just enough uncertainty to keep it interesting. The universe might not be revealing new physics through the Pioneer anomaly, but it reminded us that even in a domain we think we understand, orbital mechanics, gravity, spacecraft navigation, there's room for surprise. The cosmos is vast, and subtle effects we've never had the sensitivity to measure before might be waiting in the data, hints of deeper truths we haven't imagined yet. Let's come back to Earth now, to something strange and intimate and frustrating. Some people can hear a mysterious, low-frequency hum that drives them to distraction, but scientists can't locate its source. The hum has been reported worldwide since the 1960s, audible only to about 2% of people in affected areas. Imagine hearing a low, persistent drone, like a diesel engine idling in the distance, or a piece of heavy machinery running somewhere just out of sight. You hear it in your home, especially at night when other sounds fade. You check for appliances, for trucks outside, for industrial facilities nearby. But you can't find the source. You move to a different room and it follows you. Sometimes it's louder, sometimes quieter, but it's always there, a presence in your auditory landscape that no one else seems to notice. This is the experience of hum sufferers. They report the sound most commonly at frequencies between 30 and 80 hertz, very low, at the edge of human hearing. Some describe it as pulsing or throbbing. Many say it's worse indoors than outdoors, worse at night than during the day, worse in rural areas than in cities where ambient noise might mask it. And here's the truly strange part. When researchers bring in sensitive microphones and spectrum analyzers, they often can't detect anything unusual. The instruments register only the normal background hum of modern life: distant traffic, wind, electrical grids. So what's going on? Is it psychological? Tinnitus, perhaps, manifesting as a low-frequency sound rather than the typical high-pitched ringing. Some cases might be, but not all. Many hum hearers have been tested for hearing disorders and found to have normal hearing or even unusually sensitive low-frequency perception. Some researchers think the hum might be real, but extremely difficult to detect. Perhaps infrasound or very low-frequency radio waves that certain people can somehow perceive, maybe through bone conduction or through electromagnetic sensing we don't normally acknowledge. One compelling theory points to VLF, very low frequency, radio transmissions, used by submarines and some industrial applications. These signals can propagate enormous distances and might interact with objects, or even the human auditory system in unexpected ways. Another idea focuses on seismic activity, or microseisms, tiny vibrations in the earth that could resonate in buildings or landscapes, at frequencies some people detect. There's also the possibility of industrial sources: ventilation systems, pumps, compressors, power stations, any of which might produce low-frequency noise that carries farther than expected and affects only those with particular sensitivity. The geographic distribution is curious. The Taos hum in New Mexico, the Windsor hum in Ontario, the Bristol hum in England. These are some of the most studied cases, places where significant numbers of people report hearing the same phenomenon. Investigations have been launched, including some by government agencies, but definitive sources have been elusive. In Windsor, researchers eventually identified a potential source: industrial operations on Zug Island, across the river in Michigan. But even there, the connection wasn't airtight, and not everyone agreed the island explained all the reports. What makes the hum particularly mysterious is its selectivity. Why do only some people hear it? If it's a real sound, why don't instruments reliably detect it? If it's perceptual or neurological, why does it seem to concentrate in specific locations? The answers probably vary case by case. Some instances might be industrial, others geological, still others psychological. But the persistence of the reports, the global distribution, the consistent descriptions across cultures suggest there's something real here, even if we haven't pinned it down yet. For those who hear it, the hum is more than a curiosity. It's a presence, sometimes distressing, sometimes just puzzling, always unexplained. And perhaps that's a small reminder that our sensory experiences aren't as universal as we assume. We each inhabit a slightly different perceptual world, tuned to different frequencies, sensitive to different signals. The universe might be sending out more information than we realize. And some people are simply picking up channels the rest of us never knew existed. Here's a mystery so fundamental we rarely notice it, woven into every moment of your existence. We don't know why time only flows forward, or why we can remember the past but not the future. The laws of physics work equally well in both directions, yet we're trapped in a universe where entropy always increases. Think about this for a moment. Every equation in physics, the laws governing how particles interact, how forces work, how energy transfers from one form to another, these equations are time-symmetric. If you filmed a collision between two billiard balls and played it backward, the reversed motion would still obey Newton's laws perfectly. The same is true at the quantum level, at the cosmic level. The fundamental rules of reality don't care which direction time flows. They work just as well, backward as forward. And yet your life has an undeniable direction. You remember yesterday but not tomorrow. Eggs break but don't spontaneously reassemble. Coffee cools but never spontaneously heats up. Stars burn hydrogen into heavier elements, not the reverse. The universe seems to have a preferred direction, an arrow pointing from past to future, and that arrow is associated with something called entropy, roughly speaking, a measure of disorder or the number of possible arrangements a system can have. The second law of thermodynamics states that in a closed system, entropy always increases or stays the same. It never decreases. This gives time its arrow. The future is the direction in which entropy increases, in which order breaks down into disorder, in which energy spreads out and becomes less useful. But here's the mystery. Why? Why does entropy increase? And more puzzlingly, why was entropy so low in the early universe? If the universe began in a high entropy state, maximum disorder, everything spread out evenly, then there would be no arrow of time, no direction for change. But the Big Bang appears to have been an extraordinarily low entropy event. All the matter and energy of the universe concentrated in an incredibly tiny, hot, ordered state. And from that moment forward, entropy has been increasing. The universe has been spreading out, cooling down, becoming more disordered. Galaxies formed, stars ignited, planets coalesced. All of these are local decreases in entropy, but they're powered by larger increases elsewhere. The sun creates order on Earth by increasing disorder in its own burning core. So why did the universe start with low entropy? We don't know. It seems almost arbitrary, like an initial condition someone set when starting a simulation. Some physicists speculate that it has to do with gravity, that in the early universe, gravitational clumping represents a special kind of low entropy state. Others wonder if our universe is just one region of a larger multiverse, and we exist in a pocket where entropy happened to start low, for the same reason that we exist on a planet with liquid water and breathable air. We couldn't be anywhere else. There's also a deep connection between entropy and information, between the second law of thermodynamics and the nature of memory and consciousness. You remember the past because your brain contains records, physical traces of previous states. Making those records requires increasing entropy elsewhere. Memory itself is bound to the arrow of time. If entropy could decrease as easily as it increases, there would be no persistent records, no memory, no sense of cause and effect. The universe would be fundamentally different, perhaps uninhabitable by anything that thinks. Some physicists have even proposed that time itself might be an emergent property, something that arises from the statistical behavior of vast numbers of particles rather than being fundamental to reality. At the deepest level, the quantum foam, the Planck scale, time might not flow at all. It might be more like another dimension of space, directionless, symmetric. And what we experience as time's passage might be a kind of illusion created by entropy's increase, by the way our brains process patterns in the arrangement of particles. But that raises its own questions. If time is an illusion, who's being fooled? If consciousness itself is a pattern unfolding in time, can we step outside time enough to see it as an illusion? We're back to the hard problem of consciousness, circling around the same deep mysteries from different angles. Why does it feel like something to be a consciousness moving through time? Why do we experience this moment, this now, this present that seems to glide forward from past to future? Perhaps the answer is that we don't know, and maybe can't know, because we're made of time, embedded in it, unable to see it from outside. We're like fish trying to understand water. It's the medium we exist in, so fundamental to our being that we might never fully grasp it. Time flows, entropy increases, memories accumulate, and we ride this arrow wherever it points, into a future we can't see but can't help but move toward. Let's shift to something controversial, something that sits uncomfortably at the boundary between science and impossibility. The impossible EM drive appears to generate thrust without propellant, violating conservation of momentum. Multiple labs have detected thrust from this device, but it shouldn't work according to known physics. If it's real, it rewrites the rules. Conservation of momentum is one of the most fundamental principles in physics. If you throw something in one direction, you recoil in the other. Rockets work by expelling exhaust at high speed. The momentum of the exhaust going backward equals the momentum of the rocket going forward. It's elegant, simple, and seemingly inviolable. Every form of propulsion we've ever invented relies on pushing against something: air, water, ground, or expelled propellant. The EM drive doesn't seem to push against anything. It's essentially a closed metal cavity, shaped like a truncated cone, into which you pump microwaves. That's it. No exhaust, no moving parts, no propellant expelled. According to everything we understand about physics, it should just sit there, the microwaves bouncing around inside, maybe heating up the walls, but producing zero net thrust. And yet, when researchers test these devices, they measure thrust. Small thrust, tiny, really, just a few micronewtons, but consistent, repeatable thrust. The British engineer Roger Scheuer first proposed the concept in the early 2000s, claiming that the asymmetric cavity shape would cause the microwaves to produce more radiation pressure on one end than the other, creating thrust. Physicists immediately objected. That's not how momentum works. The radiation pressure inside a closed cavity cancels out. There's no external interaction, so there can be no net force. Scheuer's explanation didn't hold up to scrutiny, but then other labs started testing. NASA's EagleWorks laboratory measured thrust from an EM drive in 2016. Chinese researchers reported positive results. Independent teams found similar effects. The thrust was always small, right at the edge of what the instruments could reliably measure, but it seemed real. And that's when things got interesting, because if the effect is genuine, it means one of several very strange things must be true. Maybe the device is pushing against quantum vacuum fluctuations, those virtual particles that pop in and out of existence in empty space. Maybe it's interacting with the fabric of space-time itself in some way we don't understand. Maybe there's a subtle energy transfer happening through fields or dimensions we haven't detected. Or maybe, and this is the option most physicists lean toward, the measured thrust is an experimental artifact, a systematic error in measurement caused by thermal expansion, electromagnetic interference, seismic vibration, or some other mundane effect that happens to correlate with the microwave power. The challenge is that measuring tiny forces is extraordinarily difficult. You need to isolate your apparatus from vibration, temperature changes, electromagnetic fields, air currents, any of which can produce forces in the range of micronewtons. You need to account for cable forces, thermal radiation, even the interaction of magnetic fields with the Earth's field. Multiple teams have reported null results or retracted initial positive findings after identifying error sources. The more carefully controlled the experiments, the weaker or more ambiguous the thrust signals become. And yet, the effect hasn't been definitively disproven. It lingers in the literature, reproduces occasionally, and continues to attract attention because of what it would mean if real. A propulsion system that requires no propellant would revolutionize space travel. You could accelerate continuously without carrying tons of fuel, reaching relativistic speeds given enough time and power. The outer solar system, even nearby stars, would become accessible in ways they currently aren't. So where does that leave us? In limbo, essentially. The EM drive might be a measurement artifact that will eventually be explained away, another example of how challenging precision physics can be. Or it might be a genuine anomaly pointing toward new physics, something subtle that emerges only under specific conditions and hasn't been properly understood yet. Most physicists bet on the former, but a few, intrigued by the persistence of the reports, Wonder about the latter. It's a reminder that science is a process, not a fixed body of knowledge. We have principles that work extraordinarily well, like conservation of momentum, but we hold them tentatively, ready to modify or discard them if reality demands. The universe doesn't care about our laws. It does what it does, and we try to describe it as accurately as possible. If the EM drive works, we'll need better descriptions. If it doesn't, we'll have learned something valuable about experimental error and the care needed when measuring at the limits of precision. Either way, the mystery teaches us something. Now let's turn to something living, something delicate and beautiful and utterly mysterious in its competence. Monarch butterflies migrate thousands of miles to a specific forest in Mexico they've never seen, using a navigation system we barely understand. These insects use the sun, Earth's magnetic field, and possibly quantum effects in their eyes to find their way across generations. Every autumn, millions of monarch butterflies from eastern North America begin a journey. They travel from as far as Canada, from forests and fields and gardens, all converging on a destination none of them have ever visited. A small region of Oyamel fir forests in the mountains of central Mexico. The area they're targeting is tiny, geographically speaking, just a few hectares of specific forests, at specific elevations, in specific microclimates, that provide the cool temperatures and humidity needed for the butterflies to survive the winter. Here's what makes this remarkable. The butterflies making this journey are not the same individuals that made it the year before. Monarchs that emerge in late summer undergo a physiological change. Instead of reproducing immediately like earlier generations, they enter a state called reproductive diapause. Their bodies focus on fat storage and energy conservation instead of mating. They live months instead of weeks, and they fly south. These butterflies have never seen the Mexican forests. Their parents didn't make the journey either. It takes 4 or 5 generations for the monarchs to complete their annual cycle. The butterflies that migrate south are the great-great-grandchildren of those that migrated north the previous spring. Yet somehow, they know where to go. They navigate across an entire continent, adjusting their flight paths to account for wind and weather, and they zero in on forests their ancestors visited generations ago. How? The navigation system is complex, multi-layered, and still not fully understood. Part of it involves the sun. Monarchs have a time-compensated sun compass in their brains. They can determine direction by the sun's position and adjust for the time of day, accounting for the sun's apparent movement across the sky. This is already sophisticated. It requires an internal clock and the ability to integrate temporal and spatial information. But there's more. Monarchs can also sense Earth's magnetic field, using it as a backup navigation system when skies are cloudy. The mechanism appears to involve a protein called cryptochrome in their antennae, and possibly their eyes. Cryptochrome is light-sensitive and may use quantum entanglement. Pairs of electrons whose spins become correlated when exposed to blue light to detect the subtle differences in magnetic field orientation. This is quantum biology in action, macroscopic organisms using quantum effects to sense their environment. The monarchs also rely on genetic programming, an inherited sense of direction and distance. Researchers have found that if you relocate monarchs during migration and release them, they don't head toward Mexico. they head in the direction they would have been flying if they hadn't been moved, suggesting they're following an internal vector rather than homing in on a specific target. Only as they get closer do local cues, perhaps landscape features, scents, or microclimatic conditions, help them pinpoint the exact forests. There's something profound about this. A tiny insect, with a brain smaller than a grain of rice, contains the computational capacity to integrate celestial navigation, geomagnetic sensing, temporal awareness, and genetic programming to execute a multi-thousand-mile journey it has never made before. And it works. Millions of butterflies arrive each year in the same handful of forests, clustering on the same trees their ancestors used, sometimes even on the same branches. We're still piecing together the details. How is the navigational information encoded genetically? How do the quantum processes in cryptochrome translate into directional information the butterfly can use? What happens in the neural circuits that process all this sensory input and convert it into flight behavior? Every answer raises new questions, and there's a melancholy edge to this mystery now, because the monarchs are declining. Habitat loss, pesticides, climate change, all threaten both the butterflies and the specific forests they depend on. This ancient navigation system, honed over millions of years of evolution, might lead the butterflies to destinations that no longer exist or no longer provide what they need. We're learning how monarchs navigate just as we're disrupting the world they navigate through. But for now, on autumn days, they still fly. Fragile orange wings riding thermals and tailwinds, a living river flowing south, each butterfly a tiny miracle of biology and physics, carrying secrets we're only beginning to understand. Here's a thought experiment that becomes more unsettling the longer you consider it. The Silurian hypothesis asks how we detect an industrial civilization that existed on Earth millions of years before humans. Erosion and plate tectonics erase most evidence. We might never know if we're the planet's first technological species. The name comes from Doctor Who. The Silurians were a fictional reptilian species that supposedly ruled Earth before humans. But the hypothesis itself is serious science, proposed by astrophysicist Adam Frank and climatologist Gavin Schmidt in 2018. They weren't suggesting ancient industrial civilizations actually existed. They were asking, if they had existed, would we be able to find evidence? The answer is more uncertain than you might think. Humans have been around for perhaps 300,000 years, an industrial civilization for only about 200 years. The fossil record suggests complex life has existed for over 500 million years. That's an immense span of time. If an industrial civilization rose and fell sometime in, say, the Cretaceous period, 100 million years ago, would anything remain for us to find? Buildings and cities would be gone, obviously. Erosion, weathering, and tectonic activity would pulverize anything on the surface. Even fossilization is rare and selective. It requires specific conditions that preserve only a tiny fraction of organisms that lived. The odds of finding a fossilized tool or artifact from a civilization that existed briefly millions of years ago are vanishingly small. Most of the Earth's surface from 100 million years ago has been subducted, uplifted, eroded away, or buried under miles of sediment. But Frank and Schmidt suggested looking for indirect signatures. An industrial civilization would alter the planet's chemistry. They'd mine rare elements and redistribute them. They'd change the ratio of carbon isotopes in the atmosphere through fossil fuel burning. They'd create synthetic molecules, plastics, PCBs, CFCs, that don't occur naturally. They'd potentially cause mass extinctions through habitat destruction or climate change. All of these might leave traces in the geological record as anomalous layers or chemical signatures in ancient rocks. The problem is distinguishing those signatures from natural events. The Earth has experienced multiple mass extinctions from asteroids, volcanism, and climate shifts. Carbon isotope ratios have fluctuated for many reasons. Even plastics, though synthetic, eventually break down into microparticles that might be hard to identify millions of years later. And the further back you go, the more ambiguous the evidence becomes. Rocks from the Paleozoic, 250 million years ago and older, have been heated, crushed, metamorphosed, making subtle chemical signatures harder to read. There's also the question of duration. How long would an industrial civilization need to last to leave detectable traces? Human civilization might create an identifiable layer, the Anthropocene, some geologists call it, marked by concrete, microplastics, radioactive isotopes from nuclear testing, and a spike in carbon emissions. But if civilization collapsed suddenly and the planet recovered over tens of millions of years, those markers might fade or become ambiguous. A civilization that lasted only a few thousand years, rising, flourishing, and vanishing, might leave almost nothing we could recognize. Does this mean ancient industrial civilizations existed? Almost certainly not. Evolution has a traceable history on Earth, and there's no evidence of any species developing complex technology before humans. Intelligence is rare, and technological intelligence even rarer. But the hypothesis highlights an uncomfortable truth. Deep time erases things. The further back you look, the less certain you can be about what didn't exist. We assume we're Earth's first technological species, and we're probably right. But the evidence for that assumption is less ironclad than you might think. And if we apply this thinking to other planets, to Mars, for instance, which had surface water billions of years ago, it becomes even more intriguing. If life arose on Mars and somehow developed intelligence during that brief habitable period, would we recognize the traces now? The planet has been geologically dead for ages, its surface scoured by radiation and dust storms. Any ancient cities would be dust. Any fossils would be rare and hard to find. We'd be looking for chemical anomalies in rocks billions of years old, trying to distinguish civilization from geology. It's a daunting prospect. The Silurian hypothesis doesn't claim anything extraordinary. It simply reminds us that absence of evidence isn't always evidence of absence, especially when enough time has passed to erase the evidence. The universe is old, planets are dynamic, and the past is more uncertain than we usually admit. We're probably the first, probably alone in our planet's history, but probably isn't the same as certainly, and that gap, however small, leaves room for wonder. Let's return to life now, but to a form so extreme it seems more alien than earthly. Some tardigrades survived being frozen for 30 years, and we don't fully understand how they essentially pause life itself. These microscopic creatures can withstand radiation, vacuum, and extreme temperatures by replacing their water with protective sugar molecules. Tardigrades, also called water bears because of their stumpy, bear-like appearance under a microscope, are perhaps the most resilient animals on Earth. They're tiny, usually less than a millimeter long, living in moss, lichen, soil, and aquatic sediments worldwide. Under normal conditions, they lumber around on 8 legs, eating bacteria and plant cells, living unremarkable lives. But when conditions turn harsh, when their environment dries out, freezes, or becomes toxic, they do something extraordinary. They transform into a state called cryptobiosis, a kind of suspended animation where metabolic activity becomes undetectable. The tardigrade pulls in its legs, expels most of its water, and forms a structure called a tun, a compact desiccated barrel that can survive conditions no active organism could endure. In this state, tardigrades have survived temperatures near absolute zero and above boiling. They've been exposed to vacuum in space experiments and survived. They can withstand pressures 6 times greater than the deepest ocean trenches. They've been subjected to radiation doses that would liquefy human tissue. And they've been revived after decades, in some cases over 30 years, of dormancy. How is this possible? The key seems to be what happens to their cells during desiccation. Water is essential for life. Biochemical reactions occur in aqueous solution. Proteins need water to maintain their shape. DNA requires hydration to remain stable. Remove the water, and normally everything falls apart. Proteins denature, membranes collapse, DNA breaks. The cell dies. Tardigrades avoid this by replacing water with other molecules, primarily a sugar called trehalose. As the tardigrade dries out, trehalose concentrations increase inside its cells, forming a glassy matrix that effectively preserves cellular structures in place. Proteins are held in their functional configurations. Membranes are stabilized. DNA is protected from breaking. It's like amber preserving an ancient insect, except here the preservation medium is sugar molecules surrounding every structure within the cell. But there's more to it than just sugar. Tardigrades also produce unique proteins called tardigrade, specific intrinsically disordered proteins, TDPs. These proteins don't fold into stable shapes like most proteins. Instead, they form flexible networks that protect other molecules from damage. They might prevent aggregation of cellular components, shield DNA from radiation, or provide additional structural support during cryptobiosis. Researchers are still working out the details, but it's clear that tardigrades have evolved a sophisticated molecular toolkit for surviving the unsurvivable. And then there's the question of how they revive. When water becomes available again, the tun absorbs it, the trehalose dissolves, the proteins and membranes rehydrate, and metabolism restarts. Within hours, the tardigrade is active again, apparently undamaged by its ordeal. Some research suggests there is cumulative damage. Cryptobiosis isn't perfectly reversible, but the repair mechanisms are efficient enough that tardigrades can undergo the cycle many times. What does this tell us about the nature of life? Traditionally, we define life by its activity. Metabolism, growth, reproduction, response to stimuli. But a tardigrade in cryptobiosis does none of these things. It's effectively dead by most definitions, yet it retains the capacity to return to life. It's poised between states, neither fully alive nor fully dead, waiting for conditions that permit activity. This has implications for astrobiology. If Earth organisms can survive decades in cryptobiosis, perhaps life could spread between planets, carried on meteorites ejected by impacts. Mars rocks have reached Earth. Earth rocks have probably reached Mars. If tardigrades or their microbial equivalents were embedded in those rocks, could they survive the journey through space, the vacuum, the radiation, the cold, and revive on arrival? It's possible. Panspermia, the idea that life can spread from world to world, becomes more plausible when you realize how resilient life can be. And there's something philosophically interesting here. Life, at its core, might not require constant activity. It might be more about potential, the ability to be active, to metabolize, to grow, given the right conditions. A tardigrade in cryptobiosis carries within it the memory of life, the instructions and structures needed to live, all preserved in a state of biochemical suspension. Its life waiting to happen, paused, but not erased. In a universe that tends toward entropy and decay, that's a remarkable achievement. A tiny animal that learned to press pause on itself, to wait out catastrophe, to persist against all odds. Let's shift perspective now to something massive and ceaseless that shapes global climate in ways we're still discovering. The Antarctic Circumpolar Current is the largest ocean current on Earth, and we're still discovering how it regulates global climate. This river in the ocean, flowing eternally around Antarctica, acts as a barrier that isolated an entire continent for millions of years. Imagine a current of water flowing uninterrupted around the globe. In most places, ocean currents are constrained by continents. They flow between land masses, circulate in ocean basins, but eventually they hit a shore and have to turn. But in the Southern Ocean, something unique happens. There's no continent blocking the flow at the latitudes where Antarctica sits. The current can circle the planet endlessly, driven by powerful westerly winds and the Earth's rotation, forming a vast ring of moving water. This isn't a small stream. The Antarctic Circumpolar Current transports more water than any other current on Earth, somewhere between 130 and 180 million cubic meters per second. For comparison, all the world's rivers combined discharge about 1.2 million cubic meters per second into the oceans. This single current moves more than 100 times that amount. It's like a river wider than continents, deeper than mountains, flowing through the southern seas with a volume that dwarfs anything on land. And it's cold. The current circulates around Antarctica, mixing frigid waters from near the continent with slightly warmer waters from lower latitudes, but remaining cold enough to act as a barrier. Warm waters from the Atlantic, Pacific, and Indian Oceans have difficulty crossing this boundary. The current essentially isolates Antarctica, keeping it refrigerated, maintaining the conditions that allow its massive ice sheets to exist. If the Antarctic Circumpolar Current were to weaken or shift significantly, more warm water could reach the continent, potentially accelerating ice melt and contributing to sea level rise. But the current's influence extends far beyond Antarctica. It connects all three major ocean basins, the Atlantic, Pacific, and Indian Oceans, creating a global mixing system. Water sinks in the North Atlantic, flows south, joins the Antarctic Circumpolar Current, gets carried around the continent, and then upwells and spreads northward into the Pacific and Indian Oceans. This is part of the global thermohaline circulation, sometimes called the global conveyor belt, which distributes heat and nutrients throughout the world's oceans. Changes in the Antarctic Circumpolar Current could affect climate patterns worldwide, altering rainfall, storm tracks, and temperature distributions in regions thousands of miles away. We're still learning how the current responds to climate change. Some studies suggest it's strengthening as winds over the Southern Ocean intensify. Others find evidence of shifts in its position or structure. The current interacts with atmospheric patterns like the southern annular mode, with Antarctic ice shelves, with upwelling of deep waters that bring ancient carbon and nutrients to the surface. These interactions create feedback loops. Warming temperatures affect wind patterns, which affect the current, which affects ice melt, which releases fresh water that changes ocean salinity, which affects the density of water and how it sinks or rises. It's a complex system with many moving parts, and we're still mapping the connections. There's also a deep time perspective. The Antarctic circumpolar current is relatively young, geologically speaking. It began forming about 30 to 34 million years ago when the Drake Passage, the gap between South America and Antarctica, opened wide enough for the current to flow through. Before that, Antarctica was warmer, connected or nearly connected to other continents, and covered in forests rather than ice. The formation of the current helped isolate the continent, initiating the conditions for permanent glaciation. In a sense, the current created the Antarctica we know today, frozen, remote, a land governed by ice. What happens if the current changes? Climate models suggest that as the planet warms, the Southern Ocean could warm too, potentially altering the current's strength or position. If more warm water reaches Antarctica, ice melt accelerates. If the current shifts latitude, it could affect storm tracks and precipitation patterns across the southern hemisphere. If the global conveyor belt is disrupted, the consequences could be felt in ocean chemistry, marine ecosystems, and climate worldwide. We're watching carefully, monitoring, trying to understand a system that operates on scales of space and time that challenge human intuition. And meanwhile, the current flows. Day and night, year after year, millions of cubic meters per second circling endlessly around the bottom of the world, connecting oceans, shaping climate, carrying nutrients and cold water and ancient secrets from deep below the surface. It's been flowing longer than our species has existed, longer than civilizations have risen and fallen. A river in the sea, eternal and indifferent, following the wind and the spin of the planet, keeping its course through the cold southern waters. Let's close this section with something gentler, a mystery of delicate interactions between living things. Bees can detect the electric fields of flowers using a sense we didn't know existed until recently. Flowers build up a negative charge while bees become positively charged in flight, creating an invisible communication channel. Picture a bee flying through a summer garden. We usually think of bees navigating by vision, seeing the colors and patterns of flowers, and by scent, detecting the chemical signatures of nectar and pollen. Both are true, but there's another layer we only recently discovered. Every time a bee flies, friction with the air strips electrons from its body, leaving it with a positive electric charge. Meanwhile, flowers, rooted in the ground, connected to the Earth's negative charge, build up a negative charge on their petals. When a bee approaches a flower, these charges interact. The bee can sense the flower's electric field, possibly through mechanoreceptors in its body, tiny hairs that bend in response to electrical forces. This gives the bee information about the flower even before landing. Different flower species have different electric field patterns, depending on their shape, petal arrangement, and the distribution of charge across their surface. The bee might be able to identify flowers by their electrical signature, adding another dimension to its foraging decisions. But it's more than just detection. The electric field can carry information. When a bee lands on a flower and drinks its nectar, the interaction changes the flower's electric field. The charge temporarily shifts or neutralizes slightly. Other bees approaching can detect this change, learning that the flower was recently visited and might have less nectar. It's a signal, a form of communication mediated through physics rather than chemistry, an electromagnetic handshake between insect and plant. We don't fully understand all the implications yet. Does the electric sense help bees navigate in conditions where visual cues are limited? At dusk, for instance, or in the shade? Do flowers actively manipulate their electric fields to attract or repel certain pollinators? Are there electric field patterns that signal toxicity or reward? And what about other pollinators, butterflies, hummingbirds, bats? Do they sense electric fields too? Or is this unique to bees? There's also a concerning angle. Human activity has changed the electrical environment in subtle ways. Power lines, electronics, radio transmissions, all of these create electromagnetic fields that might interfere with the natural electric signals between flowers and bees. We don't yet know if this interference is significant, but it's another variable in the complex equation of pollinator health, which is already challenged by habitat loss, pesticides, and climate change. What strikes me about this discovery is how much we didn't know. Bees and flowers have coexisted for over 100 million years, evolving together, shaping each other's evolution. We've studied them for centuries, their anatomy, behavior, ecology. And yet, this entire sensory channel, this electrical dimension of their interaction, remained hidden until scientists in the 21st century thought to look for it. How many other sensory systems exist that we haven't imagined? How many ways do organisms perceive and communicate that remain invisible to us because we don't share those senses? It's a reminder that the world is richer than it appears. When you watch a bee visiting a flower, you're seeing a transaction mediated by color, scent, shape, texture, and, invisibly, electricity. The flower and the bee are locked in an ancient conversation, speaking in multiple languages simultaneously, exchanging information through channels both visible and hidden. And we, watching from outside, are only beginning to learn the vocabulary. Here's a mystery from the early 20th century that still puzzles researchers today. The Tunguska event in 1908 flattened 800 square miles of Siberian forest, but we found no crater or meteorite fragments. The leading theory is an asteroid or comet that exploded in mid-air, but alternative explanations from mini black holes to natural gas explosions persist. On the morning of June 30th, 1908, something streaked across the sky over the Yenisei River basin in Siberia. Witnesses hundreds of miles away saw a brilliant fireball, brighter than the sun, moving across the sky from southeast to northwest. Then came the explosion. The blast was so powerful that it registered on seismographs across Europe and Asia. The shock waves circled the Earth twice. In Britain, the night sky glowed bright enough that people could read newspapers at midnight, a phenomenon that lasted for several days. But the location was remote, deep in the Siberian taiga, a vast wilderness of pine and larch forest, hundreds of miles from any significant settlement. It took nearly 2 decades before the first scientific expedition reached the site. What they found was extraordinary and puzzling. Trees were flattened radially outward from a central point, knocked down like matchsticks, their branches stripped away. An area of about 830 square miles had been devastated. At the epicenter, some trees remained standing, though they were charred and stripped of branches. The blast had come from directly above, so there was no lateral force to knock them over. But there was no crater, no impact site, no meteorite fragments, at least none that could be definitively linked to the event. Whatever had caused the explosion had apparently detonated in the air, probably at an altitude of 5 to 10 kilometers. The energy released was estimated at 10 to 15 megatons, roughly 1,000 times more powerful than the Hiroshima atomic bomb. If the object had arrived a few hours later, as Earth rotated beneath its trajectory, it might have destroyed St. Petersburg or another major city. As it was, the remoteness of the location meant that casualties were minimal. A few reports of people knocked down or injured by the shock wave. Some reindeer killed, but no confirmed human deaths. So what was it? The most widely accepted explanation is an asteroid or comet, probably 50 to 100 meters across, entering Earth's atmosphere at high speed. The immense friction and pressure as it plowed through the air heated and compressed the object, building up stresses until it exploded catastrophically. This would explain the air burst, the lack of a crater, and the energy release. Comets, being more fragile, essentially dirty snowballs, would be particularly likely to explode rather than reach the ground intact. But the absence of meteorite fragments is puzzling. You'd expect at least some material to survive, some residue to rain down on the forest. Researchers have found microscopic particles, tiny spherules of melted rock and metal in the soil that might be remnants of the impactor, but nothing definitive. Some studies suggest chemical signatures consistent with a stony asteroid or comet, but the evidence is ambiguous. This ambiguity has allowed alternative theories to flourish. Some early researchers proposed that it was a natural gas explosion, methane or other gases erupting from the ground and igniting. But the radial pattern of destruction and the eyewitness accounts of a fireball in the sky make this unlikely. Others have suggested a small black hole passing through the Earth, though this would have created a second explosion when it exited on the other side, which wasn't observed. There have been proposals involving antimatter, alien spacecraft crashing, secret scientific experiments, even geophysical phenomena we don't understand. Most of these can be ruled out with varying degrees of confidence, leaving us with the cosmic impact hypothesis as the most plausible explanation. But the lack of definitive physical evidence means we can't close the case completely. We're fairly certain something from space exploded over Siberia in 1908, but the exact nature of that something, its composition, its origin, whether it was an asteroid or comet or something else, remains just uncertain enough to keep the mystery alive. And there's a practical angle to this. Tunguska reminds us that Earth is still bombarded by objects from space, and while most are small and harmless, occasionally something larger arrives. If Tunguska happened today over a populated area, the consequences would be catastrophic. We're now scanning the skies for potentially hazardous asteroids, trying to catalog anything that might threaten us. But smaller objects, the Tunguska-sized impactors, are harder to detect and track. They're out there, orbiting, and one day another might arrive. We probably won't have much warning, just a bright light in the sky, a few moments of wonder, and then the shockwave. Now let's venture into the quantum realm of materials science, where substances behave in ways that defy classical physics. Some materials become superconductors at unexpectedly high temperatures, defying theoretical predictions about how this should work. We've discovered materials that conduct electricity with zero resistance, but we can't explain the mechanism behind high-temperature superconductivity. Superconductivity was discovered in 1911 when Dutch physicist Heike Kamerlingh Onnes cooled mercury to just a few degrees above absolute zero and found that its electrical resistance vanished completely. Not just became very low, disappeared entirely. Current flowing through a superconducting loop would continue circulating forever, without any energy loss, without any need for a power source. It was a phenomenon unlike anything in everyday experience. For decades, superconductivity was understood fairly well within certain limits. At very low temperatures, close to absolute zero, electrons in certain materials form pairs, Cooper pairs, they're called, that move through the crystal lattice without scattering off atoms or defects. This pairing is mediated by vibrations in the crystal structure, phonons, and it only works when thermal energy is low enough that it doesn't break the pairs apart. The theory, developed in 1957 by Bardeen, Cooper, and Schrieffer, BCS theory, explained conventional superconductors beautifully and predicted an upper limit to the temperature at which superconductivity could occur. Around 30 Kelvin, or about 243 degrees Celsius. Then in 1986, everything changed. Researchers discovered superconductivity in a ceramic material, a copper oxide compound, at 35 Kelvin. That was already slightly above the BCS limit, which was surprising. But then more copper oxide superconductors were found, with critical temperatures climbing rapidly. 50 Kelvin, 77 Kelvin, warmer than liquid nitrogen, which is a huge practical threshold, even up to 133 Kelvin in some compounds. These were dubbed high-temperature superconductors, even though 133 Kelvin is still 140 degrees Celsius, cold by everyday standards, but remarkably warm for a superconductor. The problem is, we don't fully understand how these high-temperature superconductors work. BCS theory doesn't apply. The phonon-mediated pairing mechanism isn't strong enough to explain superconductivity at these temperatures. The materials themselves are complex, layered structures with copper and oxygen, often doped with other elements, exhibiting strange magnetic and electronic properties even above their critical temperatures. They're not simple metals. They're correlated electron systems where interactions between electrons are strong and complicated. Physicists have proposed dozens of theories. Maybe the pairing is mediated by magnetic fluctuations instead of phonons. Maybe there are exotic quantum states involved, charge density waves, spin fluctuations, quantum criticality. Maybe the layered structure creates quasi-two-dimensional electron behavior that enhances pairing. There are hints and clues in experiments, patterns in how the critical temperature depends on doping, anomalies in heat capacity and magnetic susceptibility, but no single theory has emerged as definitive. Different researchers favor different mechanisms, and the debate continues. Meanwhile, the search for even higher critical temperatures goes on. In 2015, researchers found that hydrogen sulfide under extreme pressure, around 1.5 million atmospheres, becomes superconducting at 203 Kelvin, about 70 degrees. That's warmer than some winter days in Antarctica, warmer than the surface of some moons in the outer solar system. The catch is the pressure. You need a diamond anvil cell to achieve those conditions, making it impractical for applications. But it shows that superconductivity at much higher temperatures is possible in principle. The dream, of course, is room temperature superconductivity at ambient pressure. Imagine wires that transmit electricity with zero loss. Power grids would become dramatically more efficient. Magnetic levitation trains would become practical. Quantum computers could operate without complex cryogenic cooling. Energy storage in superconducting loops could revolutionize how we handle renewable power. The technological implications would be transformative. But we're not there yet, and we might not get there without understanding the fundamental mechanism. High-temperature superconductivity is one of the major unsolved problems in condensed matter physics. We found the phenomenon. We can measure it. We can even engineer better superconductors through trial and error. But we don't really know why it works. The materials are showing us something about quantum mechanics, about how electrons behave in complex environments that our theories haven't captured yet. And maybe that's a good reminder of how science works. We don't need to fully understand something to use it. Engineers built steam engines before thermodynamics was developed, built airplanes before fluid dynamics was complete. But understanding deepens our capabilities. It lets us predict, design, optimize. The mystery of high-temperature superconductivity isn't just an intellectual puzzle. It's a locked door behind which might lie technologies we can barely imagine. And we're still searching for the key. Here's something that changed cosmology forever and introduced one of the deepest mysteries in physics. The universe's expansion is accelerating, pushed by dark energy that makes up 68% of everything, but remains completely mysterious. We discovered this cosmic acceleration in 1998, winning a Nobel Prize for finding something we cannot explain or directly detect. For most of the 20th century, cosmologists thought they understood the universe's expansion. The Big Bang started everything, space itself expanding, galaxies moving apart from each other. Gravity, pulling everything together, should slow that expansion over time. The question was whether there was enough matter in the universe to eventually halt the expansion and cause a big crunch, or whether the expansion would continue forever, gradually slowing but never quite stopping. In the 1990s, two independent research teams set out to measure the universe's deceleration by observing distant supernovae. Type Ia supernovae are remarkably consistent in their brightness. They can be used as standard candles to measure cosmic distances. By comparing how bright they appear with how bright they should be, you can calculate how far away they are. By measuring their redshift, how much their light has been stretched by the expansion of space, you can tell how fast they're moving away. Put these together, and you can map the expansion history of the universe. Both teams expected to measure deceleration, to find that the universe's expansion was slowing down, as it should if gravity is the dominant force. Instead, they found the opposite. Distant supernovae were fainter than expected, meaning they were farther away than they should be. The universe wasn't slowing down, it was speeding up. Galaxies are accelerating away from each other, driven by some unknown force that opposes gravity. This was shocking. It contradicted expectations and seemed to require something entirely new in physics. The researchers checked their data obsessively, looking for errors, alternative explanations, anything that might account for the anomaly without invoking new physics. But the effect persisted. In 1998, both teams published their findings, and the cosmological community had to grapple with the implications. The discovery earned the leaders of both teams the Nobel Prize in Physics in 2011. The simplest explanation involves what's called dark energy, a form of energy that fills all of space uniformly and exerts negative pressure, effectively pushing space apart. Einstein's equations of general relativity allow for this through a term called the cosmological constant, which Einstein himself introduced and later called his biggest blunder when he thought it was unnecessary. Now it seemed the cosmological constant might be real after all, representing an intrinsic energy of empty space itself. But here's the problem. We have no idea what dark energy actually is. If it's the energy of the vacuum, quantum fields fluctuating even in empty space, then calculations suggest it should be vastly, almost incomprehensibly larger than what we observe. The theoretical value is about 10^120 times larger than the measured value. That's not a small discrepancy. It's arguably the worst prediction in the history of physics. Something is wrong with our understanding, either of quantum field theory or gravity or how they interact. Maybe dark energy isn't constant. Maybe it changes over time, in which case it's not a cosmological constant, but some dynamical field, sometimes called quintessence. Maybe it's not a substance at all, but a sign that our theory of gravity needs modification on cosmological scales. Maybe there are extra dimensions of space, or we're living in a region of a larger multiverse where the local vacuum energy happens to be small. The proposals are diverse and speculative, and none has been confirmed. What we do know is that dark energy makes up about 68% of the universe's total mass energy content. Dark matter, another mystery, accounts for about 27%. Ordinary matter, everything we can see and touch, all the stars and planets and galaxies, is just 5% of the total. We are a minority component in a universe dominated by things we don't understand, and the consequences of dark energy are profound. If the acceleration continues, and current observations suggest it will, the universe's fate is what's sometimes called the Big Rip, or more gently, a cold and lonely future. Galaxies outside our local group will accelerate away from us until they cross beyond our cosmic horizon, their light redshifted into undetectability. Eventually, even structures within our local group might be torn apart if dark energy strengthens, or the universe might just expand forever, cooling and darkening, stars burning out one by one until nothing remains but cold, dead remnants in an ever-expanding void. But that's billions, probably trillions of years away. For now, the mystery is more immediate. What is dark energy? Why does it have the value it does? How does it interact with the rest of physics? We've measured its effects with increasing precision, but we're no closer to understanding its nature. The universe is accelerating into darkness, driven by something we can observe but not explain. And that mystery sits at the heart of modern cosmology. Let's come back to Earth now, to intelligence that evolved in an entirely different way from our own. Octopuses evolved intelligence independently from vertebrates, suggesting consciousness can emerge through radically different paths. Their neurons are distributed throughout their arms, creating a form of intelligence so alien that each arm can make decisions independently. An octopus is, in many ways, the closest thing we have to an alien intelligence on Earth. The last common ancestor we share with octopuses lived about 600 million years ago, a simple worm-like creature with barely any nervous system at all. Since then, we've evolved along entirely separate paths. Vertebrates developed centralized brains encased in skulls, with intelligence concentrated in the head. Cephalopods, octopuses, squid, cuttlefish, took a different route. An octopus has about 500 million neurons, which is comparable to a dog, but only about 40% of those neurons are in its brain. The rest are distributed throughout its body, particularly in its 8 arms. Each arm contains a cluster of ganglia that can process information and control movement semi-independently. When an octopus reaches into a crevice, the arm can explore and react to what it touches without waiting for instructions from the brain. It's as if each arm has its own peripheral intelligence, its own capacity for decision-making. This creates a form of consciousness, if that's the right word, that's profoundly different from ours. We experience our bodies as centrally controlled, with a unified sense of self located somewhere behind our eyes. An octopus might experience itself differently. Does it have a unified self, or is it more like a collective? A brain coordinating with 8 semi-autonomous arms. When an octopus reaches into multiple crevices simultaneously, is there a single consciousness experiencing all of it, or something more distributed? We don't know, and it's difficult to even ask the question properly. But we do know octopuses are remarkably intelligent by any measure. They solve problems. They use tools, carrying coconut shells to construct shelters, wielding rocks to barricade dens. They learn through observation, watching other octopuses and mimicking their behavior. They play, manipulating objects for apparently no purpose other than curiosity or entertainment. They escape from tanks, unscrew lids from jars, and have been known to turn off lights in laboratories by squirting water at the bulbs. Whether out of annoyance at the brightness or simple mischief is unclear. They're also masters of camouflage, changing color and texture in milliseconds to match their surroundings or communicate with other octopuses. This involves sophisticated visual processing and real-time control of specialized skin cells called chromatophores. Curiously, octopuses are colorblind. They don't have multiple types of color receptors in their eyes like we do, yet they match colors perfectly. Some researchers think they might sense color through their skin directly, though this remains speculative. There's also evidence of personality. Individual octopuses have consistent behavioral differences. Some are bold and exploratory, others cautious and shy. Some are aggressive, others gentle. They recognize individual humans and respond differently to people they like versus those they don't. Stories from aquarium keepers describe octopuses that squirt water at staff members they dislike, or that show preference for certain people during feeding. But here's the melancholy part. Octopuses are short-lived. Most species live only 1 to 2 years. They reproduce once and die, the parents never meeting their offspring. There's no opportunity for cultural transmission, for learning to accumulate across generations. Each octopus must figure out the world from scratch, its intelligence erased when it dies. Imagine if humans lived only a year or two, with no ability to pass knowledge to the next generation. How much could we accomplish? How complex could our societies become? Some researchers wonder if octopuses might become more intelligent if they lived longer and could form lasting social structures. Currently, they're mostly solitary. Interactions between octopuses are brief, often aggressive or mating-related, but intelligence in vertebrates is often associated with social complexity, with the need to navigate relationships and hierarchies. If octopuses lived decades instead of years, if they formed stable groups with persistent relationships, would their intelligence deepen? Would they develop something like culture? We'll probably never know because evolution has locked them into their current life history. But octopuses, as they are, still teach us something profound. Intelligence is not unique to our evolutionary lineage. Consciousness, or something like it, can emerge from very different neural architectures. There's no single path to minds, no universal blueprint. The universe has found at least two ways to create awareness on Earth, and that suggests it might find others elsewhere, in forms we might not even recognize as alive or aware. An octopus watching you from its tank is, in some sense, a mirror showing an alternate possibility. What intelligence looks like when it evolves without bones, without a centralized brain, without social structures or long lives. And yet it watches, it solves problems, it changes, it exists in a bubble of experience we can only dimly imagine. That's the mystery. Not just that octopuses are intelligent, but that their intelligence is so radically different from ours yet still recognizable as something more than mere reflex. In October 2017, astronomers detected something unprecedented, an object from interstellar space passing through our solar system. The Oumuamua object that passed through our solar system in 2017 accelerated in ways that suggest it wasn't just a simple asteroid. Its strange cigar shape, unusual trajectory, and unexplained speed boost sparked serious scientific debate about artificial origins. Telescopes spotted Oumuamua, Hawaiian for scout, or messenger from afar, as it was already leaving the inner solar system, moving too fast to be bound by the sun's gravity. It was traveling at over 26 kilometers per second, fast enough that no current human technology could have caught up with it. Within a few months it would be too far away to observe, already on its way back into interstellar space. Astronomers had a brief window to study it, and what they saw was puzzling. First, the shape. Based on how its brightness varied as it tumbled through space, Oumuamua appeared to be highly elongated, perhaps 10 times longer than it was wide. Some estimates suggested it might be cigar-shaped, or possibly disc-shaped like a pancake, but definitely unusual. Most asteroids and comets are more roughly spherical or potato-shaped. Something about Oumuamua's formation or history had given it this strange geometry. Second, the trajectory. As Oumuamua swung around the sun and headed back out, it accelerated slightly more than gravity alone could account for. Comets do this too. When they get close to the sun, ice sublimates into gas, creating jets that push the comet like tiny rockets. But Oumuamua showed no visible coma, no tail, no evidence of outgassing that telescopes could detect. If it was outgassing. It was doing so in a way that didn't create visible clouds of dust or gas, which is odd. Third, its color and surface properties. Oumuamua was reddish, similar to some outer solar system objects, suggesting an organic-rich or radiation-aged surface. It was tumbling chaotically, rotating about multiple axes, which might indicate it had experienced a violent collision or ejection event. But its spectrum, the way it reflected different wavelengths of light, didn't match any common solar system object perfectly. The combination of these characteristics led to speculation. If Oumuamua wasn't outgassing in the usual way, what caused its acceleration? One idea proposed by Harvard astronomer Avi Loeb suggested that radiation pressure from sunlight could account for it. If Oumuamua was very thin and light, like a sail, photons from the sun could push on it. This would require an unusual shape and density, but it's possible. And if you're imagining a thin, large, artificial object designed to catch starlight, you're thinking about a solar sail, technology we've proposed for spacecraft. Loeb went further, suggesting the possibility that Oumuamua might be artificial, a probe or debris from an alien civilization drifting through space. This sparked considerable controversy. Most astronomers argued that there are natural explanations that don't require invoking extraterrestrial technology. Perhaps Oumuamua was a comet outgassing hydrogen, which is invisible to optical telescopes. Perhaps it was a fragment sheared off a larger body by tidal forces, giving it an unusual shape. Perhaps its acceleration was within the range of measurement uncertainty. The problem is that Oumuamua is gone, and we'll never get another chance to study it. We can't send a probe to catch up. We can't get better images or spectroscopy. We're left with a handful of observations collected over a few weeks, and those observations don't quite fit any simple explanation perfectly. It's probably a natural object. The universe is full of comets and asteroids, and some are bound to be unusual. But the ambiguity is tantalizing. And here's the thing. Oumuamua was likely the first interstellar object we detected, not because such objects are rare, but because we only recently had telescopes sensitive enough to spot them. Now that we know what to look for, we've found others. Borisov, a second interstellar object, passed through in 2019 and looked much more like a conventional comet. The solar system is probably being visited by interstellar objects all the time, most of them too small or too dim to detect. So we might get another chance. Perhaps another Oumuamua-like object will arrive, this time when we have better instruments ready. Perhaps we'll spot one earlier in its approach, giving us time to observe it more thoroughly, or even launch a mission to rendezvous with it. Until then, Oumuamua remains a data point, an outlier, an anomaly, a visitor from the chai depths of space that didn't quite behave as expected and left before we could figure out why. Here's something that sounds almost magical, but appears to be real. Some plants appear to hear the sound of running water through their roots, growing toward it preferentially. They respond to specific frequencies of water sounds, suggesting a vibroacoustic sense we're just beginning to understand. Plants don't have ears, obviously. They don't have nervous systems or brains, but they do respond to their environment in sophisticated ways, growing toward light, sensing gravity, detecting chemicals in the soil. And now, it seems, they might respond to sound. researchers in Australia conducted an elegant experiment with pea plants. They placed seedlings in Y-shaped containers where the roots could grow in two directions. At the end of one branch, they placed a source of moisture. At the end of the other branch, they either placed nothing or played a recording of water flowing. The question was, which direction would the roots grow? When there was actual water, the roots preferentially grew toward it. No surprise there. Plants are known to sense moisture gradients and grow toward water sources through a process called hydrotropism. But when there was no moisture, only the sound of water, the roots still grew toward the sound. They seemed to be detecting acoustic vibrations and interpreting them as signals of water nearby. Even more interesting, the effect was frequency-specific. The roots responded to the low-frequency sounds of water flowing, roughly 200 to 300 hertz, but ignored other sounds at different frequencies. This suggests they're not just sensing random vibrations, but specifically tuned to the acoustic signature of water moving through soil or along roots. How do they do this? We don't know exactly. Plants don't have mechanoreceptors like animal ears, but they do have cells that respond to mechanical stress and pressure. Root cells are constantly sensing their surroundings, detecting obstacles, changes in moisture, nutrient concentrations. Perhaps some of these sensing mechanisms are sensitive to vibrations in ways we hadn't realized. Perhaps acoustic waves propagating through soil cause microscopic deformations in root tissue that trigger cellular responses. Or perhaps plants are sensing the vibrations differently, maybe through water channels within their cells, or through the tension in their cell walls, or through some other mechanism entirely. The research is still in early stages, and replication is needed. Not all studies have found the same effects, and some researchers remain skeptical, but the basic finding that roots can respond to acoustic signals that correlate with water is intriguing. And plants might be more acoustically aware than we realize in other ways too. Some studies suggest that plants respond to the vibrations of insect chewing on their leaves, triggering defensive responses like producing bitter chemicals or releasing volatiles that attract predators of the insects. Other research has found that plants exposed to certain sound frequencies grow faster or produce more biomass, though the mechanisms are unclear and results are variable. There's a long history of people claiming that talking to plants helps them grow, or that playing music to plants improves their health. Most scientists dismissed this as wishful thinking or simple confirmation bias. But maybe there's a grain of truth buried in the folklore. Not because plants enjoy music or respond to human intentions, but because sound waves are physical vibrations that can affect biological systems in subtle ways. Of course, we should be careful not to overinterpret. Plants don't hear in any sense that resembles animal hearing. They don't have subjective experiences of sound, no awareness of acoustic patterns, no appreciation for music. What they have is a sensitivity to certain vibrations that correlates with ecologically relevant information, like the presence of water, and they've evolved to respond to those vibrations in adaptive ways. But it does expand our understanding of how plants sense their environment. They're not passive, static organisms rooted helplessly in place. They're actively exploring, sensing, responding, making decisions about where to grow, which direction to extend their roots, how to allocate resources, They're doing this through a combination of chemical sensing, light detection, gravity perception, touch responses, and now, possibly, vibroacoustic sensing. Each of these is a different channel through which information flows from the environment into the plant's physiology, shaping growth and behavior. And it's another reminder that the world is full of signals we don't perceive. Sound travels through soil in ways different from air. Low-frequency vibrations propagate through earth and water, carrying information about water flow, about animals moving, about roots of other plants. If you're a plant rooted in place, listening to the soil might be as important as seeing the sun. And evolution has shaped plants to do exactly that, to feel the world through vibrations, to navigate the underground landscape using senses we're only beginning to appreciate. Let's look up now to our closest celestial neighbor and consider a change so gradual that it's almost imperceptible yet inevitable. The moon is slowly drifting away from Earth at about 1.5 inches per year, and we don't know if there's a limit to this. Eventually, Earth and Moon will be tidally locked, showing each other the same face forever, if they remain bound at all. The Moon wasn't always where it is now. The prevailing theory is that about 4.5 billion years ago, a Mars-sized object struck the young Earth in a glancing blow, ejecting debris that coalesced into the Moon. Initially, the Moon was much closer, perhaps 10 to 20 times closer than today. The sky would have been dominated by a massive lunar disk, far larger than the Moon appears now, and Earth's day was only about 5 hours long. Since then, the Moon has been slowly receding. The mechanism is tidal interaction. The Moon's gravity raises tidal bulges in Earth's oceans, the familiar high tides on the sides of Earth facing and opposite the Moon. But Earth rotates faster than the Moon orbits, so the tidal bulges are carried slightly ahead of the Moon by Earth's rotation. These bulges exert a gravitational pull on the Moon, slightly accelerating it in its orbit. Orbital mechanics dictate that when you speed up an orbiting object, it moves to a higher orbit, so the Moon gradually drifts outward. Meanwhile, the tidal bulges act as a drag on Earth's rotation, slowing it down. Earth's day is getting longer by about 1.7 milliseconds per century, imperceptible on human timescales, but significant over geological time. Fossil evidence supports this. Ancient corals, which lay down daily growth rings, show that 400 million years ago, a year contained about 400 days, meaning each day was shorter. So the system is exchanging angular momentum. Earth's rotation slows, the Moon's orbit expands, and the total angular momentum of the Earth-Moon system is conserved, with a small loss to tidal heating. This will continue for billions of years. Eventually, in about 50 billion years, Earth and Moon would become tidally locked to each other. Earth's rotation would slow until one day equals one lunar month, both around 47 current days long. The Moon would hang stationary in the sky as seen from one side of Earth, invisible from the other hemisphere. Each would present the same face to the other perpetually. But there's a catch. The Sun will have become a red giant by then, possibly engulfing Earth and Moon both, so this tidal locking probably won't actually occur. The system will be disrupted or destroyed before reaching that final state. Still, the gradual recession raises interesting questions. Is there a limit? Could the Moon eventually escape Earth's gravity entirely? Probably not. The tidal interactions will stabilize long before escape velocity is reached. but the moon will be much farther away, appearing smaller in the sky, and the connection between Earth and moon will be looser, more tenuous. The moon's recession also has practical consequences. Ancient solar eclipses were longer because the moon was closer and appeared larger in the sky. In the far future, the moon will appear smaller, and total solar eclipses will become impossible. The moon won't be large enough to cover the sun's disk completely. We live in a special time when the moon and sun appear almost exactly the same size in our sky, making perfect total eclipses possible. That's a coincidence, a temporary alignment that will fade as the moon drifts away. There's something poignant about it. The moon has been humanity's companion throughout our existence, lighting the night, driving tides, stabilizing Earth's axial tilt, and thus our climate. Our calendars and mythologies are shaped by it. It's the only other world humans have walked upon. And slowly, inexorably, it's leaving us, receding at the speed fingernails grow, a pace so gradual that we'll never notice in our lifetimes, but which will eventually carry it to a higher, lonelier orbit. Of course, on human time scales, the change is negligible. The moon will look the same to your descendants 1,000 years from now as it does to you tonight. But it's a reminder that nothing is static, not even the most permanent seeming features of our world. The universe is in motion, always changing, always evolving. Even the moon, constant companion, is slowly saying goodbye, 1 inch at a time, over eons we can barely comprehend. Let's come back to Earth, to intelligence that might be watching you right now. Crows can recognize individual human faces years after a single encounter and teach their offspring to avoid specific people. They hold grudges, conduct funeral rituals, and may possess a theory of mind, understanding that others have different thoughts than they do. Crows are among the most intelligent birds, with brain-to-body ratios comparable to great apes. But their intelligence isn't just general problem-solving ability. It's deeply social and surprisingly human-like in some ways. They recognize faces, not just vaguely distinguishing one person from another, but remembering specific individuals and associating them with past experiences. In a famous experiment at the University of Washington, researchers wore distinctive masks while capturing and banding crows. The crows, understandably, found this stressful and threatening. Later, when people wearing those same masks walked around campus, even years after the initial capture, the crows mobbed them aggressively, diving and scolding. But people wearing different masks, or the same researchers without masks, were ignored. The crows had learned to associate specific facial features with danger. More remarkably, crows that weren't even present during their original capture learned to recognize and mob the masked individuals. They somehow transmitted the information socially, possibly through observing other crows' reactions, or through some form of crow communication we don't fully understand. The knowledge spread through the local crow population. A human wearing that mask became notorious among crows that had never personally encountered them. This suggests something like cultural transmission, information passing from one generation to the next through learning rather than genetics. And it's not just about danger. Crows also remember people who feed them or help them, responding with apparent affection or bringing gifts, shiny objects, stones, sometimes pieces of food left on doorsteps or windowsills. The gifts might be attempts at reciprocity or play, or simply deposit of objects near places the crows associate with positive experiences. The motivation isn't entirely clear, but the behavior is consistent enough to suggest crows have some concept of maintaining relationships with individual humans. Crows also display behaviors that suggest self-awareness and theory of mind. They cache food and, if watched by other crows, will return later to move the cached food to a new location, suggesting they understand that other crows might steal from them if they saw where the food was hidden. This requires understanding that other minds have knowledge different from one's own. They also engage in what looks like deception, making false caches or pretending to hide food while actually keeping it. Behaviors that suggest strategic thinking about other crows' mental states. And then there are crow funerals. When a crow dies, other crows gather around the body, calling loudly, sometimes for hours. They don't eat the corpse, they're not scavenging. They appear to be investigating, learning. Researchers have found that crows remember the location of dead crows and avoid those areas, possibly associating them with danger. The gathering might be a way of learning about threats, of understanding what killed the crow and whether it poses a danger to them. But the behavior looks ceremonial, almost mournful, and it's hard not to interpret it through an emotional lens, even though we can't know what crows experience internally. Crows use tools, fashioning hooks from twigs to extract insects from crevices, or dropping nuts on roads for cars to crack open. They solve multi-step puzzles, plan for the future, and adapt their behavior based on experience. Their intelligence is flexible, not just instinctual. What's striking is that all this cognitive sophistication exists in a brain structurally very different from mammalian brains. Crows don't have a neocortex, the layered brain structure mammals use for complex cognition. Instead, their intelligence arises from different neural architectures, different arrangements of neurons and connections. Like octopuses, crows demonstrate that intelligence is not constrained to one evolutionary solution. The universe has found multiple paths to awareness, to memory, to social cognition, and crows are everywhere: urban environments, forests, coasts. They're watching, learning, remembering. If you feed crows regularly, they'll remember you. If you threaten them, they'll remember that too, and possibly avoid you or mob you for years. You've become part of their social landscape, an individual in their mental map of relevant beings. It's a strange kind of relationship, mediated by recognition and memory, spanning the divide between species. You see a crow, and somewhere in its small, dense brain, neurons fire in patterns that encode your face, your actions, your significance in the crow's world. And that crow might tell other crows about you. You've become part of crow culture. There's something humbling about that. We'll close this section with a return to an unsolved mystery that's been frustrating researchers for decades. The Taos hum in New Mexico has been investigated by scientists and engineers, but no definitive source has ever been identified. Unlike other unexplained sounds, this one has been formally studied by government agencies, yet it remains elusive. In the early 1990s, residents of Taos, New Mexico, began reporting a persistent low-frequency humming sound. It was especially noticeable at night, indoors, and seemed to emanate from no identifiable source. People described it as maddening, a constant drone that interfered with sleep, caused headaches, and created a pervasive sense of unease. Only about 2% of the population heard it, but for those who did, it was inescapable. The Tao's hum gained enough attention that in 1993, a team of researchers, scientists, engineers, and audiologists conducted a formal investigation. They interviewed hearers, performed hearing tests, brought in acoustic monitoring equipment, and searched for potential sources: industrial facilities, power lines, radio transmitters, geological activity. They analyzed electromagnetic fields, seismic vibrations, atmospheric conditions. They tried to correlate the reports with measurable phenomena. They found nothing definitive. Some hearers had unusually sensitive, low-frequency hearing, but not all. No acoustic instruments detected a consistent, anomalous sound in the frequency range described. No electromagnetic or seismic patterns correlated clearly with the reports. Some potential sources were identified: certain electrical equipment, distant industrial operations, but none explained the phenomenon comprehensively. The investigation concluded that the hum was real, in the sense that people were genuinely experiencing it, but the source remained unknown. The case stayed open, unsolved. What makes the Tao's hum particularly intriguing is that it's not unique. Similar hums have been reported in other locations worldwide: Bristol in England, Bondi in Australia, Windsor in Ontario. The descriptions are remarkably consistent. Low frequency, around 30-80 Hz, more noticeable at night and indoors, audible only to a small percentage of people. This consistency suggests there's something real underlying the reports, but the variability in location suggests multiple potential causes rather than a single explanation. Some theories focus on environmental sources. Low-frequency sounds can travel enormous distances. Seismic activity, ocean waves, distant machinery, even atmospheric phenomena like microbaromes. Low-frequency sounds generated by ocean waves colliding. These sounds might be below the threshold of conscious perception for most people, but detectable by those with particularly sensitive hearing or neurological quirks that amplify certain frequencies. Other theories are more speculative. Could electromagnetic fields interact with the auditory system or inner ear in ways that create the perception of sound? Some people report being able to hear electromagnetic interference from certain devices: power supplies, monitors, radio transmitters, even though no acoustic sound is present. The mechanism might involve bone conduction or direct stimulation of nerves, or even microwave hearing effects where electromagnetic pulses create pressure waves in tissue. These effects are real but rare and poorly understood. There's also the possibility of tinnitus, not the typical high-pitched ringing, but a rare form that manifests as low-frequency sound. But this doesn't explain the geographic clustering or the fact that some hearers report the sound disappearing when they travel away from certain areas. What's frustrating is the lack of resolution. Despite investigations, despite modern acoustic and electromagnetic monitoring technology, despite interviews and testing, the Tao's hum remains unexplained. It's possible that different instances of the hum have different causes, some industrial, some geological, some neurological, and we're grouping distinct phenomena under one label. Or perhaps there's a common cause we haven't identified yet, some subtle environmental factor that affects a small subset of people with specific sensitivities. For the hearers, though, the lack of explanation doesn't diminish the experience. The sound is real to them, persistent, and distressing. Some have moved away to escape it. Others have learned to live with it, using white noise machines or earplugs to mask the sound. And a few have become amateur investigators themselves, trying to track down the source, convinced that somewhere there's an explanation waiting to be found. The Tao's hum sits in that uncomfortable category of phenomena that are empirically real. People genuinely experience it, but scientifically elusive. It's not paranormal, it's not a hoax, but it's also not solved. And maybe that's a reminder that even in our modern, sensor-filled, scientifically advanced world, there are still local mysteries, small anomalies that resist explanation. The universe, it seems, still has the capacity to hum at us in frequencies we can't quite pin down, leaving us to wonder what we're hearing and where it comes from. Now let's descend into the quantum realm, where particles behave in ways that seem to violate common sense. Quantum tunneling allows particles to pass through barriers they shouldn't be able to cross, as if teleporting through walls. This isn't science fiction. It's happening in your body right now, enabling the nuclear fusion that powers the sun and the chemistry of life. In classical physics, if you throw a ball at a wall, it bounces back unless you throw it hard enough to break through. The ball either has enough energy to overcome the barrier or it doesn't. There's no middle ground. But at the quantum level, particles don't follow these rules. They exist as probability waves, smeared out clouds of possible locations. And those waves can extend through barriers that classical objects could never penetrate. Imagine an electron approaching a barrier, say, the electrical repulsion between two positively charged atomic nuclei. Classically, if the electron doesn't have enough energy to overcome this repulsion, it should bounce back. But quantum mechanics allows for a small probability that the electron will appear on the other side of the barrier, as if it had tunneled through. The electron doesn't gradually bore through the barrier. It doesn't lose energy along the way. It simply has some probability of being on one side and some probability of being on the other. And when you measure it, you might find it has crossed over. This seems impossible, but it's been verified countless times. Scanning tunneling microscopes work by exploiting this effect. Electrons tunnel between a sharp metal tip and a surface, creating a current that depends on the distance between them. By scanning the tip across a surface and measuring tunneling current, you can map individual atoms. The images are stunning. You can literally see the arrangement of atoms on a surface, visualize molecular structures, even manipulate individual atoms by pushing them around with the microscope tip. But quantum tunneling isn't just a laboratory curiosity. It's fundamental to how the universe works. In the sun's core, hydrogen nuclei fuse into helium, releasing the energy that makes the sun shine. But hydrogen nuclei are positively charged and repel each other strongly. To overcome this repulsion through classical means would require temperatures much higher than the sun's actual core temperature. The sun shouldn't be able to fuse hydrogen at the temperatures it has, yet it does, because quantum tunneling allows the nuclei to penetrate the electrical barrier and get close enough for the strong nuclear force to bind them together. Without tunneling, stars wouldn't shine. The universe would be cold and dark, with hydrogen remaining inert, unable to fuse into heavier elements. There would be no carbon, no oxygen, no elements necessary for planets or life. The existence of chemistry, of complexity, of everything beyond the simplest elements depends on quantum tunneling in stellar cores. And it happens in your body too. Many biochemical reactions involve particles tunneling through energy barriers, electrons tunneling in enzyme reactions, protons tunneling through cell membranes. Some researchers think quantum tunneling might be involved in DNA mutation. Protons in the base pairs can tunnel from one position to another, changing the pairing properties temporarily and potentially leading to replication errors. This could be part of how evolution generates variation, how random mutations arise from quantum randomness. There's something philosophically intriguing about tunneling. It suggests that reality at the quantum level is less about definite positions and trajectories, and more about probabilities and possibilities. The electron doesn't have a path through the barrier. It doesn't travel through it in any conventional sense. It just has amplitude on both sides, and measurement collapses that amplitude into a definite location. Before measurement, the electron is in a superposition, simultaneously on both sides of the barrier in some sense. Can macroscopic objects tunnel? In principle, yes, but the probability drops exponentially with mass and barrier width. For an object the size of a person to quantum tunnel through a wall, the probability is so astronomically small that it would effectively never happen, not once in the lifetime of the universe, not even if the universe repeated a googolplex times. Quantum effects dominate at small scales and wash out at large scales due to decoherence, the environment constantly measuring and collapsing the quantum states of large objects, forcing them to behave classically. But in the quantum realm, tunneling is routine. Particles slip through barriers constantly, enabling processes that make the universe habitable. It's a reminder that the foundations of reality are probabilistic, not deterministic. The universe allows for possibilities that seem forbidden, paths that appear blocked but aren't quite, outcomes that shouldn't happen but do. And somehow, from these ghostly quantum probabilities, the solid, reliable macroscopic world emerges. Stars burning steadily, chemistry proceeding predictably, life organizing itself into patterns that persist. The impossible made routine, the improbable made inevitable, through the strange rules that govern the very small. Let's zoom out now, far beyond our solar system, to a cosmic mystery that reveals how much we don't know about the universe's structure. The great attractor is pulling our galaxy and thousands of others toward a point we can't directly see, hidden behind the Milky Way. Something with the mass of tens of thousands of galaxies is tugging on us from 150 million light years away. Galaxies aren't randomly scattered through space. They cluster, forming groups, clusters, and superclusters bound together by gravity. Our Milky Way is part of the local group, which includes Andromeda and about 50 other smaller galaxies. The local group, in turn, is part of a larger structure called the Laniakea supercluster, containing about 100,000 galaxies spread across 520 million light years. In the 1970s and 1980s, astronomers mapping the motions of galaxies noticed something odd. Galaxies in our region of space weren't just moving with the expansion of the universe. They were also moving with a peculiar velocity, a bulk flow toward a particular direction in the sky. Something massive was pulling on them gravitationally, adding a component of motion on top of the cosmic expansion. By measuring the redshift and distances of many galaxies, researchers triangulated the source of this pull. It lay in the direction of the constellations Hydra and Centaurus, behind the disk of our own galaxy. This region of the sky is obscured by the Milky Ways, stars, gas, and dust. We call it the zone of avoidance because it's difficult to observe distant objects through the dense material of our own galaxy. But whatever was out there was massive enough to affect galaxies across hundreds of millions of light years. They called it the Great Attractor. Estimates suggest it has a mass equivalent to tens of thousands of galaxies, an enormous concentration of matter. But when astronomers finally managed to peer through the Milky Way's obscuring material using radio, infrared, and X-ray observations, they found a large cluster of galaxies called the Norma cluster in that region. It's massive, yes, but not quite massive enough to account for all the observed motion. Further mapping revealed that the story is even more complex. The Great Attractor itself appears to be falling toward an even larger structure called the Shapley supercluster, which lies beyond it at about 650 million light-years away. The Shapley supercluster contains over 8,000 large galaxies and more than 25 galaxy clusters, one of the largest known structures in the universe. It might be the real source of the gravitational pull, with the Great Attractor region being an intermediate concentration of matter along the way. So we live in a universe where galaxies aren't just drifting apart due to expansion. They're also flowing along gravitational currents, pulled by massive structures tens or hundreds of millions of light-years away. Our Milky Way, along with thousands of neighboring galaxies, is falling through space toward the Shapley supercluster at about 600 kilometers per second, a journey that will take billions of years. We're like leaves in a cosmic river, carried by currents we can barely see. What does this mean? It reveals the universe's large-scale structure, the cosmic web of filaments, clusters, and voids that emerged from tiny density fluctuations in the early universe. Gravity amplified those fluctuations over billions of years, pulling matter together into increasingly large structures. The Great Attractor and the Shapley supercluster are peaks in this landscape of density, attractors in the truest sense, shaping the flow of galaxies across cosmic distances. But it also highlights how much we still don't know. Dark matter dominates the mass of these structures, outweighing visible galaxies by factors of 5 or 10. We map the visible light, the galaxies we can see, but the real gravitational architecture is dark, invisible, known only through its effects on motion. The Great Attractor is as much a dark matter structure as a visible one, possibly more so. What we see are the galaxies embedded in it, like lights on a ship at night, but the bulk of the ship is dark, unseen. And then there's the realization of scale. Our entire local group, the Milky Way, Andromeda, and all our neighboring galaxies, is a tiny part of a flow pattern that encompasses thousands of galaxies spread across hundreds of millions of light years. The motions we observe locally are echoes of gravitational influences on scales so vast they're hard to comprehend. We're caught in forces shaped by structures we can barely observe, falling through space toward destinations we'll never reach within human timescales. There's something humbling about that. We think of ourselves as inhabitants of Earth, citizens of a solar system, members of a galaxy. But zoom out far enough, and we're part of a galactic stream, a current in the cosmic web, flowing toward the Shapley supercluster, along with thousands of other galaxies. All of us responding to the same vast gravitational architecture. We're not isolated. We're connected to the universe's largest structures, participating in motions that dwarf anything we can control or even fully perceive. The great attractor pulls, and we fall, along with everything around us, through the dark. Let's return to the mysteries of human perception now, to the strange ways some brains connect experiences that most people keep separate. Some people with synesthesia automatically experience colors when they hear sounds or taste words, cross-wiring we don't fully understand. For them, Tuesday might be green, or the word table might taste like blueberries, revealing how subjective perception truly is. Synesthesia means joined perception, and it describes a family of conditions where stimulation of one sensory pathway automatically triggers experiences in another. The most common form is grapheme color synesthesia, where letters or numbers are associated with specific colors. A synesthete might see the number 5 as inherently red, or the letter A as blue. These associations are consistent. The same letter always evokes the same color, and they're automatic, not something the synesthete chooses. Other forms exist: chromesthesia, where sounds have colors; lexical gustatory synesthesia, where words evoke tastes; spatial sequence synesthesia, where numbers or time periods have specific spatial locations. Some synesthetes experience personalities for numbers or letters. 3 might be friendly, 7 might be aloof. Some see months of the year arranged in specific three-dimensional configurations in space, like a calendar they can mentally navigate. For a long time, synesthesia was dismissed as metaphor or imagination, but modern neuroscience has confirmed it's real. Brain imaging shows that when a synesthete sees a number, not only does the visual cortex activate, but also the color processing regions, even if the number is printed in black ink. The brain is genuinely creating a color experience in response to the symbol. Why does this happen? The leading theory involves cross-activation between adjacent brain regions. In the developing brain, there's initially excess connectivity. Neurons make connections widely, and then pruning occurs, refining the networks. In synesthetes, perhaps some of these cross-connections remain, creating pathways between regions that normally don't communicate directly. The grapheme area, which processes letters and numbers, sits next to the color area in the brain. A slight excess of connections between them could cause activation in one to spill over into the other. Genetic factors seem to play a role. Synesthesia runs in families, suggesting inherited differences in how the brain wires itself. But it's also influenced by learning and culture. Synesthetes don't experience colors for letters they haven't learned yet, and the specific color associations can be influenced by childhood experiences. A red letter A in a favorite book, for instance, might shape a lifelong association. What's fascinating is that synesthesia reveals the constructed nature of perception. We tend to think we perceive reality directly, that our senses show us the world as it is. But really, perception is a process. Sensory information is filtered, processed, integrated, and constructed into a coherent experience by the brain. Most people's brains construct experiences in similar ways, so we assume our perceptions are universal. But synesthetes experience a different construction, one where sensory streams mix in ways that reveal the brain's flexibility. And they're not disordered. Many synesthetes find their synesthesia useful or pleasant. It can aid memory. If you associate colors with letters, you might remember phone numbers or names more easily by recalling their color patterns. Some artists and musicians with synesthesia describe it as enriching their creative work, giving them access to cross-modal associations that inspire their art. For them, the world is richer, more layered with sensory meaning than it is for non-synesthetes. But it also raises questions about qualia, the subjective qualities of experience. When a synesthete sees green for the number 5, is that green the same as the green you see when you look at grass? Or is it a different kind of green, an internally generated color experience that doesn't quite map onto externally perceived colors? Synesthetes give varying answers, suggesting that the subjective nature of synesthetic experience might differ from ordinary color perception in subtle ways. And if synesthesia can create these cross-modal perceptions, what does that say about the boundaries between senses? Maybe those boundaries are more flexible than we realize. Maybe all perception involves some degree of cross-modal integration, just not consciously accessible to most people. When you bite into a crisp apple, the sound of the crunch influences how fresh you perceive it to be. When you hold a warm cup, you judge people as warmer and friendlier. Senses bleed into each other subtly all the time. Synesthetes just experience a more dramatic version of this crosstalk. There's also the philosophical question: what is it like to be a synesthete? Thomas Nagel famously asked, "What is it like to be a bat?" to illustrate the difficulty of understanding subjective experience. We can never truly know what another being experiences. And in a sense, synesthetes are experiential aliens, people whose perceptual worlds are structured differently from the majority. They inhabit the same physical reality, but experience it through a different phenomenal lens. And that difference can never be fully communicated. You can describe tasting words or seeing colored numbers, but the actual experience, the what it feels like, remains private, locked in the synesthete's consciousness. So synesthesia doesn't just tell us about unusual brains. It tells us about the nature of subjective experience itself, about how profoundly perception can vary while still being grounded in the same physical world. We each live in our own perceptual bubble, shaped by our unique neurology. Synesthetes' bubbles are just a bit more colorful, a bit more cross-connected than most, and they remind us that the world we experience is always, in some sense, a personal construction, real, but filtered through the peculiarities of our individual minds. Here's a mystery that's more about human psychology than geography, but it's instructive nonetheless. The Bermuda Triangle has no more disappearances than any other heavily traveled ocean region, yet the myth persists for unclear psychological reasons. Our pattern-seeking brains created a mystery from statistical noise, showing how easy it is to find meaning in randomness. The Bermuda Triangle, roughly the area between Miami, Bermuda, and Puerto Rico, has been blamed for dozens of ships and aircraft disappearing under mysterious circumstances. The stories are dramatic: vessels vanishing without distress calls, planes lost despite good weather, entire crews missing without a trace. Some accounts invoke paranormal explanations: alien abductions, time portals, underwater civilizations, magnetic anomalies that scramble instruments. But when researchers actually analyze the data, The Bermuda Triangle isn't anomalous at all. The number of incidents in that region is proportional to the volume of traffic. It's one of the most heavily traveled shipping and aviation routes in the world. Statistically, you'd expect accidents to occur there simply because so many vessels pass through. And when you compare the incident rate to other busy maritime regions, the Bermuda Triangle is average or even below average in terms of losses per transit. Many of the famous disappearances have mundane explanations. Weather in the region can be severe: hurricanes, sudden storms, waterspouts. The Gulf Stream flows through the area, swift and turbulent, capable of quickly dispersing debris and carrying wreckage far from the site of an incident. The ocean floor has deep trenches where wreckage can sink beyond easy recovery. Methane hydrate deposits on the seafloor can theoretically release gas bubbles that reduce water density, potentially sinking ships, though this is more speculative. And some of the mysterious cases turn out, upon investigation, to involve human error, mechanical failure, or weather conditions that weren't mysterious at all, just poorly documented or sensationalized. The mythology grew through repetition and embellishment, with the writers cherry-picking incidents, omitting explanations, and emphasizing the dramatic while ignoring the ordinary. So why does the Bermuda Triangle myth persist? It's a perfect example of apophenia, the tendency to perceive patterns in random data. Humans are exceptionally good at pattern recognition. It's been crucial for survival. Recognizing the rustle of a predator in the grass, identifying edible plants, predicting seasonal changes. These require detecting patterns. But the flip side is that we sometimes see patterns where none exist. We're biased toward false positives. It's safer to assume a pattern and be wrong than to miss a pattern and be eaten. The Bermuda Triangle is a case where people noticed a cluster of incidents, which, given the high traffic volume, isn't surprising, and interpreted it as meaningful. Once the idea was out there, confirmation bias took over. New incidents in the region were added to the narrative, reinforcing the pattern. Incidents outside the region or in other regions with similar incident rates were ignored because they didn't fit the story. The boundaries of the triangle were drawn post hoc, encompassing the incidents people wanted to include. And there's an emotional appeal to the mystery, a world where ships and planes disappear for mundane reasons: storms, mechanical failures, human mistakes, is less interesting than a world where they vanish into an enigmatic zone of paranormal activity. Mystery is more compelling than statistics, so the Bermuda Triangle endures in popular culture despite the lack of evidence, because it satisfies a psychological need for wonder and the unexplained. This doesn't mean we should dismiss everything as randomness. Real patterns exist, and we should investigate anomalies seriously. But we also need to be aware of our cognitive biases, our tendency to see faces in clouds and shapes in static. The universe contains genuine mysteries: dark energy, consciousness, the origin of life. But it also contains a lot of noise, a lot of coincidence, a lot of mundane explanations for things that seem strange at first glance. The Bermuda Triangle myth is useful as a cautionary tale. It reminds us to check our assumptions, to compare rates rather than raw accounts, to look for alternative explanations before invoking the extraordinary. It shows how easily narratives can form and propagate, taking on lives of their own despite contradictory evidence. and it illustrates the importance of skepticism, not cynical dismissal, but careful evaluation, willingness to question popular beliefs, insistence on proportionality between evidence and claims. So the Bermuda Triangle isn't a mystery, it's a mirror, reflecting our tendency to create mysteries where none exist. And recognizing that tendency, understanding the psychology behind it, is its own kind of insight. We see patterns because we're pattern-seeking creatures, but sometimes the pattern is in us, not in the world. And learning to tell the difference is part of what it means to think clearly about reality. Let's turn now to extremophiles, organisms that survive in conditions we'd consider utterly lethal, revealing just how adaptable life can be. Some bacteria can survive in the cooling pools of nuclear reactors, thriving on radiation that would kill almost anything else. Deinococcus radiodurans can withstand 1,000 times the radiation that would kill a human, repairing its shattered DNA with enzymes we're studying. Most life on Earth avoids radiation. Ionizing radiation, the kind produced by radioactive decay, cosmic rays, or nuclear reactions, damages DNA by breaking the molecular bonds that hold the double helix together. A cell hit with enough radiation has its genetic instructions shredded into fragments. Normal cells can repair some damage, but beyond a threshold, the breaks are too numerous, and the cell dies or becomes cancerous. Humans can tolerate a few gray of radiation, a measure of absorbed dose, before experiencing acute radiation sickness. Around 5 gray, you have a 50% chance of dying within weeks without medical intervention. Above 10 gray, survival is unlikely, even with treatment. Now consider Deinococcus radiodurans. It can survive doses of 5,000 gray or more without significant harm. It's been nicknamed Conan the bacterium for its toughness. How does it do this? The bacterium has multiple copies of its genome, 4 to 10 copies in each cell, providing redundancy. When radiation shatters the DNA, the cell doesn't panic. It collects the fragments and, using the intact copies as templates, begins reassembling the broken pieces. It has an arsenal of DNA repair enzymes, some unique to Deinococcus, others similar to repair mechanisms in other organisms, but present in much higher quantities or enhanced efficiency. The repair process is astonishingly precise. Even when the genome is fragmented into hundreds of pieces, the bacterium can reassemble it correctly within hours, stitching the pieces back together in the right order, restoring genes to their functional configurations. It's like taking a shredded book and reconstructing every page perfectly, with no reference except other similarly shredded copies. But there's more to radiation resistance than DNA repair. Deinococcus also protects its proteins from radiation damage by maintaining high levels of manganese ions and low levels of iron, which reduces the formation of damaging free radicals. Its cellular machinery is inherently resistant to oxidative stress, and it has systems to degrade damaged proteins quickly, recycling them before they can cause problems. Where did this extreme radiation resistance come from? Interestingly, Deinococcus doesn't live in naturally radioactive environments. It's found in soil, on meat, in other relatively mundane places. The leading hypothesis is that its radiation resistance is a byproduct of desiccation resistance. Extreme dryness also fragments DNA and damages cells in ways similar to radiation. Organisms that evolved to survive prolonged desiccation, lying dormant in dry soil for years, for instance, would need robust DNA repair mechanisms. Once you have those mechanisms, radiation resistance comes almost for free. This has practical implications. Deinococcus radiodurans is being studied for bioremediation of radioactive waste sites, where it could potentially degrade organic pollutants in environments too contaminated for human workers. It's also of interest for astrobiology. If life can exist on other planets or moons, it might need to survive high radiation environments. Europa, for instance, Jupiter's moon with an ocean beneath its icy shell, receives intense radiation from Jupiter's magnetosphere. Any life there would need to cope with radiation levels far higher than Earth's surface. Studying Deinococcus gives us insights into what's possible, how life can adapt to extremes, and it raises the broader question of life's limits. For every extreme we discover, extreme heat, cold, pressure, acidity, salinity, radiation, we find organisms that thrive there. Life on Earth occupies an astonishing range of environments. It's been found in Antarctic ice, in deep-sea hydrothermal vents, in acidic mine drainage, in salt crystals, in the upper atmosphere, kilometers underground in solid rock. Wherever liquid water exists, even transiently, life seems to find a way. This suggests that life, once started, is remarkably tenacious. It adapts, it evolves, it exploits niches that seem uninhabitable. And if life is this adaptable on Earth, maybe it's adaptable elsewhere too. Maybe the universe is full of extremophiles, organisms clinging to existence in environments we'd consider hellish, but which they call home. Maybe life doesn't require Earth-like conditions to flourish, just liquid, energy, and the chemical building blocks to build complexity. Deinococcus radiodurans is a small bacterium, invisible without a microscope, living unremarkable lives in soil and dust. But it carries within itself a demonstration of life's resilience, a proof that living systems can be far tougher than we once imagined. And in a universe filled with harsh radiation, extreme temperatures, and hostile chemistry, that resilience might be the rule rather than the exception. Here's a mystery from the ocean, a sound so powerful it was heard across an entire ocean basin. The bloop was an ultra-low frequency underwater sound detected in 1997, loud enough to be heard across the Pacific Ocean. Initially thought to be from a massive unknown creature, it was likely an ice quake, but the alternative captured our imagination. In the 1960s, during the Cold War, the U.S. Navy developed a network of underwater microphones, hydrophones, called SOSUS, Sound Surveillance System, to track Soviet submarines. Sound travels remarkably well in water, especially at certain depths where temperature and pressure create an acoustic channel that can carry low-frequency sounds for thousands of miles. After the Cold War, the Navy declassified some of this data and made it available to scientists studying ocean acoustics, marine life, and geological activity. In the summer of 1997, hydrophones in the Pacific picked up an unusual sound. It was extremely low frequency, around 20 hertz, at the edge of human hearing. And it was loud, detected by sensors over 5,000 kilometers apart. The sound rose in frequency over about 1 minute, creating a characteristic bloop pattern on spectrograms, hence the name. What could make such a sound? The initial speculation was biological, a massive marine animal, perhaps something unknown, something larger than a blue whale. Blue whales are the largest animals ever known to exist, reaching lengths of 30 meters and masses of 200 tons. Their calls are powerful, low frequency, and can travel long distances. But the bloop didn't quite match whale vocalizations. It was louder, with a different spectral profile. Could there be something even larger, a creature from the deep that we'd never encountered? The idea captured the public imagination. Sea monsters, giant squids, prehistoric survivors. The ocean is vast and largely unexplored, especially the deep regions beyond the reach of sunlight. The Marianas Trench descends to 11 kilometers. The average ocean depth is about 4 kilometers. We've explored less than 5% of the ocean floor in any detail. It's entirely plausible that large animals exist that we haven't documented. Giant squids, once thought to be mythical, turn out to be real. The megamouth shark wasn't discovered until 1976. Who knows what else is down there? But as researchers analyzed the bloop more carefully, the biological explanation became less likely. The sound's characteristics, its frequency range, the way it propagated, its seasonal timing, were more consistent with a geological or cryogenic source. Ice, particularly large icebergs calving from glaciers or ice shelves fracturing, can produce extremely loud, low-frequency sounds. These ice quakes occur when ice under tension fractures, or when large masses of ice scrape against rock or each other. The location of the bloop, triangulated from the hydrophone detections, was in the South Pacific, somewhat near the location of large ice shelves in Antarctica. The timing, southern hemisphere winter, when ice is most active, also fit. Subsequent similar sounds have been recorded, and most have been attributed to ice quakes or ice shelf movements. The bloop, in retrospect, was probably one of these. A massive ice event, an iceberg fracturing or an ice shelf breaking, releasing energy as sound. So the mystery is likely solved. It was ice, not a creature. But there's a lingering wistfulness, isn't there? The idea of something vast and unknown lurking in the ocean's depths is compelling, romantic even. The bloop became a symbol for our incomplete knowledge of the ocean, a reminder that the planet we live on still holds secrets, still has unexplored frontiers. And even though the bloop wasn't a creature, the ocean certainly contains life we haven't fully cataloged. Deep sea species, behaviors, ecosystems that remain mysterious. And there's something about sound in the ocean that's inherently evocative. Whale songs traveling across thousands of miles, ships' propellers audible continents away, submarine volcanoes rumbling, ice cracking and groaning. The ocean is alive with sound, a cacophony we rarely hear because we're surface dwellers, air breathers. But beneath the waves, sound is a primary sense for many organisms. Dolphins and whales echolocate, using sound to navigate and hunt. Fish communicate with grunts and clicks. The ocean is full of voices, full of signals we're only beginning to decode. So the bloop, even if explained, serves as a reminder. We share this planet with a vast, mostly unseen ocean world. Its soundscapes, its inhabitants, its geological processes are ongoing mysteries. We've listened to a few fragments, captured a few sounds, but the ocean continues its conversations, its crashes and songs, largely beyond our awareness, and occasionally something loud enough breaks through, a bloop, a hum, an anomalous sound. And for a moment we're reminded of how much we don't know, how much remains hidden beneath the surface. Now let's return to relativity, to one of its strangest and most verified predictions. Time actually passes more slowly near massive objects due to gravity, proven by atomic clocks on mountains versus sea level. Your head ages faster than your feet by about 90 billionths of a second over a lifetime. Minuscule, but real. This sounds like science fiction, but it's been measured with extraordinary precision. In the 1970s, physicists placed atomic clocks, instruments so accurate they lose less than a second over millions of years, on airplanes and flew them around the world. When the clocks landed and were compared to identical clocks that stayed on the ground, they disagreed. The flying clocks had experienced slightly less time. The difference was tiny, measured in nanoseconds, but it matched Einstein's predictions from general relativity. The effect arises because gravity is not a force in the traditional sense. It's a curvature of space-time. Massive objects like Earth warp the fabric of space-time around them, and this warping affects how time flows. Closer to a massive object where space-time is more curved, time runs slower relative to regions farther away. This is called gravitational time dilation. Your feet are closer to Earth's center of mass than your head. The difference is only about 2 meters, and Earth's gravitational field is relatively weak, so the effect is minuscule. But over a lifetime of, say, 80 years, your head will have experienced about 90 billionths of a second more time than your feet. Your brain is infinitesimally older than your toes. You are not aging uniformly. Different parts of your body are moving through time at slightly different rates. The effect becomes more dramatic with stronger gravitational fields. Near a neutron star, an object with the mass of the sun compressed into a sphere 20 kilometers across, time dilation would be substantial. A clock on the star's surface would run noticeably slower than one in orbit above it. Near a black hole, the effect becomes extreme. At the event horizon, time dilation approaches infinity. From the perspective of a distant observer, time for an object falling into a black hole seems to slow and stop, the object frozen at the edge forever. From the falling object's perspective, time progresses normally, and it crosses the horizon in finite time. But the two perspectives never reconcile. Each is valid in its own reference frame. This isn't just theoretical. GPS satellites orbiting Earth experience less gravitational time dilation than clocks on the surface because they're farther from Earth's mass. But they also experience time dilation due to their high velocity, special relativity's time dilation, which slows clocks that move fast relative to an observer. The two effects partially cancel, but don't eliminate each other. The net result is that satellite clocks run faster than ground clocks by about 38 microseconds per day. If this weren't corrected, GPS would accumulate errors of several kilometers within a day, rendering the system useless. Every GPS device in your phone relies on corrections for both gravitational and velocity-based time dilation, applying Einstein's relativity equations to keep your navigation accurate. So relativity isn't abstract physics. It's woven into the technology we use daily, and it's woven into reality itself. Time is not absolute, not a universal clock ticking uniformly everywhere. It's flexible, relative, dependent on motion and gravity. Two observers can disagree on the duration of events, on the simultaneity of distant occurrences, and both be correct from their own perspectives. This raises philosophical questions. If time is relative, if different observers experience different durations, what does it mean for something to happen now? The present moment isn't a universal instant shared by everyone. It's a local, subjective slice through space-time. Simultaneity is relative. Events that appear simultaneous to you might not be simultaneous to someone moving relative to you. The universe doesn't have a single, objective, present moment. It has a multitude of overlapping, relative present moments. And what about the nature of time itself? In Newtonian physics, time is a backdrop, a stage on which events occur. In relativity, time is woven together with space into a four-dimensional fabric. Events don't happen in space. At a certain time, they happen at space-time locations, points in a four-dimensional continuum. Past, present, and future are directions in this continuum, no more absolute than up, down, left, or right. Some physicists and philosophers take this further, suggesting that the flow of time, the sense that the present moment is special, that time passes from past to future, might be an illusion. The equations of relativity treat time as just another dimension. The block universe view suggests that all of space-time exists equally. Past, present, and future are all out there, equally real. We perceive time flowing because our consciousness moves through space-time, experiencing one moment after another. But from a God's eye view, the entire history of the universe is laid out, a static, four-dimensional structure. But this view is controversial. Many physicists and philosophers argue that the flow of time is real, that the present moment is genuinely different from past and future. The debate continues, unresolved. What's clear is that time is far stranger than everyday experience suggests. Your head and feet age at different rates. Satellites require relativistic corrections. Time bends near massive objects. The universe doesn't provide a universal clock. It provides a flexible, mutable, temporal dimension that shifts and stretches depending on where you are and how you move. And perhaps that's fitting. Time is the dimension we move through, the river we float on, the medium in which change occurs, its fluidity, its relativity, its dependence on context. All of this makes time less like a rigid ruler and more like the universe's way of preventing everything from happening at once. Though, given relativity, maybe everything does happen at once, depending on your frame of reference. It's enough to make a clock melt, or at least tick at slightly different rates, depending on where you put it. Let's travel back in time now, to a discovery that challenged our assumptions about ancient technological sophistication. The Antikythera mechanism from ancient Greece predicted astronomical positions decades in advance, using gear technology not seen again for 1,000 years. Discovered in a shipwreck, this 2,000-year-old computer suggests our ancestors were far more sophisticated than we assumed. In 1901, sponge divers exploring a Roman shipwreck off the Greek island of Antikythera found something strange among the amphorae and statues, a corroded lump of bronze and wood. Initially overlooked, it was later noticed that the lump contained gear wheels, dozens of them, precisely cut and arranged in a complex mechanism. This was shocking. The ancient Greeks were not supposed to have such advanced gear technology. The device dated to around 100 BCE, and nothing comparable would appear in Europe until medieval astronomical clocks over 1,000 years later. For decades, the mechanism was a puzzle. X-rays revealed its internal structure. At least 30 meshed bronze, gears of varying sizes, some with as many as 223 teeth cut with remarkable precision. There were inscriptions, instructions, labels, descriptions of celestial phenomena. As researchers painstakingly reconstructed the mechanism's function, They realized they were looking at an analog computer, a device designed to calculate and display astronomical information. The Antikythera mechanism could predict the positions of the sun, moon, and planets. It could calculate lunar and solar eclipses. It displayed the phases of the moon, the cycles of Olympic Games, and possibly even the positions of the 5 planets known to ancient astronomers. You turned a crank, and the gears rotated, simulating the motion of celestial bodies as seen from Earth. It was a planetarium, an ephemeris calculator, an educational tool, and possibly a navigation aid, all in one intricate bronze package about the size of a shoebox. The complexity is astounding. The mechanism compensated for the moon's elliptical orbit using a clever arrangement of gears that produced variable speed, an epicyclic gear system that wouldn't be seen again until the Renaissance. It used differential gears, mechanisms that add or subtract rotational speeds, considered an invention of the 16th century. The level of mathematical and mechanical sophistication required to design such a device is comparable to 18th century clockwork. Who built it? We don't know. The inscriptions suggest it was made in Rhodes, or possibly Syracuse, centers of learning in the Hellenistic world. It might have been designed by someone in the tradition of Archimedes, who was known for his mechanical inventions, or it might have been one of several such devices. Perhaps they were more common than we realize, but few survived because bronze was valuable and was melted down for reuse when the devices were no longer needed. The Antikythera mechanism only survived because it was lost in a shipwreck, protected from recycling by the sea. What does it tell us? That ancient technology was more advanced than we often assume. We tend to think of progress as linear, primitive ancient times, crude medieval technology, gradual improvement leading to modern sophistication. But the reality is messier. Knowledge is lost, civilizations fall, techniques are forgotten. The Roman Empire had concrete that could set underwater, a recipe lost for over a millennium. Damascus steel, with its remarkable properties, was produced in the medieval period, but the technique was lost and still hasn't been fully replicated. The Antikythera mechanism is another example, proof that ancient engineers achieved sophistication that we didn't think possible for them. And it raises questions about what else we've lost. If this device was unique, we got extraordinarily lucky that it survived. But if there were many such devices or other complex technologies, most would have been destroyed, melted down, or simply decayed beyond recognition. How much ancient knowledge vanished without trace? How many inventions were made and lost, only to be reinvented centuries later by people who had no idea they were rediscovering what their distant ancestors already knew? The Antikythera mechanism is a humbling reminder that intelligence and ingenuity are not modern inventions. People 2,000 years ago were just as clever as we are. They looked at the sky, noticed patterns, developed mathematics to describe those patterns, and built machines to predict them. They understood eclipses, orbital periods, the complex dance of celestial bodies. They encoded that understanding in bronze gears, creating a device of stunning elegance and functionality. And it's a reminder that history is fragmentary. We reconstruct the past from remnants, texts that survived, artifacts that endured, structures that didn't collapse. But most of the past is lost. Most people left no records. Most inventions were forgotten. The Antikythera mechanism survived by chance, pulled from the sea after 2,000 years. How many other marvels are still out there, buried, corroded, waiting to be found? Or lost forever, dissolved into the earth, their stories untold? We'll never know. But every discovery like this expands our view of what ancient people could do, and reminds us that we're not as different from them as we sometimes think. Now let's confront one of cosmology's deepest frustrations. Dark matter holds galaxies together, but has never been directly detected, despite making up 27% of the universe's mass energy. We know it's there because galaxies spin too fast to hold together otherwise, but every attempt to capture it has failed. The evidence for dark matter is indirect but compelling. In the 1970s, astronomer Vera Rubin measured the rotation speeds of galaxies by observing the Doppler shifts of stars and gas at various distances from the galactic centers. According to Newtonian gravity, stars farther from the center should orbit more slowly, just as outer planets in our solar system orbit the sun more slowly than inner planets. But Rubin found that stars in the outer regions of galaxies move just as fast as those closer in. The rotation curves were flat instead of declining. This shouldn't be possible with the visible matter alone. The galaxies should fly apart, their outer stars flung into intergalactic space by centrifugal force. But they don't. Something invisible is providing additional gravity, holding the galaxies together. That something is dark matter, matter that doesn't emit, absorb, or reflect light, detectable only through its gravitational effects. The evidence extends beyond rotation curves. Gravitational lensing, the bending of light by massive objects, shows that galaxy clusters contain far more mass than their visible stars and gas account for. The cosmic microwave background, the afterglow of the Big Bang, has temperature fluctuations that reveal the density of matter in the early universe, and the patterns require dark matter to match observations. Computer simulations of galaxy formation can't reproduce the observed structure of the universe without including dark matter. Every line of evidence points to the same conclusion. The universe contains large amounts of matter we can't see directly. So what is it? The leading candidates are WIMPs, weakly interacting massive particles. These would be subatomic particles that interact through gravity, and possibly the weak nuclear force, but not through electromagnetism, which is why they don't emit or absorb light. They'd be left over from the Big Bang, filling the universe as a diffuse halo around galaxies. Physicists have built detectors to catch WIMPs, sensitive instruments deep underground, shielded from cosmic rays, waiting for the extremely rare event of a WIMP colliding with an atomic nucleus. So far, despite decades of searching, no confirmed detection. Other candidates include axions, hypothetical particles even lighter and more weakly interacting than WIMPs, or primordial black holes formed in the early universe that are too small and too dark to detect directly but would contribute gravitational mass. Or perhaps dark matter is something entirely unexpected, a particle or phenomenon we haven't imagined yet. There's also the possibility that we're wrong about gravity. Maybe Newton's and Einstein's laws don't work as expected on galactic scales. Modified Newtonian dynamics, MAO-ND, proposes that gravity behaves differently at very low accelerations, which could potentially explain galaxy rotation curves without invoking dark matter. But Mond struggles to explain other observations, like gravitational lensing and the cosmic microwave background. It's not as successful as dark matter at fitting the full range of data. So dark matter remains the standard assumption. Most cosmologists believe it's real, even if we haven't detected it yet. But the failure to find WIMPs or axions after so many years of searching is frustrating. Maybe dark matter particles are even more elusive than we thought, interacting so rarely that detection is nearly impossible with current technology. Maybe we're looking in the wrong place, or with the wrong methods. Or maybe the universe is telling us that dark matter isn't made of particles at all. There's something unsettling about this. We've mapped the visible universe in extraordinary detail. Galaxies, stars, nebulae, black holes. We've detected gravitational waves, neutrinos, cosmic rays. But the majority of the matter in the universe remains invisible, undetectable except through gravity. It's like living in a house where most of the walls are invisible. You know they're there, you bump into them, you see pictures hanging on them, but you can't see the walls themselves. And dark matter isn't evenly distributed. It forms halos around galaxies, creating the gravitational scaffolding that holds galaxies together. It's denser in galaxy clusters, where it dominates the mass budget. It's flowing through you right now, billions of dark matter particles passing through Earth every second, through your body, interacting with nothing, ghosts in the cosmic machine. If dark matter particles do occasionally interact with normal matter, the rate is so low that you'll never notice. You could live 1,000 lifetimes and never experience a single dark matter collision in your body. What would it mean if we never detect dark matter directly? Would we be content with indirect evidence, with the gravitational signatures, knowing that the particles themselves remain forever beyond our reach? Or would we eventually question the assumption, rethink the models, search for alternative explanations? Science is built on the tension between evidence and detectability. Dark matter has evidence in abundance, but detectability has been elusive. And that tension, that gap between knowing something is there and being able to touch it, is where the mystery lives. Let's return to Earth, to forests and the hidden connections beneath the soil. Some trees in a forest are connected by underground fungal networks that share nutrients and even warnings about insect attacks. The Wood Wide Web suggests forests are more like superorganisms than collections of individuals competing for resources. For a long time, ecologists viewed forests as competitive arenas, where trees vie for sunlight, water, and nutrients. Each tree was an individual, maximizing its own survival and reproduction. But research over the past few decades has revealed a different picture, one where trees are connected, communicating and cooperating through an underground fungal network called the mycorrhizal network. Mycorrhizae are symbiotic relationships between fungi and plant roots. The fungus colonizes the root system, extending far into the soil with thread-like hyphae, fungal filaments much finer than roots, capable of reaching into tiny soil pores and accessing nutrients plants can't reach directly. In exchange for sugars produced by the plant through photosynthesis, the fungus provides the plant with water, nitrogen, phosphorus, and other minerals. It's a mutually beneficial partnership, but the fungus doesn't connect to just one plant. A single fungal network can link dozens or even hundreds of trees and plants, creating a web of connections beneath the forest floor. And through this web, trees can share resources. A tree in a sunny spot, photosynthesizing vigorously, can send excess sugars through the fungal network to a tree in shade that's struggling. A healthy tree can support its neighbors, and those neighbors can support others. The forest becomes a community, a collective where resources flow based on need as much as individual success. Even more intriguingly, trees appear to send chemical signals through the network. When a tree is attacked by insects, it can release volatile organic compounds into the air. A distress signal that warns nearby trees, which respond by increasing their production of defensive chemicals. But signals also travel underground through the mycorrhizal network. Trees receiving these signals ramp up their defenses preemptively before the insects reach them. It's an early warning system mediated by fungus. This was demonstrated by ecologist Suzanne Simard and her colleagues in experiments where they severed the mycorrhizal connections between trees and found that chemical signaling stopped. The network is the communication channel, and the fungus is the medium through which trees talk, if we can use that word. The trees aren't conscious, don't have intentions, but they are exchanging information, coordinating responses, behaving in ways that benefit the group. Simard also identified hub trees, or mother trees, large old trees that are central nodes in the mycorrhizal network, connected to many other trees. These hub trees appear to support younger trees, especially their own offspring, transferring more resources to them through the fungal network. When a hub tree is cut down, the surrounding trees suffer, growing more slowly and showing increased stress. The network loses a keystone, and the community weakens. This changes how we think about forests. They're not just collections of individual trees. They're ecosystems where cooperation and competition both play roles, where the underground network creates interdependencies, where what happens to one tree can affect many others. The forest is a superorganism in a sense, not conscious, not centrally controlled, but functionally integrated in ways that transcend individual boundaries. And it's not just trees and fungi. Soil is teeming with life. Bacteria, archaea, nematodes, insects, all interacting in complex webs. The mycorrhizal network is just one component of the soil ecosystem, but it's a crucial one, shaping plant communities, influencing which species thrive and which decline. Some plants can tap into the network better than others. Some fungi favor certain plants. There's competition and cooperation happening simultaneously, at scales from microns to kilometers. This research has practical implications. Forest management strategies that focus on maximizing timber production from individual trees might inadvertently weaken the mycorrhizal network, reducing overall forest health and resilience. Clear-cutting removes hub trees, disrupting the network and leaving younger trees without the support they'd normally receive. Understanding the underground connections suggests we should manage forests as integrated systems, not just collections of tree stalks. And there's something almost poetic about it, isn't there? The idea that beneath the visible world of trunks and branches, there's an invisible web of connection, a fungal internet through which trees exchange resources and information. We walk through forests seeing individual trees, but beneath our feet is a living network, pulsing with chemical signals, flowing with nutrients, binding the forest into a community. The trees are talking in their slow chemical way, and the fungi are listening, relaying, connecting. It's a conversation conducted over days and weeks, in molecules and sugars, beneath the soil where we can't see. But it's real, it's measurable, and it fundamentally changes our understanding of what a forest is. Let's venture beyond Earth now, to a phenomenon that occurs when humans leave the planet and see it from a perspective few ever experience. The overview effect causes astronauts to experience profound cognitive shifts when seeing Earth from space, but we don't know why it's so universal. Nearly every person who's seen our planet from orbit reports an overwhelming sense of connection and perspective that changes them permanently. The term was coined by author Frank White in 1987, but the experience itself has been reported consistently by astronauts since the earliest space missions. Yuri Gagarin, the first human in space, described Earth as appearing very small and feeling a surprising sense of unity. Edgar Mitchell, walking on the moon during Apollo 14, experienced what he called a samadhi, a profound sense that everything is interconnected, that the molecules in his body and the spacecraft were manufactured in ancient stars. He spent the rest of his life exploring consciousness and the nature of reality, forever changed by what he'd seen. Sally Ride spoke of looking at Earth and seeing no borders, no divisions, just a beautiful, fragile sphere floating in blackness. Ron Garan described it as seeing a planet that's alive, realizing that problems like pollution and war that seem insurmountable on the surface appear absurd from space, where you can see the whole planet, where national boundaries are invisible lines, and the atmosphere is a thin, delicate layer protecting everything. The effect seems to have several components. First, there's the visual impact, seeing Earth as a whole, as a single unified object, rather than an infinite flat plane extending in all directions. From space, Earth is small enough to take in at a glance, to hold in your visual field, yet large enough to contain everything you've ever known, every person you've loved, every place you've visited, every story, every conflict, every achievement. All of it exists on that small sphere. Second, there's the realization of fragility, the atmosphere, the thin blue line at the edge of the planet, looks impossibly delicate from space. It's all that stands between life and the vacuum. You can see storms swirling, clouds moving, the Terminator line between day and night sweeping across continents. And you realize how precious it all is, how vulnerable. There's no backup planet, no spare biosphere. This is it. Third, there's a shift in identification. On Earth, we identify with nations, cities, tribes, groups. From space, those distinctions vanish. You see Earth as a whole, and you become aware that you are an Earthling, that everyone is, that we're all on this spacecraft together. Borders are human constructs, invisible from orbit. The planet doesn't care about our divisions. It's a single integrated system, and we're all part of it. Astronauts often describe the effect as spiritual, not necessarily religious, but transcendent, a sense of awe and interconnection that goes beyond intellectual understanding. It's an emotional, almost visceral response. Some say it changes their priorities, making them more focused on environmental conservation, more interested in promoting peace and cooperation, more aware of how trivial many human conflicts appear from a cosmic perspective. But here's the mystery. Why is this response so consistent? It's not just a few astronauts. It's nearly all of them. People from different cultures, different belief systems, different backgrounds, they all report similar experiences. Is there something about the visual configuration, the sight of Earth as a whole, that triggers deep cognitive or emotional responses? Does the brain have circuits evolved for recognizing home? And does seeing the entire planet activate those circuits in an unusually powerful way? Or is it more about the context, the isolation, the silence of space, the contrast between the vibrant planet and the empty void surrounding it? Astronauts often describe space as profoundly silent, as black and empty in a way that's hard to convey. Earth, by contrast, is bursting with color and life. The juxtaposition might create a powerful emotional response, a recognition of how rare and special life is against the backdrop of cosmic emptiness. Some researchers think the overview effect might relate to awe, an emotion that arises when encountering something vast and beyond one's frame of reference. Awe has been shown to reduce the sense of self, to make people feel smaller and more connected to something larger. Studies suggest awe increases prosocial behavior, generosity, and ethical decision-making. Seeing Earth from space is certainly awe-inspiring. It's vast, it's beautiful, it's unlike anything in normal experience. Perhaps the overview effect is an extreme form of awe, amplified by the context and the uniqueness of the experience. There's also a practical angle. As space travel becomes more accessible, commercial spaceflight, space tourism, lunar bases, eventual Mars missions, more people will experience the overview effect. Will it change humanity's collective consciousness? If thousands, then millions of people see Earth from space, will it shift global priorities toward cooperation and environmental stewardship? Or will the effect diminish as space travel becomes routine, as the novelty wears off? It's impossible to say. But the consistency of the response among astronauts suggests there's something profound about the experience, something that touches something deep in human cognition or emotion. We evolved on the surface of a planet, perceiving our world as flat and infinite. Seeing it as a sphere, as a finite object in space, violates that evolutionary expectation. And perhaps in that violation, in the cognitive dissonance between what our brains expect and what our eyes see, something shifts. A perspective opens, a realization settles in, and the person who returns to Earth is different from the person who left. Let's return to quantum mechanics, to one of its most counterintuitive and experimentally verified phenomena. Some quantum particles can exist in multiple states simultaneously until observed, a phenomenon called superposition that defies everyday logic. Schrödinger's cat isn't just a thought experiment. Particles genuinely exist in many states at once, until measurement collapses them to one. The classic demonstration is the double-slit experiment. Fire a single photon at a barrier with two slits, and it passes through. But which slit? If you don't measure which slit the photon goes through, it behaves as if it went through both slits simultaneously, creating an interference pattern on the detection screen behind the barrier. Interference requires waves from both slits interacting, yet you sent only one photon. The only explanation is that the photon was in a superposition, simultaneously taking both paths, interfering with itself. But if you measure which slit the photon goes through, the interference pattern disappears. The photon behaves like a particle going through one slit or the other, not both. The act of measurement collapses the superposition, forcing the photon to choose a definite path. Before measurement, it was in a superposition of both paths. After measurement, it's in only one. This isn't limited to photons. Electrons, atoms, even small molecules have been shown to exhibit superposition. In 2019, researchers demonstrated quantum interference with molecules containing over 2,000 atoms, among the largest objects ever shown to behave quantum mechanically. The boundary between quantum and classical behavior is blurry, and we're pushing it to larger and larger scales. Superposition is more than just being uncertain about a particle's state. It's not that the particle has a definite position or momentum that we just don't know. It genuinely doesn't have a definite value until measured. It exists in a state where all possible values are present simultaneously, weighted by quantum amplitudes. This is what makes quantum mechanics so different from classical physics. Not just uncertainty, but genuine ontological indefiniteness. Schrödinger's cat was proposed as a thought experiment to illustrate the absurdity, as Schrödinger saw it, of applying quantum superposition to macroscopic objects. Put a cat in a box with a device that has a 50% chance of killing the cat based on a quantum event, say, the decay of a radioactive atom. Until you open the box and observe, quantum mechanics says the system is in a superposition. The atom is both decayed and not decayed. The cat is both alive and dead. Only when you observe does the superposition collapse, and the cat becomes definitively alive or dead. Schrödinger intended this to show how ridiculous it would be if quantum superposition applied to everyday objects. But experiments have increasingly shown that superposition is real at the quantum scale, and the boundary to classical behavior is a matter of decoherence. Interaction with the environment causes quantum superpositions to collapse rapidly for large objects. A cat interacts with countless air molecules, photons, and other environmental factors, causing its quantum state to decohere into a definite classical state almost instantaneously. But in principle, if you could perfectly isolate a cat from its environment, it would behave quantum mechanically. The cat wouldn't be a metaphor, it would be a quantum system. This has practical applications. Quantum computers exploit superposition to perform calculations. A classical bit is either 0 or 1. A quantum bit, a qubit, can be in a superposition of 0 and 1 simultaneously. With multiple qubits, you can represent a superposition of all possible binary strings, allowing quantum computers to explore many solutions in parallel. It's not magic. There are constraints on what quantum computers can do, but for certain problems, they can be exponentially faster than classical computers. But superposition also raises deep questions about the nature of reality. What does it mean for something to exist in multiple states? Is the superposition real, or is it just a mathematical description of our ignorance? The Copenhagen interpretation suggests that quantum systems don't have definite properties until measured. Superposition is real indefiniteness. The many worlds interpretation suggests that all possibilities in a superposition are realized, but in different branches of reality. When you measure, you don't collapse the superposition. You become entangled with it, splitting into versions of yourself that experience each outcome. Pilot wave theories suggest particles always have definite positions, but they're guided by a wave function that interferes with itself, reproducing superposition effects without actual indefiniteness. Physicists disagree on interpretation, but they agree on the experimental results. Superposition is real, Measurement affects outcomes, and quantum mechanics is one of the most accurately tested theories in science. The equations work. The predictions are confirmed. But what the equations mean, what's actually happening at the ontological level, remains mysterious. And there's something unsettling about it, isn't there? The idea that things don't have definite properties until observed, that reality at its foundation is probabilistic and undefined. We live in a macroscopic world where objects have positions, where causes lead to effects, where things are what they are. But zoom in far enough, and all of that dissolves into quantum fuzziness, superpositions of possibilities, particles that are everywhere and nowhere until you look. Perhaps that's the universe's final secret, that at the deepest level, reality isn't made of definite things, but of potentials, probabilities, fields of possibility that crystallize into actuality only when they interact, when they're measured, when consciousness or environment or whatever constitutes observation forces a decision. We live on the surface of this quantum ocean, experiencing a world that appears solid and definite, never suspecting that beneath it all, everything is shimmering with indefiniteness, existing in multiple states at once, waiting for something, measurement, interaction, observation, to make it real. Let's journey back in geological time to one of Earth's most dramatic and mysterious events. The Mediterranean Sea completely dried up and refilled multiple times during the Messinian salinity crisis. In events we can't fully explain, salt deposits thousands of feet thick testify to this catastrophic cycle, which would have been visible from space. About 596 million years ago, something happened that cut off the Mediterranean Sea from the Atlantic Ocean. The likely cause was tectonic movement, the African plate gradually closing the Strait of Gibraltar, or perhaps a combination of tectonic shifts and sea level changes that sealed the connection. Once isolated, the Mediterranean began to evaporate. This might seem slow, but on geological timescales, it was rapid. The Mediterranean is relatively shallow and narrow compared to major oceans, and it's located in a warm, dry climate where evaporation exceeds precipitation and river inflow. Cut off from the Atlantic's resupply of water, the sea level would have dropped steadily. Within a few thousand years, perhaps as few as 1,000, the Mediterranean could have dried almost completely, leaving behind a vast, hot, below sea level basin filled with salt flats and scattered hypersaline lakes. The evidence for this is striking. Drill cores from the Mediterranean seafloor reveal layers of evaporate minerals, gypsum, halite, and hydrite, salt deposits that form when seawater evaporates. These layers are thick, sometimes over 1 kilometer deep, representing enormous amounts of salt that could only accumulate from repeated cycles of evaporation. The pattern suggests the Mediterranean dried and refilled multiple times over about 600,000 years, each cycle leaving its signature in the sediment. Why multiple cycles? The prevailing theory is that the connection to the Atlantic opened and closed repeatedly. Perhaps small changes in sea level or tectonic movements or erosion would temporarily reopen the strait, allowing Atlantic water to flood back into the basin in a catastrophic event. A waterfall of biblical proportions, possibly the largest waterfall in Earth's history, with water pouring through the strait at rates that would refill the Mediterranean in a few years or decades. Then the connection would close again, and the cycle would repeat. Imagine what this would have looked like. The Mediterranean basin, normally filled with water, transformed into a landscape of salt deserts, deep canyons where rivers once flowed into the sea, now plunging down cliff sides to reach the floor thousands of feet below sea level. The climate around the basin would have changed dramatically. No moderating influence of a large body of water, more extreme temperatures, altered rainfall patterns. Species that depended on the sea would have gone extinct or migrated away. The entire ecosystem would have collapsed and reformed with each cycle. And then the refilling. If the Atlantic breached the barrier, water would have poured into the basin at unimaginable rates. Some estimates suggest flows of 100 million cubic meters per second, more than 1,000 times the flow of the Amazon River, the largest river on Earth today. The noise would have been deafening, audible for hundreds of kilometers. The water level would have risen meters per day, visible to any observer. If there had been human civilizations around the Mediterranean at that time, legends of this flood would have been passed down through generations. But this was before humans, before even human ancestors had split from other apes. The Mediterranean's death and rebirth occurred in deep prehistory, witnessed only by Miocene fauna. Why did it end? About 533 million years ago, the cycle stopped. The connection to the Atlantic stabilized, possibly due to further tectonic movements or sea level changes, and the Mediterranean has remained filled since. But the salt deposits remain, buried beneath millions of years of subsequent sedimentation, a record of a time when one of Earth's major seas vanished. There are still mysteries. We don't know exactly what controlled the opening and closing of the connection. We don't fully understand the ecological impacts, how species survived or recolonized. We don't know if similar events occurred in other isolated seas. The Black Sea, the Red Sea, other basins that depend on narrow connections to the ocean. Could they experience Messinian-type crises? Under what conditions? And there's a climate angle. Evaporating the Mediterranean would have affected global sea level. Locking that much water as salt deposits or releasing it back would have raised or lowered oceans worldwide by a few meters. Regional climate would have changed dramatically, possibly affecting the evolution of ecosystems and species in southern Europe and North Africa. Some researchers speculate that the Messinian salinity crisis might have influenced the evolution of early hominids in Africa by altering climate and habitat. But mostly, it's a reminder of how dynamic Earth is. We think of seas as permanent features, fixtures of the planet's geography. But on geological timescales, they come and go. Seas evaporate, ocean basins open and close, continents drift. The Mediterranean has existed in various forms for millions of years, but it nearly vanished entirely, and may someday vanish again if tectonics closes its connection to the Atlantic once more. Nothing is permanent. Even the seas are temporary, subject to the slow but inexorable movements of the planet's crust and the changing climates that govern water distribution. And if you could have stood on the edge of that desiccated basin, looking out across salt flats stretching to the horizon, thousands of feet below the level where the sea once was, it would have been one of the most alien landscapes on Earth. A dead sea floor, exposed to the sun, shimmering with heat and salt crystals, utterly barren. And then someday, the Atlantic would return, and within years, perhaps within your lifetime, had you been immortal, the entire basin would flood, transforming the desert back into a sea. Death and rebirth on a continental scale. The Mediterranean's secret history, written in salt. Here's another variation on synesthesia, this one particularly vivid and rare. Some people experience chromesthesia, a form of synesthesia where sounds automatically trigger seeing colors that others never perceive. For them, a trumpet might be orange, a violin purple, creating a constant internal light show, accompanying all auditory experience. This isn't metaphorical. Chromesthetes don't just associate sounds with colors, they perceive them. When they hear music, colors appear in their visual field. Not external hallucinations, but internal perceptions, often described as appearing in the mind's eye, but experienced with a vividness and automaticity that distinguishes it from mere imagination. The colors are consistent. A particular note, instrument, or type of sound always produces the same color. A C note might always be red, a G note always blue. For some chromesthetes, the colors are specific to pitch. Each note on the scale has a color. For others, it's timbre, the quality of sound that distinguishes a piano from a violin. Different instruments produce different colors even when playing the same note. Some experience colors in response to voices, with each person's voice having a characteristic color palette. Complex music creates complex color patterns, chords blending colors, melodies tracing colored paths through their visual space. Famous chromesthetes include composers and musicians. Duke Ellington reportedly saw colors with music and used this to guide his compositions and arrangements, choosing musicians whose sounds had colors that complemented each other. Pharrell Williams has described seeing colors with music since childhood, and it influences his production choices. Jimi Hendrix reportedly experienced sound-color synesthesia, though accounts vary. The experience can be beautiful or overwhelming. Music becomes multisensory, richer and more layered, but it can also be distracting. A chromesthete in a noisy environment might experience a chaotic light show of colors flashing in response to every sound. Some find certain sounds or music uncomfortable because the colors they produce are garish or unpleasant. Just as we might dislike certain color combinations visually, chromesthetes can dislike certain sound combinations for the color combinations they create. What causes chromesthesia? Like other forms of synesthesia, it likely involves cross-activation between brain regions. In this case, between auditory processing areas and visual areas. Sound activates not just the auditory cortex, but also regions involved in color perception. Brain imaging studies confirm this. When chromesthetes hear sounds, their color processing regions activate. But the specifics, why particular sounds produce particular colors, why some people develop chromesthesia and others don't, remain unclear. There's a genetic component, but also developmental factors. Some chromesthetes trace their synesthesia to childhood, recalling always having experienced sounds as colored. Others report it emerging or strengthening during adolescence, and a few lose it after brain injuries, suggesting the neural connections can be disrupted. There's also cultural variation. While chromesthesia itself is universal, the specific sound color mappings vary between individuals. Some commonalities exist. Low pitches tend to produce darker colors, high pitches, lighter colors. But beyond these general trends, associations are idiosyncratic. This suggests the mappings are learned or shaped by individual experience, not hardwired genetically. Interestingly, some non-synesthetes can learn synesthetic-like associations. Studies have shown that people trained to associate specific sounds with specific colors over several weeks begin to show automatic activation of color regions when hearing those sounds, similar to congenital synesthetes. The associations can be induced. This raises questions about the boundary between synesthesia and learned associations. Is synesthesia a qualitatively different phenomenon, or just an extreme form of associative learning that occurs during critical periods in brain development? And chromesthesia opens a window into perception more generally. We assume auditory and visual experiences are separate, processed by distinct brain systems, resulting in distinct qualia. But chromesthesia shows these systems can be linked, producing unified experiences that blend sensory modalities. Sound isn't just pressure waves in air processed by the auditory system. It's information that can activate multiple brain regions, creating experiences that transcend single modalities. This has implications for understanding how the brain constructs coherent perception from disparate sensory inputs. Normally, your visual, auditory, tactile, and other senses are integrated seamlessly. You see a person speaking, hear their voice, feel the handshake, and experience it all as a unified event, not separate streams of information. The brain is constantly binding sensory inputs, attributing them to objects, creating a coherent model of the environment. Chromesthesia might represent a different binding pattern, where auditory inputs are integrated into visual representations in unusual ways. For the chromesthete, this is normal. They don't experience sound and color as separate things connected secondarily. They experience sound-color, a unified percept. And that challenges our assumptions about what constitutes a sensory modality, what the boundaries between senses are, and how flexible perception can be. The brain is a remarkably plastic organ, capable of creating experiences far beyond the standard configuration. Chromesthesia is just one example, but it points to a deeper truth. Perception is constructed, flexible, and far more varied across individuals than we usually acknowledge. And if you're a chromesthete reading this, or listening perhaps, and seeing colors wash across your mental space as the words are spoken, your perceptual world is genuinely different from the majority's. You live in a richer sensory landscape, one where sound and color dance together, where music paints the air, where the world is more vivid and integrated than most people can imagine. And that's not a disorder or a deficit. It's a variation, a different way of being human, a reminder of the vast diversity of conscious experience hidden behind the commonality of our shared language and behavior. Let's venture into one of theoretical physics' most mind-bending proposals. The holographic principle suggests our three-dimensional reality might be a projection from information encoded on a two-dimensional boundary. Everything you experience, depth, volume, space itself, might be like a hologram calculated from data on a distant cosmic screen. This sounds like science fiction, but it arises from serious theoretical work in black hole physics and string theory. The principle was first suggested by physicist Gerard T. Hooft and later refined by Leonard Susskind in the context of solving the black hole information paradox, the question of what happens to information when something falls into a black hole. Here's the setup. Black holes have entropy, a measure of hidden information or disorder. Jacob Bekenstein and Stephen Hawking showed that a black hole's entropy is proportional to its surface area, not its volume. This is strange. Normally, entropy scales with volume. If you double the size of a gas container, you double its entropy. But for black holes, it's the area of the event horizon that matters. This suggested something profound. All the information about what's inside a black hole, everything that ever fell in, is somehow encoded on its two-dimensional surface. The three-dimensional interior is described by information on a two-dimensional boundary. And if this is true for black holes, maybe it's true for the universe as a whole. The holographic principle proposes that our entire universe, with all its three-dimensional complexity, might be encoded as information on a two-dimensional surface at the universe's boundary. Perhaps the edge of the observable universe, or some other horizon. The three-dimensional reality we experience would be a projection, a holographic image generated from that two-dimensional information. This doesn't mean the universe is literally a hologram in the way you might imagine a holographic image at a museum, a flat picture that looks three-dimensional. It's more abstract. The principle suggests that the maximum information content of any region of space is determined by its surface area, not its volume. Space itself might be emergent, arising from more fundamental two-dimensional physics. Evidence for this comes from string theory, particularly a result called the ADS-CFT correspondence, discovered by Juan Maldacena. This shows that certain theories of gravity in a three-dimensional space, actually 5 or more dimensions in the full theory, are mathematically equivalent to quantum field theories without gravity on the boundary of that space, a lower dimensional surface. The correspondence is exact. Every phenomenon in the higher dimensional bulk space has a corresponding description in the lower dimensional boundary theory. This doesn't prove our universe is holographic. ADS-CFT applies to specific types of spacetimes that don't match our universe exactly. But it demonstrates that holographic principles can work, that higher dimensional physics can emerge from lower dimensional descriptions. It's a proof of concept, suggesting that maybe, just maybe, our reality is similarly holographic. What would this mean? Philosophically, it's dizzying. The depth you perceive, the volume of space, the three-dimensionality of reality. All of this might be, in some sense, illusory or emergent. The fundamental description of reality might be two-dimensional, with our three-dimensional experience being a derived phenomenon, a useful but not fundamental way of organizing information. It doesn't change everyday experience. You'd still perceive depth, still navigate three-dimensional space. But at the deepest level, you might be a pattern of information encoded on a distant surface, with your three-dimensional existence being how that information is expressed. Your thoughts, your memories, your sense of occupying a three-dimensional body, all of it might reduce to two-dimensional data, structured in ways we're only beginning to understand. Some researchers have looked for experimental signatures of holographic physics. If the universe is holographic, there might be a fundamental limit to information density, a graininess to space-time at the Planck scale, detectable in principle through ultra-precise measurements of distances or times. Experiments have searched for such effects, so far without success, but the tests are at the limits of current technology. Others have explored whether quantum Entanglement, those spooky correlations between distant particles, might be related to the geometry of space itself in a holographic framework. In AD-O-CFT, entanglement in the boundary theory corresponds to geometric connections in the bulk space. Perhaps space-time itself is woven from entanglement, with the holographic principle being a key to understanding how space emerges from quantum information. It's speculative, unproven, and might be completely wrong, but the holographic principle represents a shift in how physicists think about reality, away from space and time as fundamental, toward information as the foundation. It's part of a broader trend in theoretical physics to view the universe as fundamentally informational, with matter, energy, and space-time being emergent phenomena arising from deeper informational or computational substrates. And that's profoundly strange. We think of information as abstract, as something represented in physical systems, but not physical itself. But if the holographic principle is true, information might be more fundamental than the physical. The universe might be, at its core, a structure of information, and everything else, particles, forces, space-time, might be how that information manifests. It's the kind of idea that's easy to dismiss as too abstract, too mathematical, too far from everyday reality to matter. But if it's true, it changes everything. Your existence, your experiences, the space you occupy, all of it might be a holographic projection from a two-dimensional boundary you can never see or visit, a cosmic surface encoding the information that is you. And maybe that's beautiful in its own way, a reminder that reality is stranger than it appears, that the universe conceals its deepest workings beneath layers of emergence, and that we're only just beginning to glimpse the true nature of existence. Let's return to the microbial world, to another discovery that reveals unexpected sophistication in the smallest forms of life. Some bacteria form electrical grids across distances, passing electrons through conductive filaments in what resembles a microbial power grid. These bacterial nanowires allow communities to share energy and coordinate behavior over distances thousands of times their body length. Bacteria are usually thought of as isolated cells, each fending for itself, competing for resources. But some species have evolved remarkable cooperative behaviors. Geobacter sulfurreducens, for instance, lives in oxygen-free environments like lake sediments or soil. It generates energy by metabolizing organic compounds and transferring electrons to metals like iron oxide outside the cell. Normally, the metal would need to be right next to the cell, but Geobacter can transfer electrons across distances of up to several centimeters, enormous by bacterial standards, through conductive protein filaments called pili. These filaments are essentially biological wires, nanometers in diameter, but micrometers to centimeters long, extending from one cell to another, or to distant electron acceptors. Electrons flow through them like current through a wire, allowing cells deep in sediment layers, far from oxygen or metal, to nonetheless respire, completing their metabolic cycles by shuttling electrons to distant locations where electron acceptors are available. This creates networks, bacterial communities linked by conductive filaments, forming something resembling an electrical grid. Cells in different locations can effectively share metabolic resources. A cell that has abundant organic compounds to metabolize, but no electron acceptors, can pass electrons through the network to cells that are in contact with metals or other acceptors. In return, the network might stabilize the environment, regulate pH, or distribute other metabolites. The community functions as a coordinated system, not just a collection of individuals. Even more remarkable, some bacteria can use these filaments for long-distance communication. Electrical signals, changes in voltage or current, can propagate through the network, potentially coordinating behavior across the community. Imagine bacteria thousands of times their body length apart, communicating through electrical pulses traveling along protein wires. It's reminiscent of neurons in a nervous system, though operating on different scales and through different mechanisms. Researchers are still working out the details. How exactly do the filaments conduct electricity? The PLE contain closely spaced aromatic amino acids that facilitate electron transfer through a process similar to conduction in organic semiconductors. How do bacteria coordinate the formation of networks? How do they maintain them? How widespread is this capability among bacterial species? There are practical applications. Bacterial nanowires could be used in microbial fuel cells, devices that generate electricity from organic waste by using bacteria to metabolize the waste and transfer electrons to electrodes. They're being explored for bioremediation of contaminated sites, where bacteria could metabolize pollutants in locations they couldn't otherwise access by shuttling electrons through nanowires. There's even interest in bioelectronics, using bacterial nanowires as components in biosensors or other devices that interface biology with electronics. But beyond applications, bacterial nanowires challenge our understanding of microbial life. Bacteria aren't just simple cells floating independently. They can form complex communities with differentiation, cooperation, communication, and shared infrastructure. They build electrical grids, essentially. They're tiny engineers, constructing networks that allow them to exploit environments more effectively than they could alone. And there's a philosophical angle. We often think of intelligence, cooperation, and communication as properties of complex organisms, animals with brains, social structures, language. But bacteria, lacking any nervous system or centralized control, can nonetheless organize into networks that display collective behavior. The network itself might be viewed as a kind of distributed intelligence, a system where no individual cell has a global view, but the collective exhibits coordination and adaptation. This is similar to how ant colonies function. No ant understands the colony, but the colony as a whole behaves intelligently, solving problems, adapting to changes. Bacterial communities linked by nanowires might function similarly. Cells communicating through electrical signals, coordinating metabolic activities, creating emergent behaviors that transcend individual capabilities. Intelligence, or at least intelligence-like behavior, might not require brains or even multicellularity. It might emerge from networks of simple agents following simple rules, whether those agents are ants, neurons, or bacteria. And it's a reminder that life at every scale is inventive. Bacteria have been evolving for billions of years, adapting to every conceivable environment, solving every conceivable metabolic challenge. In the process, they've invented solutions, like electrical conduction through protein filaments, that we're only now discovering and trying to understand. The microbial world is full of hidden sophistication, full of strategies, and mechanisms that evolution has honed over eons. We're still learning what bacteria can do, still surprised by their capabilities, and every discovery reveals that even the simplest life forms are far more complex than they appear. Let's return to the quantum world, to particles that blur the boundary between matter and antimatter. Some quantum particles are their own antiparticles, existing in a state of being both matter and antimatter simultaneously. The photon is its own antiparticle, and discovering others like the hypothetical Majorana fermion could revolutionize quantum computing. In particle physics, every particle has an antiparticle, a counterpart with opposite charge. The electron's antiparticle is the positron, identical except for having positive charge instead of negative. When particle and antiparticle meet, they annihilate, converting their mass into energy. This is the principle behind antimatter bombs in science fiction. Though creating and storing antimatter in reality is prohibitively difficult, but some particles are their own antiparticles. The photon, the particle of light, has no charge, so its antiparticle is indistinguishable from itself. A photon is simultaneously matter and antimatter in a sense. The Z boson, one of the carriers of the weak nuclear force, is also its own antiparticle. More intriguingly, there might be fermions, matter particles like electrons or quarks, that are their own antiparticles. These are called Majorana fermions, named after Italian physicist Ettore Majorana, who proposed them in 1937. Shortly after, Majorana mysteriously disappeared during a ferry trip never to be seen again, one of physics' enduring human mysteries, paralleling the particle mystery he left behind. Majorana fermions would need to be electrically neutral, since a charged particle can't be its own antiparticle. The neutrino, a nearly massless neutral particle that barely interacts with matter, is a candidate. If neutrinos are Majorana fermions, they'd be their own antiparticles, which would have profound implications for particle physics and cosmology. It would help explain why neutrinos have such tiny masses, and might be connected to why the universe has more matter than antimatter. Detecting whether neutrinos are Majorana particles is challenging. One signature would be neutrinoless double beta decay, a rare radioactive decay where a nucleus emits 2 electrons but no neutrinos. If neutrinos are Majorana fermions, this process could occur because the neutrino emitted by one decay event is immediately absorbed as an antineutrino by the other. Experiments are searching for this process in underground detectors, but so far it hasn't been definitively observed. Beyond fundamental particles, Majorana fermions can also appear as quasi-particles, collective excitations in certain materials that behave like particles. In topological superconductors and other exotic materials, electrons can organize in ways that create Majorana-like excitations at the edges or surfaces. These aren't fundamental particles, but they have the mathematical properties of Majorana fermions. Why does this matter? Majorana quasi-particles are of intense interest for quantum computing. Because they're their own antiparticles, they have special topological properties that make them resistant to decoherence. The environmental noise that destroys quantum information in conventional qubits. A qubit built from Majorana fermions could be far more stable, allowing quantum computers to operate for longer and perform more complex calculations. This approach, called topological quantum computing, is one of several competing strategies for building practical quantum computers. Several research groups claim to have created Majorana quasi-particles in laboratory materials, though the evidence remains somewhat controversial. Definitive proof requires ruling out alternative explanations for the observed signals, which is difficult. But if confirmed, it would be a major step toward topological quantum computing. There's also a philosophical angle. A particle that is its own antiparticle challenges our notions of identity and distinction. We think of matter and antimatter as opposites, as fundamentally different. But Majorana fermions blur that boundary, existing in a state that's neither fully matter nor fully antimatter, or perhaps both simultaneously. It's another example of quantum mechanics dissolving classical categories, revealing that reality at the fundamental level is more ambiguous, more interconnected than everyday experience suggests. And Majorana himself, the physicist who predicted these particles, adds a layer of human mystery to the scientific one. After proposing his theory, he boarded a ferry from Palermo to Naples and vanished. Some speculate he committed suicide, others that he staged a disappearance to escape his life, possibly entering a monastery. His body was never found, and despite investigations, his fate remains unknown. It's a reminder that behind every scientific mystery are human minds, human lives, human stories, sometimes as enigmatic as the phenomena they study. So Majorana fermions stand at the intersection of fundamental physics, practical technology, and human mystery. They might be the key to building stable quantum computers. They might explain why the universe is made of matter. They might illuminate the deepest symmetries of nature. Or they might remain elusive, theoretical entities that we can describe mathematically, but never quite capture in reality. Either way, the search continues, in particle detectors deep underground and in laboratories cooled to near absolute zero, looking for particles that are their own opposites, that dissolve the boundary between matter and antimatter, that bear the name of a physicist who disappeared into his own mystery. Let's close this section with an ancient mystery, one that blends archaeology, engineering, and speculation about purpose and meaning. The Nazca lines in Peru include perfectly straight lines stretching for miles, created by removing rocks to expose lighter soil beneath. These geoglyphs from 500 BCE to 500 CE are best viewed from the air, yet were made by people who never flew. Their purpose remains debated. The Nazca lines cover an area of about 500 square kilometers in the Peruvian coastal desert. They consist of hundreds of individual figures, geometric shapes, straight lines, stylized animals, and plants. The animal figures are the most famous: a spider, a hummingbird, a monkey, a condor, a whale. Some are enormous. The hummingbird is 93 meters long. The lines themselves, there are thousands, range from simple straight tracks to complex geometric patterns. Some lines run perfectly straight for several kilometers across varied terrain, which is a remarkable feat of surveying given the technology available. They were made by removing the reddish surface rocks and pebbles, exposing the lighter-colored soil beneath. The dry, stable climate of the Nazca Desert has preserved them for over 2,500 years. They're fragile, easily damaged by foot traffic, but because the region receives almost no rain and little wind, they've endured. Why were they made? This has been debated for decades. The most straightforward explanation is that they had religious or ceremonial significance. The Nazca people worshipped mountain and water deities, and some lines point toward sources of water or align with the sun's position at solstices. Walking the lines might have been a form of pilgrimage, a ritual journey, connecting sacred sites. The animal figures could represent constellations, totems, or symbols in Nazca mythology. Some researchers suggest they were offerings to the gods, visible from above, not to aircraft, but to deities imagined in the sky or mountain peaks. Others propose they were part of astronomical observations, though most lines don't align with celestial events in obvious ways. A more fringe theory, popularized in the 1960s, suggested the lines were landing strips or signals for ancient astronauts, extraterrestrials visiting Earth. This idea has no serious support. The lines aren't suitable for landing anything. They're shallow scrapes in desert pavement, not cleared runways. And the notion that ancient people couldn't create impressive works without alien help is both unsupported by evidence and dismissive of human ingenuity. What's clear is that the Nazca people had reasons meaningful to them, embedded in their culture and cosmology. The lines required significant effort, coordinating labor, planning layouts, executing designs precisely over large areas. They weren't casual doodles. They were intentional, important projects. And the fact that many are best appreciated from above suggests the Nazca conceived of an elevated perspective. Whether divine observers, shamanic visions, or simply an aesthetic understanding that the patterns had meaning beyond what any individual could see from the ground. Modern technology has revealed more lines than were previously known. Satellite imagery, drones, and AI algorithms have identified hundreds of additional geoglyphs, some smaller and more abstract than the famous figures. This suggests the Nazca lines were more extensive than we realized, perhaps integrated into daily life and ritual practice more deeply than a few iconic figures would suggest. There's also evidence that other cultures in the region created similar geoglyphs, and the tradition might have spanned centuries or millennia. The lines weren't unique to Nazca. They were part of a broader cultural pattern in ancient Andean societies. Understanding them requires understanding that broader context, the shared cosmologies and practices that motivated people across time and space to mark the earth with symbols, pathways, and art. And there's something haunting about them. Walking the desert, you might cross a line without realizing it. A slight change in the color of stones underfoot. But from above, from a plane or a drone, the pattern emerges. A hummingbird frozen in flight. A spider perfectly rendered, lines running to the horizon. The Nazca people saw their world differently than we do, imagined it from perspectives they couldn't physically access, and left marks on the land that would outlast their civilization. The lines are messages, though we're not entirely sure what they're saying, or to whom. Mysteries like the Nazca lines remind us that human cultures are diverse, that not every action maps onto our modern categories of utility or reason. The lines might have had practical purposes, ritual, astronomical, ceremonial, but they also had meaning, significance embedded in a worldview we can only partially reconstruct, and that gap between what we can observe and what we can understand is where mystery lives. The lines are there, indisputable and enduring, but the minds that made them, the intentions that drove their creation, the meanings they held, those are lost, leaving us to speculate, to wonder, to stand in the desert and look up at the sky, imagining what the Nazca saw when they looked down. Let's begin this next section with a phenomenon that reveals how much visual processing happens outside conscious awareness. Some people with blind sight can navigate obstacles despite having no conscious visual experience, their brain processing images they can't see. Damage to the visual cortex leaves them subjectively blind, yet subconscious pathways guide their actions around objects they insist they cannot perceive. Blind sight typically results from damage to V1, the primary visual cortex at the back of the brain. This area is considered essential for conscious vision. When it's destroyed by stroke, injury, or other causes, people lose conscious visual experience in the corresponding part of their visual field. They report seeing nothing, just darkness or absence where vision should be. By all subjective measures, they're blind in that region. But here's the remarkable part. Some of these individuals, when pressed to guess about objects in their blind field, to reach for something, to navigate around obstacles, to guess whether a light is on or off, perform far better than chance. They'll insist they're guessing randomly, that they see nothing, yet their hand reaches accurately for objects. They walk around barriers without bumping into them. They identify shapes or emotions on faces at rates, suggesting some visual information is getting through. This is blind sight, vision without awareness, processing without perception. The visual information still enters the eye and travels through the optic nerve, but instead of going through the conscious visual pathway, through V1, it takes alternate routes, subcortical pathways through structures like the superior colliculus, which evolved earlier and handles more primitive visual functions like motion detection and spatial awareness. These pathways can guide behavior without creating conscious experience. Patients with blind sight are often skeptical of their own abilities. When they successfully navigate an obstacle course in their blind field, they're surprised, insisting they were just lucky, that they couldn't see anything. Some become distressed by the disconnect, the feeling that their body knows something their conscious mind doesn't. It violates our intuitive sense that what we consciously experience is what guides our actions. The phenomenon reveals a deep truth about consciousness. Awareness is not necessary for information processing or even for guiding complex behavior. Your brain processes vastly more information than reaches consciousness. Most sensory input is filtered, handled by automatic systems, never bubbling up to awareness. Blind sight is an extreme example where the conscious path is severed entirely, but the unconscious processing continues, exposed in a way that's usually hidden. This raises philosophical questions. What's the difference between seeing and processing visual information? If a person can navigate using visual input but has no subjective experience of seeing, are they seeing or not? The answer depends on whether you define vision functionally, processing visual information to guide behavior, or phenomenologically, having conscious visual experience. Blind sight suggests these can be separated, function without phenomenology. It also relates to broader questions about consciousness. There are probably many processes in your brain right now that are processing information, guiding behavior, without your awareness. Your cerebellum coordinates movement. Your brainstem regulates breathing. Visual areas track objects in your peripheral vision, all without conscious involvement. Consciousness is like a spotlight, illuminating only a small fraction of your brain's activity. Blind sight shows what happens when the spotlight fails, but the underlying processes continue. Researchers have studied blind sight patients extensively, mapping which visual functions survive without V1. Motion detection often remains. Patients can sense when something moves in their blind field. Rough spatial localization works. Some emotional processing continues. Patients can detect facial expressions at above chance levels, even though they can't consciously see the faces. But fine detail, color, conscious recognition, these are lost, suggesting they depend specifically on cortical processing. There's also a therapeutic angle. Some patients can train their blind sight, improving their unconscious visual abilities through practice. With feedback, they learn to trust their guesses, to rely on the subconscious information. This doesn't restore conscious vision, but it can improve quality of life, allowing better navigation and object detection. The brain learns to use the surviving pathways more effectively. And blind sight has implications for understanding consciousness more broadly. If you can have sophisticated visual processing without awareness, what does that say about the nature of awareness itself? Is consciousness an add-on, a late stage in processing that creates subjective experience, but isn't necessary for the information itself? Or is there something special about conscious processing, some integration, some global broadcasting of information that unconscious processing lacks? Different theories of consciousness make different predictions about blind sight. Some suggest consciousness arises when information is globally broadcast, across the brain, accessible to multiple systems. In blind sight, information stays localized in subcortical areas, never reaching the global workspace, hence no awareness. Others propose consciousness requires specific types of neural activity, recurrent processing, feedback loops, that V1 enables but subcortical pathways lack. We don't have definitive answers yet, but blind sight patients provide a window into the dissociation between processing and experience, showing that the brain can know things the mind doesn't. That behavior can be guided by information that never reaches consciousness. It's unsettling in a way, the realization that your conscious self might not be in control as much as you think. That much of your behavior is guided by processes you'll never be aware of. Systems that process information and make decisions beneath the threshold of consciousness. For the person with blind sight, navigating a hallway in their blind field feels like stumbling in darkness, yet their feet avoid obstacles. Their hand reaches for doorknobs. The world guides them through channels they can't see, and they move through it like sleepwalkers, reacting to a reality they don't consciously experience. It's vision without sight, knowledge without awareness, action without intention, a reminder that consciousness, for all its seeming completeness, is only part of the story. Now let's return to particle physics, to a subtle violation that might explain existence itself. The universe's matter-antimatter asymmetry might involve CP violation, a subtle difference in how particles and antiparticles decay that we're still measuring. This tiny asymmetry, if confirmed, explains why you exist instead of annihilating into pure energy with your antimatter twin. In an ideally symmetric universe, matter and antimatter would be perfect mirrors of each other. Every process involving matter would have an equivalent process involving antimatter, proceeding at the same rate, following the same rules. Physicists call this CP symmetry, charge conjugation, C swaps particles with antiparticles. Parity, P mirrors space, and CP symmetry means the laws of physics are unchanged when you do both operations simultaneously. But CP symmetry is violated. It was first discovered in the 1960s in the decay of neutral kaons, particles that can transform into their antiparticles. Researchers found that kaons and antikaons decay at slightly different rates, a tiny asymmetry that shouldn't exist if CP symmetry were perfect. Later experiments confirmed CP violation in other particle systems, B mesons, D mesons, always small effects, but consistent and measurable. Why does this matter for the universe's matter-antimatter asymmetry? In the very early universe, right after the Big Bang, matter and antimatter were created in equal amounts from pure energy. As the universe cooled, particles and antiparticles collided and annihilated. If CP symmetry were perfect, all matter and antimatter would have annihilated completely, leaving only radiation, photons carrying the energy of what once was matter. But we exist. There's matter. This means that somehow matter survived the annihilation in slightly greater numbers than antimatter. For every billion matter-antimatter pairs that annihilated, there was apparently one extra matter particle. That tiny surplus became everything, all the stars, planets, galaxies, every atom in your body. The cosmic annihilation left behind a thin residue of matter, and that residue is the universe as we know it. CP violation provides a mechanism for this asymmetry. If particles and antiparticles decay at different rates, or if certain processes that create matter proceed faster than processes that create antimatter, then over time, even a very short time in the hot early universe, a slight excess of matter could accumulate. The CP violation observed in particle physics experiments is in the right direction to produce more matter than antimatter, though the magnitude is debated. Some calculations suggest the observed CP violation isn't strong enough to explain the full asymmetry, meaning there might be additional sources we haven't discovered yet. This is where the mystery deepens. The standard model of particle physics includes CP violation, but not enough to account for the observed matter-antimatter imbalance. This suggests new physics beyond the standard model, perhaps additional particles, new forces, or mechanisms active in the early universe that we haven't detected yet because they only operate at extremely high energies. Experiments search for stronger CP violation. Neutrino experiments, for instance, look for differences in how neutrinos and antineutrinos oscillate between different types. If neutrinos violate CP symmetry significantly, it might help explain the matter-antimatter asymmetry, especially if neutrinos played a role in the early universe's evolution. Other experiments smash particles together at high energies, creating exotic particles that might decay in CP-violating ways not yet observed. There's also a connection to time reversal. CP violation implies T violation, time reversal symmetry breaking. If you filmed a CP violating decay and ran it backward, it wouldn't look like a physically possible process. This ties into the arrow of time, the directionality of temporal evolution we discussed earlier. CP violation means the universe's laws aren't entirely time-symmetric, that there's a preferred direction built into particle physics itself, however subtle. And there's something profound about this. The reason you exist, the reason there's matter at all, comes down to a tiny asymmetry in how particles decay, a violation of symmetry so small that it went undetected for most of physics history. It's like discovering that the universe is built on an imbalance, a slight favoritism toward matter over antimatter, and that this favoritism is the only reason there's something rather than nothing. If CP symmetry were perfect, the universe would be simple and lifeless, photons expanding into darkness, energy cooling and diluting, no structure, no chemistry, no life. But reality has a small imperfection, a crack in the symmetry, and through that crack, everything emerged. Stars formed from the residual matter, galaxies coalesced, planets accreted, chemistry became biology, consciousness arose, and here you are, contemplating the asymmetry that made your existence possible. We're still measuring, still searching for the full picture. The CP violation we found might be just part of the story. There could be additional mechanisms, new particles, unexpected interactions that contributed to the matter-antimatter imbalance. But even what we know is remarkable, a reminder that the universe's most fundamental properties, the reasons for its existence, come down to subtle violations of symmetry, tiny imbalances in processes occurring in the first fractions of a second after creation. And maybe that's fitting. Perfection, absolute symmetry, would be sterile. It's the imperfections, the asymmetries, the violations of idealized rules that make reality interesting, that allow for complexity and change and diversity. CP violation is one such imperfection, a small deviation from perfect symmetry that had cosmic consequences, and in a sense, you are a consequence of that violation, a downstream effect of a tiny asymmetry in particle decay billions of years ago. Existence balanced on a razor's edge, and the edge was just slightly tilted in favor of matter. That tilt made all the difference. Here's a phenomenon that sounds impossible, yet occurs regularly, defying our simple models of thermodynamics. The Mpemba effect shows that hot water can freeze faster than cold water under certain conditions, violating our intuitive physics. Even Aristotle noticed this phenomenon, but physicists still debate exactly why it happens: convection, evaporation, or something else entirely. The effect is named after Erasto Mpemba, a Tanzanian student who in 1963 noticed that hot ice cream mix froze faster than cold mix when making ice cream. His teacher dismissed it as impossible, but Mpemba persisted, eventually collaborating with a physicist to document the effect. They published a paper in 1969, bringing the phenomenon to scientific attention, though observations of it date back centuries. Aristotle mentioned it, Francis Bacon noted it, Descartes wrote about it. And yet, despite these historical observations and modern experimental confirmations, we don't have a fully satisfying explanation for why it happens. The challenge is that hot water freezing faster than cold water isn't a universal law. It occurs under specific conditions, and those conditions are complicated and context-dependent. Several mechanisms might contribute. One is evaporation. Hot water evaporates faster, reducing the total mass that needs to freeze. Less water freezes faster, so if you start with hot water, some evaporates before freezing begins, leaving less to freeze than if you'd started with cold water. But this doesn't fully explain cases where the mass is carefully controlled, and the effect still occurs. Another is convection. Hot water circulates more vigorously due to temperature gradients, potentially creating conditions that accelerate cooling or freezing. The convection patterns might expose more of the water to cold surfaces or cold air, increasing heat transfer rates. But again, this is only a partial explanation. It depends on container shape, volume, and environmental conditions. Dissolved gases might play a role. Hot water holds less dissolved gas than cold water. So if you start with hot water, it has lower gas content, which might affect how ice crystals nucleate and grow. But experiments varying gas content have given inconsistent results. There's also supercooling. Water can remain liquid below its freezing point if it's pure and undisturbed. Cold water might supercool more readily, delaying the onset of freezing, while hot water, through its more vigorous thermal motion, might nucleate ice earlier. Once ice starts forming, it can proceed quickly, potentially overtaking cold water that's still supercooled. Or perhaps it's a combination, different mechanisms dominating in different conditions. Container shape affects convection. Initial temperature affects evaporation rate. Water purity affects supercooling. Environmental factors, humidity, air temperature, pressure, all influence the process. The Mpemba effect might not be a single phenomenon, but a collection of related effects that happen to produce the same counterintuitive result. Hot water sometimes freezes faster than cold. This complexity frustrates attempts to establish a universal explanation. Some researchers question whether the effect is even real, suggesting it's experimental error or confirmation bias. Others have replicated it under controlled conditions, showing it's genuine but highly sensitive to parameters. The debate continues. There's also a theoretical angle. Some physicists have proposed explanations based on hydrogen bonding in water. Hot water might have a different distribution of hydrogen bond configurations, and these configurations might affect how easily water transitions to ice. When you cool hot water, the bonds rearrange in ways that happen to facilitate freezing under certain conditions. This is speculative and not fully worked out, but it points toward deeper questions about water's structure and dynamics. Water is strange, as we discussed earlier. It violates many normal substance behaviors. Perhaps the Mpemba effect is another manifestation of water's anomalousness, its tendency to break the rules in ways we don't fully understand. And maybe that's appropriate. Water is the substance of life, the medium in which chemistry became biology. Its strangeness enables its versatility. The Mpemba effect is just one more way water confounds our expectations. For practical purposes, the Mpemba effect is a curiosity. It's not reliably useful. You can't count on hot water freezing faster for making ice cubes or freezing food. But it's a reminder that even simple, everyday phenomena can hide complexity. Freezing water seems straightforward. Cool it down, it solidifies. But the actual process involves nucleation, crystal growth, heat transfer, convection, evaporation, supercooling, and who knows what else. Complexity lurks beneath simplicity. And there's something satisfying about the fact that Aristotle noticed this over 2,000 years ago, and we still don't fully understand it. Some mysteries persist not because they're inaccessible. We can study water freezing as much as we want, but because they're complicated, sensitive to conditions, not reducible to a single clean explanation. The universe is messy. Nature doesn't always follow the textbook idealizations, and sometimes hot water freezes faster than cold water, defying intuition, reminding us that reality has surprises even in the familiar. Here's a variation in human vision. that reveals how subjective color perception truly is. Some people have tetrachromacy, 4 types of color receptors instead of 3, allowing them to see millions more colors than the rest of us. They live in a more vibrant world, perceiving distinctions invisible to normal vision, and might not even realize their experience is unique. Most humans are trichromats. We have 3 types of cone cells in our retinas, sensitive to short blue, medium green, and long red wavelengths. By combining signals from these 3 cone types, our brains construct the perception of color across the visible spectrum. We can distinguish about 1 million different colors, which seems like a lot, until you consider that this is a limitation, a boundary imposed by our sensory hardware. Tetrachromats have 4 types of cones. The 4th cone type, typically found only in women due to the genetics of color vision, is sensitive to wavelengths between the standard green and red cones, somewhere in the yellow-orange range. With 4 types of cones, the brain can construct a higher dimensional color space, perceiving distinctions that trichromats cannot. How many more colors can they see? The estimates vary, but potentially millions more, perhaps even 100 million distinct hues that they can differentiate. To a tetrachromat, 2 surfaces that appear identically colored to a trichromat might look completely different, one more orange tinted, the other more yellow, distinctions invisible to the rest of us. Identifying tetrachromats is challenging. You can't just ask someone if they see more colors. They have no reference for what normal vision is like. If you've always seen certain distinctions, you'd assume everyone does. Some tetrachromats only discover their enhanced vision when tested, when they're shown color chips that appear identical to trichromats but which they can easily distinguish. The most famous case is Concetta Antico, an artist and tetrachromat who describes seeing color in shadows, in supposedly neutral grays, in places where others see none. Rocks, to her, have subtle hues, lavenders, greens, blues, that others don't perceive. Her paintings reflect this, with complex color palettes that capture nuances invisible to trichromatic viewers. She literally sees a more colorful world. Tetrachromacy is likely more common than realized, but functional tetrachromacy, where the brain actually uses the 4th cone type to construct enhanced color vision, might be rare. Having the 4th cone type isn't enough. The brain needs to develop neural pathways to process the additional information. Some women have the genetic mutation for a 4th cone, but don't experience enhanced color vision, possibly because their brains never learned to interpret the extra signals. There's a gender angle. The genes for red and green cones are on the X chromosome. Women have 2 X chromosomes, so they can have different versions of these genes on each chromosome. Through a process called X inactivation, different cells in the retina express different versions, potentially creating a mosaic of cone types. If one X chromosome has a shifted version of the green or red cone gene, the woman might end up with 4 functional cone types instead of 3. Men with only one X chromosome are less likely to be tetrachromats. What's it like to be a tetrachromat? We can't fully know. Color experience is inherently subjective. But tetrachromats describe seeing more gradients, more subtlety, more complexity in color than others report. A sunset might have not just oranges and reds, but a symphony of intermediate hues that blend and shift in ways trichromats can't perceive. Tetrachromats might be better at color matching, at distinguishing similar shades, at noticing color variations that others miss. Interestingly, some animals are natural tetrachromats. Birds typically have 4 cone types, allowing them to see into the ultraviolet range. Many insects have UV vision. Some fish have even more complex color vision systems. To these animals, the world is ablaze with colors we can't imagine. Flowers have UV patterns guiding pollinators. Birds have UV plumage patterns invisible to mammalian predators. The world is painted in spectra we're blind to. This raises the broader question: how much of reality are we missing? Our senses are tuned to a narrow range of stimuli: visible light between 400 and 700 nanometers, sound between 20 and 20,000 hertz, a limited chemical palette detectable by nose and tongue. Beyond these ranges lies information we can't access directly. Infrared and ultraviolet light, ultrasound and infrasound, chemical signals we can't smell, electric and magnetic fields we can't sense. All of this exists, all of it potentially meaningful but invisible to us. Tetrachromats are a reminder that even within the human species, perception varies. We assume shared experience, that the color you call red looks the same to me. But maybe it doesn't. Maybe your red is my orange. Or maybe colors for you have dimensions I can't conceive. We can never truly know what another person's subjective experience is like. We can only describe, compare, and infer. And tetrachromacy shows that some people genuinely do experience the world differently, not in belief or interpretation, but in the raw sensory data reaching their consciousness. For the tetrachromat, explaining their experience to trichromats must be like trying to describe color to someone who's colorblind, or sound to someone who's deaf. The dimensions just aren't there for comparison. So they live in a world slightly more colorful than ours, seeing distinctions we'll never see, experiencing a richness of hue that we can only know exists intellectually, never perceptually. And they remind us that reality is always larger than our perception of it, that the world has depths and dimensions beyond what any one sensory system can capture. Let's shift to the geological forces that shape our planet, to a pattern so prominent it defines the very structure of active geology. The Pacific Ring of Fire contains 75% of Earth's volcanoes, forming a near-perfect circle we're still learning to predict. This horseshoe of tectonic violence surrounds an ocean and concentrates most of the planet's seismic energy in one ominous arc. The Ring of Fire is a 40,000-kilometer arc of tectonic boundaries encircling the Pacific Ocean. It runs from New Zealand up through Indonesia, the Philippines, Japan, along the Aleutian Islands, down the west coast of North America, through Central America, and along the Andes in South America. Nearly every major volcanic eruption, nearly every devastating earthquake in recorded history has occurred along this ring. Why here? The Pacific Plate, one of the largest tectonic plates on Earth, is bordered almost entirely by subduction zones, places where oceanic crust dives beneath continental crust or other oceanic crust. When one plate subducts beneath another, it descends into the mantle, where heat and pressure cause it to release water and other volatiles. These volatiles rise into the overlying mantle, lowering its melting point and causing magma to form. That magma rises, accumulates, and eventually erupts, forming volcanoes. So the Ring of Fire marks the boundaries of the Pacific Plate, a ring of subduction zones encircling the ocean. But it's not perfectly circular. It's irregular, broken by transform faults and other tectonic features, And the activity varies. Some sections, like Japan or Indonesia, are intensely active with frequent eruptions and earthquakes. Other sections are quieter, though still dangerous. Predicting eruptions and earthquakes along the Ring of Fire remains challenging. We can monitor volcanoes for warning signs, seismic swarms, ground deformation, gas emissions, but predicting exactly when an eruption will occur or how large it will be is still uncertain. Earthquakes are even harder. We know stress builds along faults, but we can't predict when it will release. The best we can do is identify high-risk areas, estimate probabilities over decades or centuries, and prepare for inevitable events. And the consequences are severe. The 2011 Tohoku earthquake and tsunami in Japan killed nearly 20,000 people and triggered the Fukushima nuclear disaster. The 1906 San Francisco earthquake devastated the city. The 1985 Mexico City earthquake killed thousands. The 1991 eruption of Mount Pinatubo in the Philippines ejected so much ash and sulfur dioxide into the atmosphere that it cooled global temperatures for years. Krakatoa's 1883 eruption was heard 4,800 kilometers away and killed tens of thousands. The Ring of Fire has shaped human history through disasters, forcing societies to adapt, rebuild, and learn to coexist with tectonic violence. But it's also shaped the planet's geography and ecology. Volcanic soils are fertile, rich in minerals. Civilizations have thrived near volcanoes despite the risk because the land is productive. Volcanic islands, Japan, Indonesia, the Philippines, exist because of subduction zone magmatism. Without the Ring of Fire, these islands wouldn't exist, and the cultures that developed on them would never have arisen. There's also a deep time perspective. Plate tectonics, with its cycles of subduction and spreading, has operated for billions of years. The Ring of Fire is just the current configuration. In the past, other subduction zones, other rings of fire, shaped other oceans. In the future, as plates continue to move, the Ring of Fire will change. The Pacific Plate is shrinking as it subducts beneath surrounding plates. Tens of millions of years from now, it might close entirely, and the geography of Earth will be unrecognizable. And there's something almost poetic about the name, the Ring of Fire. It evokes danger, power, a border between stability and chaos. The Pacific, largest of Earth's oceans, is encircled by volcanic mountains and earthquake-prone faults, a rim of fire marking where the planet's interior heat escapes, where tectonic forces release their pent-up energy. We live on a dynamic planet, one that's constantly reshaping itself, and the Ring of Fire is a visible manifestation of that dynamism. For those living within the ring, it's a fact of life. Earthquake drills, volcano evacuation plans, building codes designed to withstand seismic shaking. All of this is normal, necessary. The ground is not stable. It moves, cracks, heaves. Mountains are not eternal. They grow, erupt, collapse. The Ring of Fire teaches humility, a reminder that human structures are temporary, that nature operates on scales of power we can mitigate but never control. And we keep studying it, monitoring seismographs, measuring ground deformation, sampling volcanic gases, trying to understand the patterns, to see the earthquakes coming, to predict the eruptions. We've made progress. Some eruptions are successfully predicted. Evacuations save lives. But the Earth keeps its secrets, releases its energy on its own schedule. The Ring of Fire burns on, indifferent to our presence, ancient and ongoing, a circle of tectonic activity that will outlast civilizations, shaping the planet long after we're gone. Let's turn to the cutting edge of information technology, to machines that exploit quantum mechanics to solve problems in fundamentally new ways. Quantum computers can theoretically solve certain problems exponentially faster than classical computers. But we don't fully understand the limits. They harness superposition and entanglement to explore all possible solutions simultaneously, computing with the fabric of reality itself. Classical computers process information in bits. Each bit is either 0 or 1, and computation is a sequence of logical operations manipulating these bits. Quantum computers use qubits, which can be in a superposition of 0 and 1 simultaneously. With multiple qubits, you can represent a superposition of all possible bit strings. A quantum computer with 300 qubits can represent more states than there are atoms in the observable universe. This doesn't mean quantum computers can magically solve any problem faster. Quantum algorithms must be carefully designed to exploit superposition and interference. You set up your qubits in a superposition of all possible inputs. Apply quantum operations that allow different paths to interfere constructively or destructively, and then measure, collapsing the superposition to an answer. If the algorithm is designed correctly, wrong answers interfere destructively and cancel out, while the correct answer interferes constructively and emerges with high probability. Some problems are well suited to this approach. Shor's algorithm can factor large numbers exponentially faster than the best-known classical algorithms, which has implications for cryptography. Most internet encryption relies on the difficulty of factoring large numbers, and quantum computers could break it. Grover's algorithm can search unsorted databases quadratically faster than classical search. Quantum simulation can model quantum systems, like molecules, materials, or quantum field theories, more efficiently than classical simulations, potentially revolutionizing chemistry, materials science, and fundamental physics. But we don't fully understand quantum computing's limits. Which problems can quantum computers solve efficiently that classical computers cannot? This is related to fundamental questions in computational complexity theory. What are the boundaries between different complexity classes? We know some problems quantum computers can't help with. They can't solve NP-complete problems in polynomial time, for instance, unless some major assumptions in complexity theory are wrong. But there are vast regions of uncertainty, problems where we don't know if quantum computers offer advantages. And building quantum computers is extraordinarily difficult. Qubits are fragile. They interact with their environment, causing decoherence, which destroys the quantum superposition. Quantum computers must operate at temperatures near absolute zero, isolated from vibrations, electromagnetic noise, even stray cosmic rays. The qubits must be precisely controlled and measured. Error rates must be kept incredibly low, requiring quantum error correction, encoding information redundantly in multiple physical qubits to protect against errors. Current quantum computers are small, dozens to hundreds of qubits, and noisy, with error rates that limit how long computations can run. They're in the NISQ era, noisy intermediate-scale quantum devices, useful for some specialized tasks, but not yet capable of solving large-scale practical problems that classical computers can't handle. Building fault-tolerant quantum computers with millions of qubits will require major advances in qubit technology, error correction, and control systems. But progress is accelerating. Multiple approaches compete: superconducting qubits, trapped ions, topological qubits, photonic qubits, each with advantages and challenges. Tech companies and governments are investing heavily, and there's excitement about what becomes possible once quantum computers mature, designing new drugs by simulating molecular interactions, discovering new materials with desired properties, optimizing complex systems, breaking current encryption while developing quantum-secure alternatives, perhaps even insights into fundamental physics by simulating quantum field theories or quantum gravity. There's also something philosophically intriguing. Quantum computers harness the same superposition and entanglement that make quantum mechanics so conceptually strange. They're using the universe's fundamental weirdness as a computational resource. In a sense, a quantum computer doesn't just calculate. It explores many paths through possibility space simultaneously, using quantum interference to guide itself toward solutions. It's computing with reality's underlying structure, using the quantum substrate on which classical physics emerges. And there are interpretational questions. In the many worlds interpretation, a quantum computer explores all possible solutions simultaneously across many branches of reality, and measurement selects the branch with the correct answer. In the Copenhagen interpretation, the superposition is potential until measured, and the algorithm manipulates potentials to make the desired outcome probable. Different interpretations give different stories about what's really happening inside a quantum computer, though they all agree on the experimental predictions. For now, quantum computing remains a field of immense promise and significant challenges. The theory is solid. We know quantum. Computers can offer advantages for certain problems. The engineering is hard. Building large, reliable quantum computers pushes the limits of technology. But the trajectory is clear. We're learning to control quantum systems, to harness their strangeness, to compute with superposition and entanglement. And if we succeed, it will represent a new era in computation, one where we're not just manipulating bits on silicon, but orchestrating quantum states, computing with the deepest properties of reality itself. Let's return to human psychology, to a cognitive tendency that shapes how we perceive the world. The Baader-Meinhof phenomenon makes something seem ubiquitous once you notice it, revealing how attention sculpts our perceived reality. You buy a new car and suddenly see that model everywhere, not because it's more common, but because your brain is now primed to notice. This has two components. First is selective attention. Once something enters your awareness, your brain begins filtering for it automatically. Before you bought that car, thousands of cars passed through your visual field daily, but your brain didn't flag any particular model as noteworthy. After you buy one, your brain has a reason to notice. It's now relevant to you, part of your self-concept, something you have a relationship with. So every time you see that model, it catches your attention, stands out from the background. Second is confirmation bias. Once you notice the pattern, you remember instances that fit and forget instances that don't. You remember seeing 3 of the same car on your commute, but you don't consciously register the hundreds of other cars. The 3 instances feel significant, seem like evidence of ubiquity. Your brain is constructing a narrative. This car is everywhere, even though its actual frequency hasn't changed. The name comes from a discussion thread about the Baader-Meinhof Group, a German terrorist organization from the 1970s. Someone mentioned noticing the name twice in a short period after never hearing it before, and others chimed in with similar experiences. Someone coined the term Baader-Meinhof phenomenon for the effect, and it stuck. Psychologists call it frequency illusion, or sometimes connect it to recency illusion, the mistaken belief that something has become more common recently, when really you've just become more aware of it. It's related to availability heuristic, judging the frequency or importance of something by how easily examples come to mind. If examples are easily recalled, we assume the thing is common, even if recall is biased by recent exposure or salience. This cognitive quirk shapes more than just car spotting. It influences how we perceive trends, risks, cultural phenomena. You hear about a rare disease, then suddenly hear about it multiple times. Is it spreading, or are you just noticing? A friend mentions a book, then you see it recommended online. Then someone else brings it up. Is it a bestseller, surging in popularity, or have you just started paying attention? Often it's the latter. The phenomenon can feed into conspiracy thinking. Notice a few coincidences, start looking for patterns, and confirmation bias ensures you'll find more. Random events cluster. That's probability, but we interpret clusters as meaningful. See the same number repeatedly, and it feels like a sign, like the universe is sending a message. But you're likely encountering that number as often as any other. You're just noticing it now. It also affects how we consume media and news. If you read an article about a social issue, you're more likely to notice subsequent articles on that issue. This can create the impression that the issue is escalating or becoming more prominent, even if coverage is stable. Media outlets aware of audience interest might also increase coverage once a topic gains traction, creating a feedback loop where attention drives more content, which drives more attention. Understanding the Baader-Meinhof phenomenon is a form of cognitive humility, recognizing that your perception isn't a neutral window on reality, but a constructed, filtered, biased representation. Your brain is constantly choosing what to attend to, what to remember, what to connect. It's trying to find patterns to make sense of the overwhelming sensory data flooding in every moment. Most of the time, this works well. Pattern recognition is essential for learning, for predicting, for surviving. But sometimes, the patterns aren't really there, and this connects to broader questions about perception and reality. How much of what you experience is out there versus in here? The world exists independently of you, but your experience of the world is always mediated by your senses, attention, memory, and cognitive biases. Two people can witness the same event and come away with different memories, different interpretations, even different accounts of what happened. Reality is filtered through the lens of perception, and that lens is shaped by prior experiences, expectations, motivations. The Baader-Meinhof phenomenon is a small example of this filtering. It shows how noticing something changes your experience of frequency, how attention shapes perception. And it's a reminder to question your intuitions about what's common, what's rare, what's increasing or decreasing. Our brains are powerful pattern detectors, but they're not infallible. Sometimes the pattern is real. Sometimes it's just Baader-Meinhof, your brain playing tricks, attention creating the illusion of ubiquity where there's only coincidence. So next time you think, I keep seeing this everywhere, pause and ask, has it actually become more common, or have I just started noticing? Often it's the latter, and recognizing that is a small step toward clearer thinking, toward understanding how your mind constructs the reality you experience, toward appreciating that the world you perceive is always, in some sense, a world your brain has made. Let's return to the extremes of biological endurance, to organisms that challenge our definitions of life and death. Some microbes have been revived after 250 million years in salt crystals, challenging our definitions of dormancy and death. These bacteria were buried before dinosaurs existed, waiting in suspended animation through the rise and fall of countless species. The discovery was controversial. In 2000, researchers reported reviving bacteria from salt crystals, halite deposits, that had formed in the Permian period, around 250 million years ago. The crystals, found in underground salt deposits in New Mexico, contained tiny fluid inclusions, microscopic pockets of ancient brine trapped when the crystals formed. And inside those fluid inclusions, visible under a microscope, were bacteria. The researchers sterilized the crystal surfaces, cracked them open, extracted the brine, and cultured it. Within weeks, bacteria began growing. DNA analysis suggested these were ancient strains, related to modern halophilic, salt-loving bacteria, but distinct enough to suggest long evolutionary separation. If the bacteria truly were 250 million years old, it would be the oldest viable organism ever revived. Skepticism was immediate and warranted. How could bacteria survive that long? DNA degrades over time, broken by radiation, chemical reactions, thermal fluctuations. Proteins denature, cell structures collapse. The longest confirmed survival times for bacteria in dormancy were thousands of years, not hundreds of millions. Could these bacteria really have waited through the rise of the dinosaurs, their extinction, the emergence of mammals, the evolution of humans, all while locked in a crystal? Critics proposed alternative explanations. Contamination, modern bacteria introduced during sampling or handling, or younger intrusions, bacteria entering the crystals through cracks or pores, sometime in the recent past, not during the Permian. Proving that the bacteria are genuinely ancient requires ruling out these alternatives, which is difficult. You'd need to show the fluid inclusions are sealed, that the crystal surfaces are intact, that sterilization procedures were foolproof. Some researchers remain unconvinced, though others have reported similar results with ancient salt deposits from different locations and ages. Assuming some of these bacteria are genuinely ancient, perhaps not 250 million years, but millions nonetheless, how did they survive? The leading hypothesis is extreme dormancy, combined with unique environmental conditions. Salt crystals are dry, which inhibits biological activity and many chemical reactions. The bacteria might have entered a state of near-complete metabolic arrest, repairing DNA damage just fast enough to keep up with decay, using energy stored in their cells or possibly absorbed from the environment. Radiation exposure would be minimal deep underground, shielded by rock. But even with these advantages, millions of years is an extraordinary timescale. DNA repair rates would need to be exquisitely balanced, too slow, and the genome degrades irreversibly. Too fast, and energy reserves deplete. The bacteria would essentially be poised on the edge of viability, metabolizing just enough to maintain integrity, never truly alive in the sense of growing or reproducing, but never quite dead either. This raises philosophical questions about the boundary between life and death. We usually define life by activity: metabolism, growth, reproduction, response to stimuli. But bacteria in extreme dormancy exhibit none of these. They're static, preserved, waiting. Are they alive? Or are they biological structures that retain the potential for life, like seeds or spores, but aren't themselves living until conditions permit activity? Some researchers prefer terms like biostasis or cryptobiosis, suspended animation, life paused. The bacteria aren't dead because they can be revived, but they're not alive in the usual sense either, because they're not doing anything. They exist in a liminal state, neither fully one nor the other, challenging our neat categories. And there are implications for astrobiology. If bacteria can survive millions of years in salt crystals on Earth, could they survive similar timescales in space? Panspermia, the idea that life can spread between planets on meteorites, becomes more plausible if organisms can endure the journey. A rock ejected from Mars by an impact, carrying bacteria in salt or ice deposits, could travel through space for millions of years and arrive at Earth with viable organisms. Life could be transferred between worlds, seeding planets across the galaxy or beyond. It also suggests that places we consider inhospitable might harbor dormant life. Mars has ancient salt deposits, subsurface ice, stable underground environments. If Martian life ever existed, could it still be there, dormant, waiting in deposits billions of years old? Europa, Enceladus, other icy moons with subsurface oceans. Could life persist there in dormant states during long periods of unfavorable conditions? On Earth, these ancient bacteria, if genuine, are windows into deep time, survivors from eras before humans, before mammals, before most of the species that now populate the planet. They're living fossils, in the truest sense, organisms that bridged epochs, that outlasted countless other lineages, not through active survival, but through patient waiting. And now, revived, they grow in modern laboratories, anachronisms culturing alongside their distant descendants, 250 million years collapsing into petri dishes. Whether the most extreme claims are confirmed or not, the principle is established. Life can wait. It can endure unimaginable spans of time, dormant but not dead, preserved in unlikely refuges, ready to resume when conditions permit. And that's a form of resilience beyond anything we usually imagine. Not toughness in the face of immediate threats, but patience across eons. Existence stretched so thin it almost vanishes, yet never quite breaking. Here's a cosmological pattern that seems too strange to be coincidence, but too specific to explain. The axis of evil in the cosmic microwave background shows unexpected alignments that seem to point toward Earth's location. These patterns shouldn't exist in a truly random universe, suggesting either a cosmic conspiracy or flaws in our cosmological models. The cosmic microwave background, CMB, is the afterglow of the Big Bang, radiation from about 380,000 years after the universe began, when the cosmos cooled enough for atoms to form and light to travel freely. This radiation fills the universe, coming from all directions, and it's remarkably uniform. The temperature variations are only a few parts per million. But those tiny variations are incredibly important. They reveal the density fluctuations that eventually grew into galaxies, clusters, and the large-scale structure we see today. Cosmologists analyze the CMB by decomposing the temperature map into spherical harmonics, mathematical functions that describe patterns on a sphere. Different harmonics correspond to different angular scales: small-scale ripples, medium-scale patches, large-scale variations. The amplitude of each harmonic tells you how strong that scale of fluctuation is, and together they form the power spectrum of the CMB, which cosmological models predict with impressive accuracy. But when researchers looked at the largest scale harmonics, the quadrupole and octupole, describing the broadest temperature variations across the sky, they found something odd. These scales aren't oriented randomly as you'd expect. Instead, they show alignments with each other and, disturbingly, with features of our solar system. The ecliptic plane, the direction of Earth's motion through space, even the orientation of the solar system within the galaxy. This collection of alignments has been dubbed the axis of evil, a tongue-in-cheek name referencing both the unexpected nature of the patterns and their disturbing implications. If the CMB fluctuations were truly primordial and random, there should be no preferred direction in the universe, no alignments with structures billions of years younger, like our solar system. The probability of such alignments occurring by chance is low, not impossibly low, but low enough to be suspicious. Several explanations have been proposed. The most mundane is foreground contamination. Our view of the CMB is obscured by emissions from our galaxy, from dust and gas and stars between us and the ancient light. Maybe the alignments are artifacts of how we subtract these foreground emissions, patterns introduced by imperfect data processing. But researchers have tried multiple foreground subtraction methods, and the alignments persist. Another possibility is statistical fluke. With enough patterns to look for, you'll eventually find some that seem meaningful by chance. The look elsewhere effect, the problem of multiple comparisons, means that unlikely events become likely if you search widely enough. Maybe the axis of evil is a case of humans finding patterns in noise, seeing significance in coincidence. But the consistency across different analyses and data sets makes this explanation less satisfying. More exotic possibilities venture into new physics. Maybe the universe isn't entirely isotropic. Maybe there's a preferred direction baked into the cosmos, a remnant of some earlier phase or some topological feature of space-time. Maybe we're seeing the signature of a universe with non-trivial topology. Perhaps space wraps around on itself in some way, creating correlations in the CMB that happen to align with our local reference frame. Maybe there's a failure in the standard cosmological model, some assumption that doesn't hold at the largest scales. Or maybe, and this is the most unsettling thought, we're special in some way. Not because we're the center of the universe, but because something about our location or reference frame happens to correlate with large-scale cosmic structures. This would be deeply uncomfortable, echoing the pre-Copernican view that Earth occupies a special place. Modern cosmology is built on the cosmological principle, the assumption that the universe is homogeneous and isotropic, the same everywhere and in every direction. If Earth or the solar system has some special alignment with cosmic structures, it challenges that principle. Most cosmologists lean toward mundane explanations, foreground contamination, statistical artifacts, or perhaps a combination of small systematic errors that happen to align. The axis of evil might be a cautionary tale about the challenges of analyzing data with subtle systematics, not a genuine feature of the cosmos, but until it's definitively explained, it lingers in the literature, a small thorn in the side of the standard cosmological model. And there's something philosophically interesting about it. The idea that the universe's largest scale patterns might align with our tiny local reference frame feels wrong, violates our intuition about our cosmic insignificance. We're supposed to be specks, living on an ordinary planet around an ordinary star in an ordinary galaxy. The universe isn't supposed to care about our orientation, our motion, our location. And yet, if the axis of evil is real, the cosmos seems to be nodding in our direction, aligning its largest structures with our little solar system. It's probably coincidence, probably artifact, but the possibility that it's something more, something we don't understand about the universe's geometry or our place within it, is tantalizing and unsettling in equal measure. Let's turn to a phenomenon at the boundary between sleep and waking, where consciousness operates under strange constraints. Some people experience sleep paralysis, accompanied by a sensation of a malevolent presence, a phenomenon reported consistently across cultures. Your brain is awake, but your body remains in REM atonia, and the fear response activates, creating hallucinations of intruders or demons. Sleep paralysis occurs during transitions between sleep and waking. During REM sleep, the phase where most dreaming occurs, your brain paralyzes your body to prevent you from acting out dreams. This atonia is a protective mechanism. Without it, you'd physically move during dreams, potentially injuring yourself. But sometimes the transition isn't clean. You wake up, consciousness returns, but the paralysis persists. You're aware, lying in bed, unable to move or speak. And for some, this is accompanied by overwhelming fear and vivid hallucinations. The hallucinations are remarkably consistent across cultures and time periods. People report sensing a presence in the room, something malevolent, watching, approaching. They feel pressure on their chest, as if something is sitting on them, making it hard to breathe. They see shadow figures, demons, aliens, intruders, entities that feel intensely real, more real than dreams, present in the actual room. The experiences are terrifying, often described as the most frightening thing people have ever experienced. Why does this happen? Sleep paralysis itself is well understood. It's the persistence of REM atonia after consciousness returns. But the hallucinations are more complex. The brain is in a hybrid state, partially in REM, which is why you can't move, partially awake, which is why you're conscious. This hybrid state might create confusion in sensory processing and threat detection systems. One hypothesis involves the brain's attempt to explain the paralysis. Your motor cortex is trying to move your body, but the body isn't responding. This disconnect creates a sense that something external is restraining you. Your amygdala, the fear center, activates in response to the strange, threatening situation. And your brain, trying to make sense of the fear and paralysis, constructs an explanation. There's something here, something holding you down, something dangerous. The specific form of the hallucinations, intruders, demons, shadow figures, might be culturally shaped. In medieval Europe, people experiencing sleep paralysis reported encounters with witches or incubi. In Newfoundland, the old hag sits on your chest. In Japan, it's kanashibari, being bound by invisible metal. Modern reports often involve aliens, possibly influenced by popular culture. The underlying experience is universal, but the narrative your brain constructs to explain it draws on cultural frameworks. The sensation of presence is particularly interesting. Even without visual hallucinations, people report feeling that someone or something is in the room nearby, often behind them where they can't see. This might involve brain regions that normally detect and track other agents. Mirror neurons, theory of mind, networks. In the hybrid state of sleep paralysis, these systems might activate spontaneously, creating the perception of another being without any actual sensory input. Sleep paralysis is more common than most people realize. Estimates suggest 8% to 50% of people experience it at least once in their lives, with higher rates among students, shift workers, and people with disrupted sleep schedules. It's associated with sleep deprivation, irregular sleep patterns, sleeping in supine position on your back, and stress. People with narcolepsy experience it more frequently. For most, sleep paralysis is occasional and harmless, if deeply unpleasant. Learning what it is helps. Understanding that the presence isn't real, that the paralysis will end, that you're not in danger. Some people learn to recognize the state and wait it out calmly. Others develop techniques to break the paralysis, focusing on moving a single finger or toe, controlling their breathing, trying to fully relax rather than fighting it. But for some, recurrent sleep paralysis becomes distressing, disrupting sleep and causing anxiety about going to bed. In such cases, addressing underlying sleep issues, getting regular sleep, treating sleep disorders, managing stress, can reduce episodes. And there's a cultural angle. In societies where sleep paralysis is understood as a medical phenomenon, people might be frightened, but don't usually interpret it as supernatural. In cultures where spirits and demons are salient cultural concepts, the experience might be interpreted as genuine possession or haunting, potentially leading to religious interventions, exorcisms, or persistent fear. The same neurological phenomenon, filtered through different belief systems, produces different narratives and different outcomes. Sleep paralysis also offers insights into consciousness. It shows that consciousness and bodily control are dissociable. You can be fully aware while unable to move, trapped in a body that won't respond. It reveals how fear and sensory confusion can create vivid, compelling hallucinations. It demonstrates the brain's tendency to construct narratives, to explain anomalous experiences by inventing agents and threats. For the person experiencing it, sleep paralysis is visceral and terrifying, lying helpless, sensing something malevolent, struggling against a body that won't obey. The knowledge that it's a neurological quirk doesn't entirely diminish the terror in the moment, but afterward, understanding helps. The demon wasn't real. The intruder didn't exist. It was your brain, caught between sleep and waking, constructing threats from confusion and fear. And you survived, as you always will, because sleep paralysis always ends. The atonia lifts, and the presence, which was never there, vanishes with the return of full wakefulness. Let's begin this section with something that borders on the mystical, yet appears to have a scientific basis. Some crystals grow faster when exposed to certain types of music, suggesting vibrational patterns influence molecular organization. Specific frequencies appear to optimize crystal formation, hinting at deeper connections between sound, structure, and growth. The research is preliminary and somewhat controversial, but multiple studies have reported effects of sound on crystal formation. When solutions of various salts, potassium chromate, copper sulfate, others, are exposed to different sound frequencies or music while crystallizing, some frequencies appear to accelerate growth, change crystal size distribution, or alter morphology. The effects are subtle, not dramatic, but consistent enough across different experiments to suggest something real might be happening. The proposed mechanism involves resonance and vibration. Sound waves propagate through liquids as pressure waves, creating oscillations in the solution. At certain frequencies, these oscillations might interact with the crystal lattice or the solution dynamics in ways that affect how molecules attach to the growing crystal. Perhaps vibrations help orient molecules, shake off impurities, reduce surface tension, or influence convection patterns that deliver material to the growing crystal face. Classical music, particularly compositions with complex harmonic structures, has been reported to accelerate growth more than simple tones or silence. Rock music or atonal sounds sometimes show neutral or negative effects. This frequency dependence suggests the effect isn't just about acoustic energy, but about specific vibrational patterns interacting with the physical chemistry of crystallization. Similar effects have been observed in plant growth. Some studies report plants exposed to certain music or sound frequencies grow faster or produce more biomass, though results are mixed and controversial. If real, the mechanisms might overlap. Vibrations affecting cellular processes, nutrient transport, gene expression. But plants are complex living systems. Crystals are simpler, and effects in crystals might be more about straightforward physics. Acoustic energy influencing molecular motion and organization. Skepticism is warranted. Crystallization is sensitive to many environmental factors: temperature, humidity, container shape, vibration from external sources. Isolating the specific effect of intentional sound from background vibrations, thermal fluctuations, and other variables is challenging. Some studies might suffer from confirmation bias, inadequate controls, or statistical anomalies. The field needs more rigorous experiments, replication, and mechanistic understanding before sound-enhanced crystallization becomes accepted science. But if the effect is real, it would have practical implications. Industrial crystallization processes, pharmaceuticals, materials synthesis, food processing could potentially be optimized by applying specific sound frequencies. Crystals with desired size distributions or morphologies could be produced more efficiently. It's speculative, but not absurd. Acoustic energy is already used in some industrial processes like ultrasonic cleaning or sonochemistry, where high-frequency sound drives chemical reactions. And there's a deeper question: how sensitive is matter to vibrational information? Sound is mechanical energy propagating through media, but at a molecular level, its periodic changes in pressure, density, and molecular motion. If these changes can influence crystallization, what else might they affect? We know proteins fold in response to thermal vibrations, that enzymes have vibrational modes important for catalysis, that quantum effects in biology might involve vibrations. The universe is vibrating at all scales, from quantum field fluctuations to acoustic waves to seismic tremors. Matter is always in motion, always responding to vibrations. Perhaps sound-enhanced crystallization is a window into that responsiveness, a demonstration that organized vibrations can guide matter into organized structures. Or perhaps it's artifact, coincidence, wishful thinking. The experiments need replication, the mechanisms need elucidation. The effects need to be robust and reliable before conclusions can be drawn. But it's an intriguing edge case, a place where science brushes against folklore. People have claimed for centuries that singing to plants helps them grow, that certain sounds have mystical properties. Usually, such claims are dismissed as superstition, but occasionally, folklore contains kernels of truth, observations of real phenomena lacking scientific framework. And maybe, just maybe, the idea that sound influences matter has some basis, some physical reality buried beneath layers of exaggeration and misunderstanding. For now, crystals growing in laboratories while music plays are a footnote, a curiosity. But science thrives on curiosities, on anomalies that don't quite fit, on questions at the edge of knowledge. And if you're going to grow crystals, you might as well play them some Beethoven. It probably won't hurt, and who knows? Maybe the universe resonates in ways we haven't fully discovered, responding to vibrations, organizing itself in patterns shaped by frequencies, dancing to rhythms we're only beginning to understand. Here's a phenomenon that violates basic thermodynamics intuitions, yet has been verified for decades. The sun's corona is hundreds of times hotter than its surface, violating the normal laws of heat transfer in ways we still can't fully explain. Something, possibly magnetic reconnection, heats the outer atmosphere to millions of degrees, while the visible surface sits at a mere 500 degrees C. This is the coronal heating problem, and it's been puzzling astrophysicists since the corona's temperature was first measured in the 1930s and 1940s. The photosphere, the sun's visible surface, has a temperature of about 5,500 degrees Celsius. Move outward into the chromosphere and corona, and temperatures rise dramatically. The corona, the outermost layer visible during solar eclipses as a faint halo around the sun, reaches temperatures of 1 to 3 million degrees Celsius. This seems impossible. Heat normally flows from hot to cold. How can the outer layers be hotter than the inner layers when there's no heat source out there? It's like standing near a campfire and finding that the air far from the flames is hotter than the air close to them. It violates our thermodynamic intuition. The answer is that heat isn't simply flowing outward. Energy is being deposited in the corona by non-thermal mechanisms, processes other than straightforward radiative or conductive heat transfer. The leading candidates involve the sun's magnetic field, which is complex, dynamic, and filled with stored energy. Magnetic reconnection is one mechanism. The sun's magnetic field lines are twisted and tangled by the turbulent motions of plasma in the sun's interior. When field lines with opposite polarity come close together, they can reconnect, snapping into new configurations and releasing energy in the process, similar to how a twisted rubber band suddenly releases tension. This energy heats the surrounding plasma, potentially raising temperatures to coronal levels. Another possibility is wave heating. Magnetic waves, Alfvén waves, and other magnetohydrodynamic oscillations can propagate from the sun's interior through the photosphere into the corona. When these waves dissipate, they deposit their energy as heat. Observations have detected waves in the corona, but whether they carry enough energy to account for coronal heating is still debated. There's also nanoflare heating, countless small magnetic explosions constantly occurring throughout the corona, each releasing a tiny amount of energy, but collectively adding up to significant heating. These nanoflares would be too small and too numerous to observe individually, but they'd create a statistical background of energy release that keeps the corona hot. The challenge is that the corona is difficult to observe and model. It's tenuous, much less dense than the photosphere, and extremely hot, emitting primarily in extreme ultraviolet and X-ray wavelengths that are absorbed by Earth's atmosphere. Space-based observatories have provided detailed observations showing the corona is structured by magnetic fields filled with loops and plumes and dynamic activity. But capturing the detailed physics of how energy is transported and deposited remains challenging. The Parker Solar Probe, launched in 2018, is designed to fly through the corona, measuring the plasma and magnetic field properties in situ for the first time. Its observations are already providing new insights into wave activity, magnetic reconnection, and plasma dynamics in the inner corona. But fully solving the coronal heating problem will require integrating these observations with sophisticated models of magnetohydrodynamics, plasma physics, and radiative transfer. And there's a practical dimension. Understanding coronal heating is essential for predicting space weather. The corona is the source of the solar wind, the stream of charged particles flowing outward from the sun. Coronal mass ejections, massive eruptions of plasma and magnetic field, originate in the corona and can impact Earth, disrupting satellites, power grids, and communication systems. Understanding what drives coronal dynamics, how energy is released, how the corona is structured and heated, all feed into our ability to forecast solar activity and its effects on our technological civilization. But beyond applications, the coronal heating problem is fundamentally about physics. It challenges us to understand energy transport in extreme environments. Low density, highly ionized plasmas threaded with magnetic fields, governed by equations we can write but struggle to solve. It's a laboratory we can't reproduce on Earth, a natural experiment occurring right in our cosmic backyard, revealing processes that happen throughout the universe wherever stars shine and magnetic fields coil. The sun, in a sense, is refusing to behave simply. Its surface glows at 500 degrees, but its atmosphere roars at millions. The disconnect reminds us that nature doesn't follow the simplified models we first learn. Reality is layered, complex, full of mechanisms we didn't anticipate. And the sun, so familiar, so constant, still holds mysteries. It's been burning for 4.6 billion years, and we're still learning how it works, still puzzled by its outer atmosphere, still seeking to understand why the corona burns so much hotter than the surface beneath it. Let's venture into cosmology and the question of why the universe seems calibrated for complexity. The universe's fine-tuning problem shows that if fundamental constants varied even slightly, life couldn't exist, but we don't know why they have these exact values. The strength of gravity, the mass of electrons, and dozens of other values seem precisely calibrated for complexity to emerge. Consider gravity. If the gravitational constant were slightly larger, stars would burn faster and hotter, exhausting their fuel in millions rather than billions of years. Planets wouldn't have time for life to evolve. If gravity were slightly weaker, stars might not ignite at all. Gas clouds would disperse without collapsing, and the universe would be dark and cold. No fusion, no elements heavier than hydrogen and helium. Or consider the electromagnetic force. If it were slightly stronger, electrons would be bound too tightly to atoms, making chemistry sluggish or impossible. If it were slightly weaker, atoms wouldn't hold together. No molecules, no chemistry, no life. The strong nuclear force binds protons and neutrons in atomic nuclei. If it were a bit weaker, nuclei would fall apart. Only hydrogen would be stable, and complex elements couldn't exist. If it were a bit stronger, protons would bind too easily. Hydrogen might be converted into heavier elements too efficiently during the Big Bang, leaving no hydrogen for stars or water. The list goes on. The mass ratio of electrons to protons, the strength of the weak nuclear force, the cosmological constant, the initial density fluctuations in the early universe. All of these have values that fall within narrow ranges compatible with life. Change any one of them significantly, and you get a universe that's sterile, either too simple, just hydrogen, no stars, or too chaotic, black holes everywhere, no stable structures, or too short-lived, collapses in a big crunch before stars form, or too diffuse, expands so fast galaxies never coalesce. This is the fine-tuning problem. Why do these constants have the values they do? Why are they in the narrow ranges that permit complexity, chemistry, life? One response is the anthropic principle. We observe these values because we couldn't exist otherwise. If the constants were different, no observers would arise to notice. It's a selection effect. We necessarily find ourselves in a universe compatible with our existence. This doesn't explain why the constants have their values, but it explains why we observe them. In an ensemble of universes with different constants, observers only arise in the subset where conditions permit. The multiverse takes this further. If there are many universes, either from eternal inflation, quantum many worlds, or string theory's landscape of possible vacuum states, each with different physical constants, then our universe is one among countless others. Most are sterile, but a few are life-permitting, and we're in one of the latter by necessity. The multiverse makes fine-tuning a statistical inevitability rather than a cosmic mystery. Critics argue the multiverse is unfalsifiable. If other universes are causally disconnected from ours, we can never observe them, so the hypothesis can't be tested. Advocates counter that it's a natural consequence of some well-motivated theories, and the fine-tuning problem is real enough to demand explanation. Another possibility is that the constants aren't arbitrary. They're determined by deeper principles we haven't discovered yet. Maybe there's a deeper theory, a theory of everything, where the constants emerge naturally from mathematical consistency or symmetry requirements. String theory aims to be such a theory, but so far it predicts a vast landscape of possible solutions, not a unique set of constants. We haven't found the principle that selects our universe's constants over others. Or perhaps we're wrong about the fine-tuning. Maybe the ranges aren't as narrow as we think. Maybe life could arise with different constants, in forms we don't recognize. We only know one kind of life, Earth's carbon water-based biochemistry, and we extrapolate that all life must be similar. But maybe there are forms of complexity, even consciousness, that could emerge in very different physical regimes. This is speculative, but it challenges the assumption that our specific physical laws are the only ones compatible with complexity. And there's a theological angle. Some interpret fine-tuning as evidence for design, for a creator who set the constants to permit life. This moves beyond science into philosophy and theology, domains where empirical evidence gives way to interpretation and belief. Science can describe the fine-tuning but can't definitively explain it without venturing into speculative theories like the multiverse or undiscovered principles. The fine-tuning problem sits uncomfortably at the intersection of physics, philosophy, and existential wonder. It's a reminder that the universe we inhabit is, in some sense, special, not because we're at its center or because it was made for us, but because it permits complexity at all. Slight tweaks to the fundamental constants would render it barren. We exist on a knife edge of possibility, and whether that's coincidence, necessity, design, or selection from a multiverse remains one of the deepest open questions. For now, we can only marvel at the narrowness of the window. Gravity, electromagnetism, nuclear forces, all balanced just so, allowing stars to shine, elements to form, chemistry to complexify, life to emerge. It could have been otherwise, and mostly it is otherwise in the vast space of possible physical laws. But here, in this particular universe, the constants permit complexity, and we, products of that complexity, can contemplate the improbability of our own existence. Here's a recent and hopeful discovery that suggests nature might help us solve a problem we created. Some fungi can break down plastic, potentially offering solutions to pollution. But we don't know how they evolved this ability so quickly. Plastic has only existed for decades, yet nature has already found ways to digest materials that are supposed to last forever. The discovery of plastic-degrading fungi was surprising. Plastics, polymers like polyethylene, polypropylene, polyurethane, are designed to be durable and resistant to degradation. That's their advantage and their curse. They don't rot, don't break down in the environment, persisting for decades or centuries. Plastic pollution accumulates in landfills, oceans, soil, even the atmosphere as microplastics. But in 2011, researchers discovered fungi in the Amazon rainforest that could digest polyurethane, a common plastic used in foams, coatings, and adhesives. The fungus, Pestalozziopsis microspora, produces enzymes that break the polymer bonds, degrading the plastic into simpler compounds the fungus can metabolize. Since then, other plastic-degrading fungi and bacteria have been discovered. Organisms that can digest polyethylene, polystyrene, PET, polyethylene terephthalate, used in bottles. How did these organisms evolve this ability so rapidly? Plastic has only been mass-produced since the mid-20th century, about 70 years, a blink in evolutionary time. Yet, microorganisms have already adapted to exploit it as a food source. Several mechanisms might explain this. First, exaptation. The enzymes these organisms use to break down plastics weren't evolved specifically for that purpose. They were originally adapted to digest other materials. Natural polymers like cellulose, lignin, cutin, suberin, that have chemical structures somewhat similar to synthetic polymers. The enzymes happen to work on plastics as well, perhaps less efficiently, but well enough that organisms with high mutation rates and short generation times could fine-tune the enzymes to improve plastic degradation. Second, horizontal gene transfer, Microorganisms can share genes across species boundaries through plasmids and other mechanisms. If one bacterium or fungus stumbles upon a mutation that improves plastic degradation, that gene can spread through microbial communities rapidly, accelerating adaptation. Third, selective pressure. Plastics are now abundant in the environment. Any organism that can derive energy from them has access to a vast, underutilized resource. This creates strong selection for plastic degrading ability. In environments heavily contaminated with plastic, like landfills, waste sites, or plastic-rich ocean zones, organisms capable of degrading plastic would have a competitive advantage, allowing them to proliferate. The discovery raises hopes for bioremediation, using microorganisms to clean up plastic pollution. Imagine landfills seeded with plastic-degrading fungi and bacteria, accelerating breakdown, or wastewater treatment plants that remove microplastics using biological filters, or ocean cleanup efforts augmented with microbes that digest floating plastic debris. But challenges remain. The degradation rates are slow. These organisms can break down plastic, but not quickly enough to solve pollution problems on their own. Scaling up to industrial or environmental applications requires faster degradation, efficient growth conditions, ensuring the byproducts aren't toxic, and avoiding unintended consequences like releasing greenhouse gases or creating harmful metabolites. There's also the question of whether widespread plastic-degrading microbes could cause problems. If these organisms become ubiquitous, they might start degrading plastic products we want to keep: pipes, packaging, materials in use. We'd need to balance plastic degradation in waste streams with preventing degradation of useful plastics. It's similar to the problem of rust. Microorganisms corrode metal, which is useful when we want to recycle or dispose of metal, but problematic when it degrades infrastructure. Still, the discovery is hopeful. Nature is adaptable. Life finds ways. We created a material that resists natural breakdown, and within decades, evolution responded. It's a testament to biology's inventiveness, the relentless exploration of chemical space by organisms competing for resources. Every molecule is a potential food source if the right enzyme evolves. Plastic, for all its synthetic novelty, is just another organic polymer, and life has billions of years of experience digesting polymers. And there's irony in it. We invented plastic to be permanent, to resist decay, to outlast us. And now, nature is catching up, finding loopholes, evolving solutions to break down what we thought was unbreakable. The plastosphere, the ecosystem of microorganisms colonizing plastic debris in oceans, is a new ecological niche created by human pollution, being exploited by organisms adapting in real time. We're witnessing evolution responding to anthropogenic change, adapting to a world we've altered, turning our waste into resources. It won't solve the plastic problem alone. We still need to reduce production, improve recycling, design biodegradable alternatives. But plastic-degrading fungi and bacteria are tools in the toolkit, natural allies in cleaning up a mess we've made. And they remind us that life is resilient, creative, always finding new ways to exploit available resources, even if those resources are synthetic polymers never before present on Earth. Evolution works fast when the pressure is strong, and we've provided plenty of pressure by filling the environment with a novel food source. Now, we watch as nature adapts, learning to eat our leftovers, slowly reclaiming a world we've covered in plastic. Here's a phenomenon that sits at the intersection of neuroscience and the subjective nature of reality. The God helmet can induce mystical experiences through magnetic stimulation of temporal lobes, blurring the line between neurology and spirituality. People report sensing presences, cosmic unity, and even divine encounters when specific brain regions are activated artificially. The device was developed by neuroscientist Michael Persinger in the 1980s. It's essentially a modified motorcycle helmet equipped with magnetic coils that deliver weak, complex magnetic fields to specific regions of the brain, particularly the temporal lobes. Subjects wearing the helmet for 20-40 minutes often report unusual experiences, sensing a presence in the room, feeling a profound sense of meaning or unity with the universe, perceiving lights or patterns, sometimes interpreting the experience in religious or spiritual terms. Persinger's research suggested that these experiences result from stimulating brain regions associated with self-perception and spatial awareness. The temporal lobes, particularly the right hemisphere, are involved in constructing the sense of self and distinguishing self from other. When disrupted or stimulated in unusual ways, they might create the perception of another presence, a sensed other, felt as external but generated internally. The experiences vary by individual. Some report sensing God, angels, or spirits. Others describe alien presences or deceased relatives. Still others just feel a vague sense of something nearby. Atheists and religious believers both report experiences, though they interpret them differently. Believers might see confirmation of spiritual realities. Atheists might view it as interesting but purely neurological. Critics have raised questions about the God helmet's reliability. Some replication attempts have failed to produce consistent results, suggesting the effects might be influenced by suggestion, expectation, or other psychological factors, rather than the magnetic fields themselves. The magnetic fields used are weak, similar in strength to what you'd experience near household electronics, and it's unclear they can penetrate deeply enough to affect brain function significantly. But Persinger's work, even if not fully replicated, points to a deeper truth. Mystical experiences have neural correlates. Temporal lobe epilepsy patients sometimes report intense spiritual or religious experiences during seizures. Brain imaging studies show that meditative states, religious experiences, and feelings of transcendence involve specific patterns of activity in temporal lobes, parietal lobes, and frontal cortex. The sense of self, the feeling of unity with something larger, the perception of presence. All of these have neural substrates. This raises unsettling questions for those who interpret mystical experiences as evidence of spiritual realities. If magnetic stimulation or seizures can produce experiences indistinguishable from genuine religious encounters, what does that say about the nature of those encounters? Are they revealing external spiritual truths, or are they internal brain states misinterpreted as external? One perspective is reductionist. All mystical experiences are brain activity, products of neurology, no external entities involved. When someone feels the presence of God, they're experiencing a specific pattern of neural firing, nothing more. This doesn't diminish the subjective power of the experience, but it locates the cause inside the brain, not outside. Another perspective is that the brain is the interface through which we experience reality, spiritual or otherwise. If mystical experiences involve temporal lobe activity, that doesn't mean they're illusions. It might mean that's how the brain processes spiritual realities. Just as visual experiences involve activity in visual cortex, but we don't conclude that visual perceptions are illusions. Perhaps mystical experiences involve temporal lobes, because that's the neural machinery for sensing spiritual dimensions. This is ultimately unfalsifiable. Neuroscience can describe the neural correlates of mystical experiences, but it can't definitively say whether those experiences correspond to external realities or are purely internal phenomena. The God helmet doesn't solve this. It just demonstrates that mystical experiences can be artificially induced, which is consistent with both interpretations. And there's a phenomenological point. For the person having the experience, it's real, meaningful, often life-changing. Whether induced by meditation, prayer, psychedelics, seizures, or magnetic stimulation, the subjective quality is similar. People describe profound realizations, encounters with the sacred, transformations of perspective. The brain might be the source, but the experience is genuine in its effects on the person. The God helmet is controversial, its effects debated, its replications inconsistent. But it's a window into how fragile and constructed our sense of self and reality is. A weak magnetic field, flickering across temporal lobes, might be enough to make you feel you're not alone, that something is watching, that the universe contains presences beyond the physical. And whether those presences are neurons misfiring or genuine encounters with the numinous, the question reveals how deeply subjective experience is tied to brain function, how thin the line between neurology and spirituality, how much of what we experience as real is constructed by the 3 pounds of tissue inside our skulls. Here's a phenomenon that reveals how transparent the universe is to certain particles. Neutrinos from the sun are passing through your body right now, trillions per second, without interacting with a single atom. These ghost particles could fly through light years of solid lead without slowing down, carrying information from the sun's core. Neutrinos are fundamental particles, products of nuclear reactions. In the sun's core, hydrogen fuses into helium, releasing energy as light and neutrinos. The light takes thousands of years to diffuse from the core to the surface. Photons are constantly absorbed and re-emitted by atoms, scattering through the dense plasma in a random walk. But neutrinos interact so weakly with matter that they escape the sun immediately, streaming outward at nearly the speed of light. 8 minutes later, they reach Earth, about 65 billion neutrinos per square centimeter per second, passing through you as you read this, but you don't notice. Neutrinos barely interact with ordinary matter. A neutrino can pass through an entire planet, even a star, with only a tiny probability of hitting an atom. They're called ghost particles because they slip through matter as if it's not there. Detecting neutrinos requires enormous volumes of detector material and extraordinary sensitivity. Early neutrino detectors used tanks containing hundreds of tons of water or cleaning fluid, buried deep underground to shield from cosmic rays. Even then, they detect only a handful of neutrinos per day. Modern detectors are even larger. IceCube in Antarctica uses a cubic kilometer of ice as a detector, looking for the rare flashes of light produced when a neutrino interacts with an atom in the ice. Why detect them if they're so elusive? Because neutrinos carry unique information. Since they escape the sun's core immediately, they provide a real-time snapshot of fusion reactions happening right now. Light from the sun shows us conditions from thousands of years ago when that light was generated. Neutrinos show us now, and neutrinos confirmed our understanding of solar fusion. In the 1960s, the first solar neutrino detector found only about a third of the expected neutrinos, the solar neutrino problem. For decades, this was a mystery. Were our models of the sun wrong? Or was something happening to neutrinos on their way to Earth? The solution was neutrino oscillations. Neutrinos come in three types: electron, muon, tau. The sun produces electron neutrinos, but as they travel, they oscillate between types. The early detectors were only sensitive to electron neutrinos, so they missed the muon and tau neutrinos that the electron neutrinos had transformed into. Once detectors capable of detecting all three types were built, the missing neutrinos were found. The sun was fine. Neutrinos were just more interesting than expected. Neutrino oscillations imply neutrinos have mass, tiny but non-zero. This was a major discovery, earning the Nobel Prize, because the Standard Model originally predicted massless neutrinos. The fact that they have mass suggests physics beyond the Standard Model, new mechanisms for generating mass, possibly connections to dark matter or the matter-antimatter asymmetry. Neutrinos also come from supernovae, from cosmic rays colliding with the atmosphere, from nuclear reactors, from particle accelerators, from the Big Bang itself. The cosmic neutrino background, relic neutrinos from the early universe, fills space, though they're too low energy to detect with current technology. If we could detect them, they'd provide a snapshot of the universe 380,000 years earlier than the cosmic microwave background, a deeper look into the universe's infancy. And neutrinos might be Majorana fermions, their own antiparticles, as we discussed earlier, which would have profound implications for particle physics and cosmology. Experiments search for neutrinoless double beta decay to test this, but results are inconclusive. For now, neutrinos remain mysterious, ghostly messengers from the heart of the sun, from distant supernovae, from the Big Bang. They pass through us constantly, invisible and intangible, barely perturbing the atoms in our bodies. Every second, trillions of them stream through the Earth, emerging on the other side unaffected, continuing their journey into space. They're a reminder that the universe is more than what we see or touch. Most of reality is invisible, passing through us without leaving a trace, known only because we've built detectors sensitive enough to catch the rare interactions, to glimpse the ghost particles, to listen to the whispers they carry from the cores of stars. Here's a geological formation so striking it was initially mistaken for an impact site. The Richat structure in Mauritania forms a perfect 50-kilometer bullseye visible from space, originally mistaken for an impact crater. Now believed to be a symmetrically eroded dome, it's been speculatively linked to Atlantis, showing how geology can fuel mythology. The Richat structure, also called the Eye of the Sahara, is a circular feature in the Sahara Desert, concentric rings of ridges and valleys forming a bullseye pattern. From space, it's unmistakable, a perfect circle in an otherwise featureless landscape. Early astronauts used it as a landmark. When it was first photographed from orbit, researchers assumed it was an impact crater, a meteorite strike that created circular shock waves in the rock, similar to craters on the moon. But closer investigation found no evidence of impact. No shock metamorphosed minerals, no meteorite fragments, no central uplift typical of large craters. Instead, the structure is composed of sedimentary and igneous rocks arranged in circular layers. The current interpretation is that it's a deeply eroded geological dome, a circular uplift of rock layers, possibly created by volcanic activity or a rising plume of molten rock that never reached the surface. Over millions of years, erosion has worn down the dome, revealing the concentric layers of different rock types, each eroding at different rates to create the ring pattern. The symmetry is remarkable but not inexplicable. Geological domes often erode into circular patterns, though few are as perfectly circular or as well preserved as Rishat. Its location in the Sahara, where erosion is slow and weathering exposes deep layers, helps. In a wetter climate, vegetation and soil would obscure the structure, but the desert lays it bare. The formation has fueled speculation. In 2018, a documentary suggested Risha might be the location of Atlantis, the mythical island civilization described by Plato. The reasoning: Rishad's circular structure matches Plato's description of Atlantis as concentric rings of water and land. The size is roughly comparable, and it's in North Africa, not far from where some interpretations place Atlantis. This is almost certainly wrong. Risha is far inland, never submerged under ocean. Plato described Atlantis as an island that sank. The structure is geological, not architectural. There are no ruins, no artifacts, no evidence of past civilization. And Plato's account is widely considered allegorical, a philosophical story about hubris and decline, not a historical record. But the Richat Atlantis hypothesis captures imaginations, a perfect example of pareidolia, seeing meaningful patterns in random or natural structures. And geology does fuel mythology. Ancient peoples, encountering strange rock formations, might have interpreted them as works of gods, giants, or lost civilizations. Fossil bones became dragons. Volcanic eruptions became divine wrath. Strange landforms became gateways to other worlds. Rishat, had it been discovered by a pre-scientific culture, would certainly have inspired myths. A perfect circle in the desert, visible from mountains or high ground, unexplainable without geological knowledge. What god drew this eye? What power shaped the land so precisely? Even today, with geology to explain it, Rishat retains a mystique. It's beautiful, striking, improbably symmetrical. Visiting it, standing in the rings, feeling the scale, seeing the patterns up close, is to confront the power of geological processes, the slow sculpting of landscapes over millions of years. The Eye of the Sahara is a monument to erosion, a testament to how natural forces can create forms that look intentional, designed, meaningful. And maybe that's the lesson. Nature doesn't need intelligence to create order. Physics, chemistry, geology, these follow laws. And those laws can produce patterns, symmetries, structures that appear designed but emerge from processes operating mindlessly over time. The universe is full of such patterns: galaxies spiraling, crystals forming geometric shapes, rivers braiding, snowflakes exhibiting symmetry. Risha is just one more, a circular eye in the desert, watching the sky, product of uplift and erosion, beautiful and mysterious, despite or because of its natural origin. Let's return to the mysteries of consciousness and its boundaries. Some people experience terminal lucidity, suddenly regaining clarity and communication hours before death, even from severe dementia. These brief resurgences of the person they were suggest consciousness might not be as dependent on brain structure as we assume. Terminal lucidity is rare but documented. A patient with advanced Alzheimer's, uncommunicative for years, suddenly speaks clearly, recognizing family, engaging in conversation, appearing mentally intact. Then, within hours or days, they pass away. It's as if the fog lifts briefly before the end, granting a final moment of clarity, a last goodbye from the person who seemed long gone. The phenomenon has been reported across different causes of cognitive decline: dementia, brain tumors, strokes, mental illness. It's not consistent or predictable, but it happens often enough that medical staff and families recognize it, sometimes interpreting it as a sign that death is near. How is this possible? If dementia involves extensive brain damage, atrophy, plaques, tangles, loss of neurons, how can a brain so degraded suddenly function normally? It challenges the assumption that consciousness depends straightforwardly on brain integrity, that severe brain damage irreversibly destroys mental capacity. Several hypotheses attempt to explain it. One is that consciousness is more resilient than we think, capable of functioning even with damaged substrate under certain conditions. Perhaps dying processes, changes in neurotransmitter levels, metabolic shifts, hormonal releases, temporarily restore some function, allowing remaining neural networks to activate in ways they couldn't before. It's like a failing machine that flickers back to life briefly before shutting down completely. Another idea is that consciousness isn't solely generated by the brain, but is somehow broader, with the brain acting as a filter or interface. If brain damage filters or constrains consciousness, terminal lucidity might represent a lifting of that constraint as the brain's filtering function collapses. This is speculative and leans toward dualist or non-materialist interpretations of consciousness, which are controversial in neuroscience but not entirely dismissed. A simpler explanation is that terminal lucidity involves brief, unsustainable metabolic surges, adrenaline, glucose availability, changes in oxygen or other factors that allow the brain to function better momentarily, at the cost of accelerating decline. It's the brain burning its last reserves, a final flare before the darkness. But none of these explanations is entirely satisfying. The phenomenon remains mysterious, poorly understood, difficult to study because it's unpredictable, and occurs in dying patients where research is ethically and practically challenging. For families, terminal lucidity is a mixed blessing. It offers a final connection, a chance to say goodbye, a glimpse of the person they thought was lost. But it can also be heartbreaking. Why now? Why only at the end? Why couldn't they be present earlier? And sometimes it creates false hope, a belief that recovery is possible, only for the person to decline again and die shortly after. And it raises philosophical questions about personal identity. If consciousness can return briefly after years of absence, was the person still there during the dementia, just unable to express themselves? Or did they genuinely cease to exist as a person, their identity destroyed by brain damage, only to flicker back into existence briefly? These are questions about the nature of self, the relationship between brain and mind, the persistence of identity through neurological change. Terminal lucidity doesn't prove consciousness survives brain death or exists independently of the brain, but it suggests the relationship between brain damage and consciousness is more complex than simple correlation. A brain can be damaged extensively and still, under some circumstances, support moments of clarity. Consciousness might be more flexible, more distributed, more resilient than we assume. For the dying person, what is terminal lucidity like? Do they realize they're dying? Are they aware of having been absent, of time having passed? Do they feel relief, fear, peace? We can't know. Most don't survive to tell us, and those who do are too close to death to provide detailed accounts. It's a subjective experience that remains private, accessible only to the person living it, ending when they end. But for observers, terminal lucidity is a reminder that consciousness is fragile, mysterious, not fully understood. We map brain regions, measure activity, correlate damage with deficits, but the lived experience of being conscious, especially at the edges during transitions in damaged or dying brains, remains elusive. And these moments of unexpected lucidity, these brief returns of the person before the final departure, are windows into that mystery, glimpses of consciousness operating under conditions we thought incompatible with awareness, suggesting that the mind has depths we haven't plumbed, resilience we haven't measured, capacities we've only begun to understand. Let's return to the foundational strangeness of quantum mechanics. The quantum measurement problem questions whether reality exists in a definite state before we observe it, or if measurement creates reality. The universe might be fundamentally probabilistic, crystallizing into actuality only when witnessed, a deeply unsettling possibility. This is the measurement problem, one of the hardest conceptual issues in quantum mechanics. Before measurement, a quantum system is described by a wave function, a mathematical object that encodes probabilities for different outcomes. If you measure an electron's position, the wave function gives you the probability of finding it in different locations. But before measurement, the electron doesn't have a definite position. It's in a superposition. Potentially everywhere, the wave function has non-zero amplitude. When you measure, the wave function collapses to a single outcome. You find the electron at one location, and the probabilities for other locations become zero. The superposition disappears, replaced by definite reality. The problem: what causes collapse? The wave function evolves smoothly and deterministically according to Schrödinger's equation, except during measurements, when it collapses discontinuously and randomly. This is a fundamental asymmetry in the theory: smooth evolution interrupted by sudden collapse. Why? What counts as a measurement? What physically happens during collapse? The Copenhagen interpretation, historically dominant, says quantum mechanics doesn't describe reality itself, but our knowledge of reality. The wave function represents information, and collapse represents updating information when you learn the measurement outcome. This avoids committing to what's really happening, treating quantum mechanics as a tool for predictions rather than a description of underlying reality. The many worlds interpretation says there's no collapse. The wave function evolves smoothly always, but when a measurement occurs, the observer becomes entangled with the system, splitting into multiple branches, one for each possible outcome. In one branch, you measure spin up, in another, spin down. Both outcomes happen, but in different branches of reality. Collapse is an illusion. What you experience is your branch, unaware of the others. De Broglie-Bohm theory, pilot wave, says particles always have definite positions, guided by a wave function that evolves alongside them. The wave creates an effective randomness in particle trajectories that reproduces quantum statistics, but there's no collapse, just particles moving according to deterministic but complex laws. Superposition is epistemic, not ontic. It represents our ignorance of the particle's actual position, not genuine indefiniteness. Objective collapse theories propose that collapse is real and spontaneous, occurring without measurement but triggered by physical processes, perhaps gravitational effects, thresholds of mass or complexity. These theories modify quantum mechanics slightly, adding collapse mechanisms that are negligible for small systems but significant for large ones, explaining why quantum superpositions don't persist in the macroscopic world. Each interpretation has strengths and weaknesses. Copenhagen avoids ontological commitments, but leaves the measurement process vague. What is a measurement? When does it occur? Many worlds avoids collapse but multiplies realities. Is it economical to postulate countless unobservable branches? Pilot wave is deterministic and realist, but introduces non-local hidden variables. Objective collapse makes testable predictions, but lacks a compelling mechanism. The measurement problem matters because it's about the nature of reality. If reality doesn't exist in a definite state until observed, what does that mean? Is the moon there when no one looks? Quantum mechanics suggests that in some sense it's not in a definite state, anyway, until an observation forces it to be. This is profoundly strange. It suggests observation is fundamental, that the universe requires witnesses to crystallize into actuality. It challenges the idea of objective reality existing independently of observers, and it raises the question, what counts as an observer? Does consciousness matter, or is any physical interaction sufficient? Can a photon observe an electron, or does it require something more complex? Most physicists lean toward interpretations where conscious observation isn't special. Any interaction that couples a system to an environment can decohere superpositions, effectively collapsing them. But this doesn't fully solve the problem. It explains why we don't see superpositions in everyday life. Because everything is constantly interacting with environments. But it doesn't explain the fundamental origin of definite outcomes in a theory built on probabilities. The measurement problem is unresolved, and different physicists favor different interpretations based on philosophical preferences, parsimony, or intuition. Experimentally, the interpretations are hard to distinguish. They all make the same predictions for most experiments. A few tests have been proposed to distinguish them, like objective collapse versus many worlds, but results are inconclusive or experiments are infeasible with current technology, so we're left with a theory that works extraordinarily well, predicting phenomena with incredible accuracy, yet harboring at its core a conceptual puzzle about what it all means. Does measurement create reality? Or does it just reveal pre-existing definite properties? Does the universe split into branches or collapse into one? Is there hidden information guiding particles, or is randomness fundamental? These aren't idle questions. They're about the nature of existence, about what the universe is made of, about whether reality is ultimately material or informational, deterministic or probabilistic, singular or multiple. And quantum mechanics, for all its success, doesn't answer them definitively. It leaves us with mystery, with interpretations and possibilities, with the unsettling suggestion that reality might not be as solid as it seems. That observation might play a role we're only beginning to understand. That the universe might be stranger than we can easily comprehend. Let's close this section with a phenomenon that bridges biology and quantum mechanics, showing nature exploiting quantum effects for practical purposes. Migrating birds can sense Earth's magnetic field through quantum processes in their eyes. Navigation through quantum biology. A protein called cryptochrome may use entangled electrons to detect field orientation, making birds living quantum sensors. This is one of the most remarkable proposals in biology, quantum entanglement, that spooky action Einstein doubted, operating inside a bird's eye to help it navigate. The mechanism involves cryptochrome, a light-sensitive protein found in birds' retinas. When blue light hits cryptochrome, it creates a pair of radicals, molecules with unpaired electrons. These electrons are quantum mechanically entangled, their spins correlated. Earth's magnetic field is weak, but it influences the spin states of the entangled electrons, changing the yield of chemical reactions involving the radical pair. Different orientations of the magnetic field produce different chemical outcomes, which the bird's visual system detects. Effectively, the bird sees the magnetic field as a pattern superimposed on its vision, possibly a light or dark spot or a directional indicator. This is quantum biology, quantum effects operating in warm, wet, noisy biological environments where they shouldn't last. Entanglement is fragile, destroyed by environmental interactions within microseconds or less in most contexts. But in cryptochrome, the radical pair might be shielded enough that entanglement lasts long enough, tens of microseconds, to influence chemistry before decoherence erases it. Experimental evidence supports this. Disrupting cryptochrome impairs birds' magnetic sensing. Applying radio frequency fields that should interfere with the quantum states disrupts navigation. The effect is wavelength specific. It depends on blue light, consistent with cryptochrome activation. And the mechanism is theoretically plausible. Physicists have modeled the radical pair mechanism and shown it could provide magnetic sensitivity. But it's not definitively proven. Alternative mechanisms for magnetoreception exist. Some animals use magnetite crystals, tiny magnetic particles, in their tissues to sense fields mechanically. Birds might use both mechanisms or rely primarily on one. Isolating the quantum effect from other biological complexities is challenging. If confirmed, it would be a stunning example of nature harnessing quantum mechanics. Evolution, blind and opportunistic, stumbled upon a way to exploit entanglement for sensing, something human engineers are only now learning to do in controlled labs. Birds evolved quantum sensors millions of years before we understood quantum mechanics existed, and it raises broader questions. How common is quantum biology? Are there other organisms, other processes, where quantum effects play functional roles? Photosynthesis, for instance, might use quantum coherence to transfer energy efficiently between molecules. Controversial but supported by some experiments. Enzyme catalysis might involve quantum tunneling. Olfaction, the sense of smell, might involve quantum effects in detecting molecular vibrations. Quantum biology challenges the assumption that quantum effects wash out at biological scales. Yes, biology is warm and noisy, but life is also highly structured, with molecules arranged precisely, proteins folded specifically, environments controlled tightly. In these specialized contexts, quantum effects might persist long enough to matter, to provide advantages that natural selection can amplify. For the bird, quantum entanglement in its retina is just how vision works. It doesn't know it's a quantum sensor. It just sees the world, including magnetic field patterns, and uses those patterns to navigate. It's a reminder that biology is full of hidden sophistication, mechanisms we're only beginning to understand, solutions to problems we're only now learning to solve with our technology. And it connects the smallest scales, quantum entanglement of electron spins, to the largest, birds migrating across continents, flying thousands of miles guided by Earth's magnetic field. The quantum and the cosmic, linked through biology, through eyes and proteins and chemical reactions, through evolutionary processes that shape sensors without understanding the physics, creating quantum technology millions of years before physicists named it. Let's begin this section with a cosmic phenomenon that reveals the universe's early history written in the structure of the present. The universe's baryon acoustic oscillations, sound waves from the early universe, are frozen in the distribution of galaxies like cosmic fossils. We can read the echo of creation in how galaxies cluster, using sound waves from when the universe was 380,000 years old. In the first few 100,000 years after the Big Bang, the universe was opaque, a hot, dense plasma of electrons, protons, and photons all tightly coupled together. Photons couldn't travel far before scattering off electrons, but this plasma wasn't uniform. Tiny density fluctuations, quantum fluctuations stretched to cosmic scales by inflation, created regions of slightly higher and lower density. In the denser regions, gravity pulled matter inward, but photon pressure pushed outward. The radiation was energetic enough to resist gravitational collapse. This created oscillations, acoustic waves propagating through the plasma at about half the speed of light. These were sound waves, pressure waves, traveling through the primordial universe like ripples in a pond. Then, about 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. The plasma became transparent. Photons decoupled from matter and streamed freely through space, becoming the cosmic microwave background we observe today. The sound waves stopped propagating because the pressure driving them vanished. They froze in place, leaving an imprint on matter distribution. The characteristic scale of these frozen sound waves is about 490 million light-years today, accounting for expansion. Regions of space that were dense peaks in the sound waves when recombination occurred became the seeds for galaxy formation. Today, we see an excess of galaxy pairs separated by that characteristic distance. Galaxies are slightly more likely to be found 490 million light-years apart than at other separations. This is baryon acoustic oscillations, BAO, and it's one of the most powerful tools in cosmology. Because we know the physical size of the sound wave at recombination, we can calculate it from the physics of the early universe. We can use the observed angular size of the BAO feature to measure cosmic distances. It's a standard ruler, similar to how standard candles, objects of known brightness, measure distances. By observing how the BAO scale appears at different redshifts, we can map the expansion history of the universe, measuring dark energy and the geometry of space. The BAO signal has been detected in galaxy surveys. massive projects mapping millions of galaxies across large volumes of space. The pattern is subtle, a small excess at the right separation, but statistically significant and consistent with predictions. It confirms our understanding of the early universe and provides independent verification of the accelerating expansion driven by dark energy. There's something poetic about BAO, sound waves from the universe's infancy, traveling for a few 100,000 years, then frozen for 13 billion years, still visible in how galaxies arrange themselves. The universe's baby cries, echoing down through time, encoded in structure. Every large galaxy survey, every three-dimensional map of cosmic structure, carries this fossil sound, this remnant of acoustic waves that propagated before stars existed, before galaxies formed, when the cosmos was just a plasma symphony conducting itself. And we can decode it. We can measure those ancient sound waves scale, trace how space expanded since they froze, infer the universe's composition and fate. The cosmos keeps records of its own. History, written in patterns of matter, readable by anyone who builds the right instruments and applies the right mathematics. BAO is one such record, a sound wave made visible in light, an acoustic fossil preserved in galaxies, a message from the early universe about its structure and evolution. It's humbling. The arrangement of galaxies, those island universes scattered across billions of light years, isn't random. It bears the imprint of processes from the universe's first moments, frozen echoes guiding where matter accumulated, where galaxies formed, where we are now. Every galaxy cluster, every void, every filament in the cosmic web traces back to quantum fluctuations inflated to cosmic scales and then shaped by acoustic waves in primordial plasma. The universe remembers its origins, and we've learned to read that memory. Here's another variation on synesthesia, this time focusing on the richness of cross-modal experience. Some people experience chromesthesia, a form of synesthesia where sounds automatically trigger seeing colors that others never perceive. For them, a trumpet might be orange, a violin purple, creating a constant internal light show accompanying all auditory experience. We explored this phenomenon earlier, but it's worth emphasizing how fundamental it reveals perception to be. Not a passive reception of sensory data, but an active construction, a weaving together of signals into coherent experience. For chromesthetes, that weaving crosses boundaries most people maintain. Sound doesn't just produce auditory qualia, it produces visual qualia too, automatically, involuntarily. Imagine listening to a symphony and seeing it simultaneously, not synesthetically for most of us, but literally for chromesthetes. Each instrument has a color. Melodies trace colored paths through mental space. Harmonies blend colors like painters mixing pigments. Dissonance might produce clashing, uncomfortable color combinations. The experience is multisensory in a way most people can barely imagine. Some chromesthetes report that music is more emotionally powerful for them because it engages more senses. Others find noisy environments overwhelming. Every sound produces color, creating visual chaos. The car horn is yellow. The dog barking is brown. Voices are swirls of color. It can be beautiful or distracting, depending on context, and it raises questions about the boundaries of sensory experience. If synesthetes can experience sound as color, what other cross-modal combinations are possible? Could someone taste textures, smell shapes, feel time as a physical sensation? Synesthesia suggests the brain's modular architecture, separate systems for different senses, is less rigid than we assume. Sensory streams can merge, creating experiences richer and stranger than the standard configuration. There's also a deeper question. Is synesthetic experience fundamentally different from ordinary experience, or is it just more obvious? Perhaps all perception involves some cross-modal integration. We all experience subtle influences between senses. The McGurk effect shows vision affects hearing. Watching someone mouth ga while hearing ba makes you perceive da, a fusion of visual and auditory input. Synesthesia might be an extreme version of integration that occurs subtly in everyone, and it challenges our understanding of qualia, the subjective qualities of experience. What is it like to be a chromesthete? When they hear a trumpet and see orange, is that orange the same orange they see when looking at an orange object? Or is it a different kind of orange, a synesthetic color that doesn't quite map onto externally perceived colors? Some chromesthetes describe synesthetic colors as having a different quality, internal rather than external, mental rather than physical, but vivid and consistent nonetheless. For non-synesthetes, understanding chromesthesia requires imagination and humility. We can't experience it directly. We can describe it, study it scientifically, even induce temporary versions with drugs or brain stimulation. But the actual subjective experience remains private, accessible only to those who have it. It's a reminder that consciousness is diverse, that people inhabit different experiential worlds, that what seems universal about perception might be just common, not inevitable. And chromesthesia, like other synesthesias, isn't a disorder. It's a variation, a different wiring, often enriching rather than impairing experience. It's neurodiversity in its most literal sense, brains structured differently, producing different experiences, expanding the range of what it means to be human. The chromesthete's world is more colorful than yours, not metaphorically but literally, filled with hues that emerge from sound, painting reality in ways most people never see. Let's venture into one of theoretical physics' most abstract and profound ideas. The holographic principle suggests that our entire universe, with all its three-dimensional complexity, might be encoded as information on a two-dimensional surface at the universe's boundary. Everything you experience, depth, volume, space itself, might be like a hologram, calculated from data on a distant cosmic screen. We explored this concept earlier, but let's go deeper into its implications. If the universe is fundamentally two-dimensional, with three-dimensional experience being a projection or emergent phenomenon, what does that mean for physical law, for causality, for the nature of objects? One implication, entropy. In ordinary three-dimensional thinking, entropy, a measure of disorder or information content, should scale with volume. A box twice as large should hold twice as much information. But for black holes, entropy scales with surface area. The holographic principle generalizes this. The maximum information content of any region of space is proportional to its boundary area, not its volume. The universe's information is fundamentally two-dimensional, with three-dimensional space being a way of organizing that information for certain purposes. This connects to quantum gravity. General relativity describes gravity as curved space-time, inherently three-dimensional, plus time. Quantum field theory describes particles and forces, also in three dimensions. But merging these, quantum gravity, has been notoriously difficult. The holographic principle suggests the problem might be simpler in lower dimensions. Perhaps quantum gravity in 3 dimensions is equivalent to a quantum field theory, without gravity, in 2 dimensions. Solve the simpler problem, and you've solved the harder one. This isn't just speculation. The ADESA CFT correspondence, discovered by Juan Maldacena in 1997, demonstrates this for certain spacetimes. Anti-de Sitter space, ADS, a space-time with negative curvature, in d dimensions is mathematically equivalent to a conformal field theory, CFT, a special kind of quantum field theory, on its d1 dimensional boundary. Everything happening in the bulk space can be described equivalently by physics on the boundary. It's a hologram in a precise mathematical sense. ADS space doesn't match our universe. We live in a universe with positive curvature, or flat, not negative. But the correspondence proves holography can work, that higher dimensional gravity can emerge from lower dimensional quantum mechanics. Researchers are exploring whether similar principles apply to our universe, whether space-time itself is holographic, whether what we perceive as 3-dimensional reality is fundamentally 2-dimensional information arranged cleverly. If true, it would revolutionize physics. Space wouldn't be fundamental, it would be emergent, arising from entanglement and information patterns in the boundary theory. Distance, locality, the very fabric of space-time would be higher-level descriptions of something deeper and more abstract. Asking what happens at this point in space would be like asking, what's the pixel value at this location on a hologram? A meaningful question, but not fundamental. The fundamental question would be about the boundary information encoding that point, and consciousness. If we're holographic projections, does consciousness also reduce to boundary information? Or does it require the 3-dimensional emergent structure? This ventures into speculation, but it's a natural question. If you and all your thoughts are encoded on a 2-dimensional surface, does the subjective experience of being 3-dimensional arise from that encoding? Or is experience itself emergent, layered on top of already emergent space? The holographic principle is mathematically rigorous, but conceptually dizzying. It challenges our most basic intuitions about reality, that space is real, that volume is fundamental, that depth is what it seems. And it suggests the universe is more like a computation, a processing of information, with physical reality being the output, the visible manifestation of underlying informational dynamics. It's not proven to apply to our universe. It remains an active research area, a promising direction, but not a confirmed fact. But even the possibility reshapes how we think about physics. If space is emergent, if the universe is holographic, if information is more fundamental than matter or energy, then reality is stranger than we've imagined, deeper than we've perceived, built on principles that transcend the categories, space, time, matter, we usually take as foundational. And maybe that's the lesson. The universe doesn't owe us intuitive structure. It doesn't have to match our evolved perceptions or our common sense categories. As we probe deeper, quantum mechanics, relativity, holography, we find reality is layered, abstract, mathematical in ways that don't map cleanly onto everyday experience. The universe is what it is, and our job is to understand it on its own terms, even when those terms challenge everything we thought we knew about the nature of existence. Let's return to the microbial world, to organisms that communicate and coordinate in ways we're only beginning to understand. Some bacteria form electrical grids across distances, passing electrons through conductive filaments in what resembles a microbial power grid. These bacterial nanowires allow communities to share energy and coordinate behavior over distances thousands of times their body length. We touched on this earlier, but the implications are worth exploring further. Imagine a city where power lines connect buildings, allowing energy to flow from generators to consumers. Bacteria have created microscopic versions of this, protein filaments stretching across sediments, connecting cells in different locations, allowing electron transfer between them. This isn't just individual cells surviving, it's collective behavior, infrastructure construction, division of labor. Cells near surfaces with electron acceptors, like metal oxides, can respire, using organic matter to generate energy and dumping electrons onto the metal. Cells deep in sediments, far from acceptors, can metabolize but have nowhere to dump electrons. But if they're connected by nanowires to surface cells, they can send electrons through the network, completing their metabolic cycles remotely. It's a division of labor. Surface cells handle waste disposal, electron dumping. Deep cells handle energy extraction, metabolism, and the network connects them. The community functions as an integrated system, more efficient collectively than any individual cell could be alone. And the communication aspect. Electrical signals can propagate through these networks, potentially coordinating behavior across millimeters or centimeters, vast distances for bacteria. A chemical signal sensed by one cell could trigger electrical signals that propagate through the community, causing coordinated responses. Changes in gene expression, metabolic shifts, movement. The network becomes a communication infrastructure, not just an energy conduit. This resembles multicellular organisms, where cells specialize and coordinate, but bacteria are supposed to be single-celled, independent. Yet here they are, forming networks, dividing functions, communicating electrically. It blurs the line between single-celled and multicellular, between individual and collective, and it might be widespread. We've only recently developed tools to detect bacterial nanowires and measure their properties. They've probably been in sediments, soils, biofilms for millions of years, unnoticed. How many other microbial structures and behaviors remain undiscovered because we lack the right perspective or tools? The discovery also suggests new technologies. Microbial fuel cells, bioremediation, biosensors, all could exploit bacterial nanowires. Imagine wastewater treatment plants where bacteria form electrical networks, metabolizing pollutants and generating electricity simultaneously. Or contaminated sites where bacteria degrade toxins deep underground, transferring electrons to surface electrodes we can monitor. Or biosensors using bacterial networks to detect chemicals, with electrical signals reporting their presence. But beyond applications, bacterial nanowires reveal something profound. Life is inventive, collaborative, capable of creating infrastructure and communication networks without brains, without planning, through evolutionary processes that reward any advantage, however small. Bacteria that could transfer electrons farther than competitors had access to more resources, survived better, passed on their genes. Over countless generations, the sculpted nanowires refined their conductivity, integrated them into community behaviors. And it's a reminder that we've barely scratched the surface of microbial life. The bacterial world is vast, diverse, ancient. Bacteria have been evolving for over 3 billion years, adapting to every environment, solving every metabolic challenge. We've cultured and studied a fraction of bacterial species. Most bacteria can't be cultured with standard techniques, remaining unknown or barely characterized. And even known bacteria surprise us with capabilities we didn't expect, like forming electrical grids, like conducting electrons across distances, like cooperating in ways that blur the boundaries of individuality. The microbial world is a frontier, as alien and unexplored as distant planets, and every discovery, like bacterial nanowires, reminds us that life on Earth, even in its smallest, simplest forms, is more complex, more sophisticated, more surprising than we've imagined. Beneath the visible world of plants and animals lies an invisible world of microbes, building networks, exchanging signals, creating ecosystems and chemistries and structures we're only now learning to see. Here's a return to a pattern in human cognition that raises questions about our future. The Flynn effect shows IQ scores have risen consistently worldwide for a century, and we don't fully understand why it might be reversing now. Each generation scored higher than the last, possibly from better nutrition or education, but recent data suggests the rise has stopped or reversed. We discussed this earlier, but it's worth emphasizing the implications. If intelligence, or at least measured intelligence, can rise across entire populations through environmental improvements, it's not fixed by genetics. We have some control over cognitive outcomes through policy, improving nutrition, education, healthcare, reducing environmental toxins. But if intelligence can rise, it can also fall. The reversal observed in some countries is troubling. Are we losing ground? Are modern environments, despite material prosperity, somehow worse for cognitive development than mid-20th century environments? The causes aren't clear, but possibilities include more screen time, less reading. Digital environments might train different cognitive skills, multitasking, rapid information sampling, at the expense of others, sustained attention, deep processing. Changes in education, teaching to tests, reduced emphasis on abstract reasoning. Shifts in curriculum might not develop the same cognitive skills as before. Environmental factors, new pollutants, chemicals, substances we're exposed to might subtly impair development. Or perhaps it's artifact. Testing populations are more diverse. Immigration patterns change demographics. And if different groups start from different baselines, aggregate scores can shift even if individual groups are stable. But studies controlling for demographics still find declines in some places, suggesting real changes in cognitive ability or test-relevant skills. The Flynn effect rising was hopeful. It meant improvement was possible, that human potential wasn't fixed, that we could enhance cognition through better conditions. The reversal is concerning. It suggests we might be getting something wrong, that modern life has hidden costs, that we're not attending to factors that matter for cognitive development. And there's a broader question. What is intelligence, really? IQ tests measure specific abilities, abstract reasoning, pattern recognition, verbal comprehension, spatial manipulation. But intelligence is multifaceted. Emotional intelligence, social skills, creativity, practical problem solving, tacit knowledge, These aren't captured by IQ. If IQ is declining while other forms of intelligence are rising, what's the net effect? We don't know. We lack comprehensive measures of all cognitive abilities across time. We have IQ scores, which are useful but incomplete. So the Flynn effect and its reversal are signals. Something is changing in human cognition, but we don't have the full picture. What's clear is that cognition is malleable, shaped by environment, culture, technology, nutrition, education. We're not passive recipients of genetic endowments. We're active participants in our cognitive development, individually and societally. Decisions about how we structure education, how we design environments, what we expose children to, all of this shapes minds, shapes intelligence, shapes the next generation's cognitive capacities. The Flynn effect rising was an achievement, collective, unplanned, emerging from improving conditions. The reversal, if real and persistent, is a warning. We might be backsliding, losing cognitive ground despite material prosperity. And understanding why, addressing root causes, reversing the trend if needed, that's a challenge for educators, policymakers, researchers, societies. Because intelligence matters, not just individually, but collectively. Innovations, institutions, solutions to complex problems, all depend on human cognition functioning well. If we're losing cognitive capacity, even slightly, it's something we need to understand and address. Let's return to the strange world of particle physics. Some quantum particles are their own antiparticles, existing in a state of being both matter and antimatter simultaneously. The photon is its own antiparticle, and discovering others like the hypothetical Majorana fermion could revolutionize quantum computing. We explored this earlier, but the implications for quantum computing deserve emphasis. Majorana fermions, if they exist as quasi-particles in certain materials, could form the basis for topological quantum computers, potentially the most stable architecture for quantum computation yet conceived. The idea: conventional qubits are fragile, easily disturbed by environmental noise. They decohere, lose their quantum properties within microseconds or milliseconds. Error correction can help, but it requires many physical qubits to encode one logical qubit, a significant overhead. Topological qubits built from Majorana fermions would be inherently protected. Information is encoded not in the state of individual particles, but in the global topological properties of the system, how Majorana modes are braided, how their positions relate. Local disturbances, thermal fluctuations, stray electromagnetic fields wouldn't affect topology, so they wouldn't corrupt information. The qubit is protected by geometry, by the mathematics of topology, which doesn't change under small perturbations. This could enable quantum computers that operate at higher temperatures, require less error correction, and scale more easily. It's an elegant solution, using physics itself to protect information rather than brute forcing error correction. But creating Majorana quasi-particles is challenging. They require exotic materials, topological superconductors, semiconductor-superconductor hybrids, and precise control of conditions. Several research groups have reported signatures of Majorana modes, but definitive proof remains elusive. Distinguishing genuine Majorana signals from other phenomena mimicking them requires careful experiments, and replication has been mixed. If successful, though, topological quantum computing could leapfrog other approaches. It's a high-risk, high-reward direction in quantum computing research. driven by elegant theory and tantalizing experimental hints. And it's remarkable that the path to robust quantum computers might go through Majorana fermions, particles predicted 87 years ago by a physicist who disappeared, now potentially the key to technologies that could transform computation. And philosophically, Majorana fermions embody a deep symmetry, being their own antiparticles, straddling the boundary between matter and antimatter. In a universe where most things have opposites, Majorana fermions are their own opposites, self-symmetric, self-contained. It's a reminder that nature explores all possibilities, including the possibility of self-mirroring particles, and that these strange configurations might turn out to be useful, might be harnessed by humans or evolved by nature, might be sitting in ordinary materials, waiting for us to notice and exploit them. Let's return to ancient mysteries that challenge our understanding of past cultures. The Nazca lines in Peru include perfectly straight lines stretching for miles, created by removing rocks to expose lighter soil beneath. These geoglyphs from 500 BCE to 500 CE are best viewed from the air, yet were made by people who never flew. Their purpose remains debated. We touched on this earlier, but it's worth reflecting on the human impulse to create marks that transcend individual perspective. The Nazca created images and lines best seen from above, from a viewpoint they couldn't personally access. Why? Perhaps they imagined their work being viewed by gods, deities dwelling in the sky or on mountain peaks, looking down on the desert. The geoglyphs would be offerings, messages, declarations visible to the divine. Or perhaps they conceived of an elevated viewpoint spiritually. Shamans in trance states might have experienced flying, seeing the landscape from above, and then created earthworks reflecting those visions. Or maybe the Nazca simply understood geometry and planning well enough to create large-scale designs without needing to view them from above. They could work from small-scale drawings, scaling up using ropes and stakes, trusting their measurements. The fact that the designs are visible from above might be incidental, a consequence of their scale, not the primary intention. But whatever the purpose, the Nazca lines reveal sophisticated planning, organization, and cultural investment. Creating a geoglyph hundreds of meters across requires coordinating labor, maintaining vision across time. Some lines probably took years to complete, and valuing the result highly enough to invest resources, and they endure. The dry Nazca Desert preserves them. Minimal rain, little vegetation, stable ground. The lines have survived 2500 to 2500 years, outlasting the culture that created them, becoming mysteries for later peoples to ponder. The Nazca couldn't have known their geoglyphs would last so long, would be discovered by future civilizations flying above them in aircraft, viewing them from space. But they created them anyway for reasons meaningful to their culture, and those marks endure. It's a reminder that humans create meaning through marks, structures, symbols. We alter landscapes, build monuments, leave traces. Sometimes the purpose is practical, sometimes religious, sometimes artistic, sometimes all of these. And sometimes the marks outlast their meaning, becoming mysteries, archaeological puzzles, occasions for speculation and wonder. The Nazca lines are one such enduring mystery, visible, measurable, mapped in detail, yet still enigmatic. We know the how, but not fully the why, and maybe that's appropriate. Not every ancient creation needs to be fully explained. Some mysteries can remain, reminders that past peoples thought differently, valued differently, experienced the world through frameworks we can only partially reconstruct. The lines are there, drawn across the desert, speaking of a culture that looked to the sky and made marks for the gods, or the birds, or themselves, or reasons we'll never entirely know. Let's return to a phenomenon that reveals the complexity of consciousness. Some people with blind sight can navigate obstacles despite having no conscious visual experience. Their brain processing images they can't see. Damage to the visual cortex leaves them subjectively blind, yet subconscious pathways guide their actions around objects they insist they cannot perceive. We explored this earlier, but it's worth emphasizing what blind sight teaches us about the architecture of mind. Consciousness is not necessary for sophisticated information processing. Your brain can extract information from the environment, recognize objects, track motion, navigate space, without that information ever reaching conscious awareness. This has implications for artificial intelligence. If we build systems that process information, make decisions, guide actions, but lack consciousness, are they like blind sight patients? Capable but unaware? Or is consciousness necessary for some kinds of processing, some flexibility or integration that unconscious systems can't achieve? We don't know. Blind sight shows consciousness and function can dissociate, that processing without awareness is possible. But blind sight is also limited. Patients can navigate, but they lack the richness, the integration, the flexibility that conscious vision provides. They can't describe what they see, can't reflect on it, can't use it to inform complex decisions beyond immediate action. So maybe consciousness is integration, global availability of information, accessible to multiple systems, reportable and reflective. Blind sight processes information locally, in subcortical pathways, useful for guiding action but not broadcast to the rest of the brain. Consciousness broadcasts information, making it available widely, enabling flexibility and integration. This is the global workspace theory of consciousness. Information becomes conscious when it's broadcast to a global workspace, accessible to many cognitive systems. Blind sight is local processing without broadcast, function without consciousness, action without awareness. But the existence of blind sight challenges simplistic views that consciousness is necessary for any sophisticated behavior. It shows the brain has parallel pathways, some conscious, some not, both capable of processing sensory information. Consciousness might be one mode among several, useful for certain tasks, but not universal. And for the blind sight patient, the experience is disconcerting, knowing that their actions are guided by information they can't consciously access, feeling a disconnect between what they do and what they experience. It's a lived example of the unconscious mind at work, a demonstration that much of what guides behavior happens below awareness, in neural processes that never surface to consciousness. Let's return to cosmology and the deep question of existence. The universe's matter-antimatter asymmetry might involve CP violation, a subtle difference in how particles and antiparticles decay that we're still measuring. This tiny asymmetry, if confirmed, explains why you exist instead of annihilating into pure energy with your antimatter twin. We discussed this earlier, but it's worth reflecting on how contingent existence is. If CP violation were absent, if matter and antimatter were perfect mirrors, the universe would be empty. Every particle would have found its antiparticle, annihilated, and left only radiation. The tiny asymmetry, 1 part in a billion, made the difference between emptiness and everything, and we don't fully understand it. The CP violation we've measured in particle physics is in the right direction, but might not be large enough to explain the observed asymmetry. This suggests missing pieces, new particles, new interactions, physics beyond the standard model that was active in the early universe, but inaccessible in our low-energy experiments. Finding those missing pieces is one of particle physics' major goals. Neutrino oscillation experiments, searches for new particles at colliders, precision measurements of rare decays, all might reveal additional sources of CP violation, completing the explanation for matter's dominance. And there's a philosophical angle. Existence required breaking symmetry. Perfect symmetry would be sterile. Asymmetry, imperfection, violation of idealized balance. These are necessary for complexity, for structure, for matter, for life. The universe isn't built on perfect laws perfectly obeyed. It's built on laws with small violations, symmetries with small breaks, balances tipped just slightly in one direction. And those small imperfections cascaded into everything. It's humbling and remarkable. You exist because of an asymmetry so small it's almost zero, but just enough to survive the cosmic annihilation. Every atom in your body is part of the surplus, the tiny excess that remained after matter and antimatter destroyed each other. You're made of leftover matter, the remnant of an imbalance, a violation of symmetry that occurred in the universe's first instance. And that violation, that tiny, unexplained favoritism of matter over antimatter, is the reason there's something rather than nothing, the reason existence exists at all. Let's close this section with a phenomenon that reveals how strange, familiar substances can be. The Mpemba effect shows that hot water can freeze faster than cold water under certain conditions, violating our intuitive physics. Even Aristotle noticed this phenomenon, but physicists still debate exactly why it happens. Convection, evaporation, or something else entirely. We explored this earlier, but it's worth emphasizing how this simple phenomenon humbles our physics. Water, the most studied substance on Earth, essential to life, ubiquitous, still surprises us. We can't definitively explain why hot water sometimes freezes faster than cold. We have partial explanations: evaporation reducing mass, convection affecting heat transfer, supercooling delays in cold water, but no single, comprehensive theory that predicts when the effect occurs and when it doesn't. This is partly because water is complex. It's not a simple liquid following idealized physics. It has unusual properties: density maximum at 4 C, high surface tension, complex hydrogen bonding networks, anomalous expansion on freezing. These properties interact in nonlinear ways, making water's behavior context-dependent, sensitive to conditions. The Mpemba effect sits at the intersection of these complexities. It's real, observed, replicated, but elusive. Not universal, not always present, dependent on container shape, initial conditions, environment. It's a phenomenon that emerges from the interplay of multiple mechanisms, not reducible to a single cause. And that's a lesson. Nature is messy. Textbook physics works in idealized conditions: perfect gases, frictionless surfaces, isolated systems. But real-world phenomena involve multiple effects, interactions, nonlinearities. Simple questions: does hot water freeze faster than cold? Can have complex answers. Sometimes yes, sometimes no, depending on dozens of variables. The Mpemba effect is a reminder to stay humble, to keep questioning, to not assume we understand even simple things completely. Water freezing, one of the most mundane phase transitions, still holds mysteries. And if something so familiar, so fundamental, so studied, still surprises us, imagine how much we don't know about less familiar domains: exotic materials, extreme environments, the cosmos, consciousness, life. Science is a process, not a finished edifice. We build models, test them, refine them, but there are always edge cases, anomalies, phenomena that don't quite fit. The Mpemba effect is one such anomaly. Small, curious, frustrating, and ultimately humbling. It reminds us that the universe doesn't owe us simplicity, that even common substances can behave unexpectedly, that mystery lurks in the familiar as much as in the exotic. Let's begin this section with a phenomenon that reveals the boundaries of human perception and what lies beyond. Some people have tetrachromacy, 4 types of color receptors instead of 3, allowing them to see millions more colors than the rest of us. They live in a more vibrant world, perceiving distinctions invisible to normal vision, and might not even realize their experience is unique. We've touched on this before, but let's delve deeper into what it means to perceive a different reality. For most humans, color is constructed from 3 dimensions: responses from short, medium, and long wavelength cones combined in the brain to create our experience of color. This is sufficient to distinguish about 1 million colors, which seems rich until you realize it's a limitation, a constraint imposed by our hardware. Tetrachromats add a 4th dimension to color space. Their 4th cone type responds to wavelengths between the standard green and red cones. This additional dimension doesn't just let them see more of the same. It allows them to perceive color relationships that don't exist for trichromats. 2 paint samples that match perfectly to your eye might look distinctly different to a tetrachromat, one perhaps having a subtle warmth or coolness that you literally cannot perceive. What's remarkable is that tetrachromats often don't realize they're different. They might notice they're better at color matching, more sensitive to color variations, more bothered by color clashes that others don't see. But unless tested, they might assume everyone sees what they see. After all, we all use the same color words: red, blue, green. How would you know your red is richer, more nuanced than someone else's? This raises the classic philosophical problem of qualia, the subjective qualities of experience. When you and a tetrachromat both look at a sunset, are you seeing the same thing? Obviously not, in terms of the information being processed. But what about the experience itself? Is their sunset more beautiful because it has more colors? Or is beauty independent of the number of distinguishable hues? And it's not just about having more color receptors. The brain must learn to process the 4th channel of information. Some women genetically have the mutation for 4 cone types, but don't experience enhanced color vision, possibly because their brains never developed the neural pathways to utilize the 4th cone. The hardware exists, but isn't fully integrated into the perceptual system. This suggests that perception isn't just about sensors. It's about the entire processing pipeline from retina to brain, and that pipeline must be trained during development. Tetrachromacy also exists in the animal kingdom. Most birds have 4 cone types, including sensitivity to ultraviolet light. Their visual world is dramatically different from ours. Flowers that appear uniformly colored to us display UV patterns visible to birds and bees, guiding pollinators to nectar. Male and female birds of some species look identical to humans, but display different UV plumage patterns to each other. The avian world is painted in colors we cannot see, conducting visual conversations in spectra invisible to mammalian eyes. And beyond tetrachromacy, some animals have even more complex color vision. Mantis shrimp have 12 types of photoreceptors, suggesting an incredibly rich color experience. Except research suggests they might process color differently, using their receptors more like a barcode reader than constructing a high-dimensional color space. Their experience might be alien in ways we can barely conceive. The existence of tetrachromacy reminds us that perception is contingent, that the world we experience is filtered through our particular sensory apparatus, and that other configurations are possible, sometimes within our own species. What seems like a unified, objective redness is actually a constructed experience that varies between individuals. We share language about colors, but our experiences might be surprisingly different. And it raises questions about enhancement. If we could add photoreceptors through genetic engineering or cybernetic augmentation, would we want to? Would seeing more colors enrich experience, or would it be overwhelming, perhaps making the ordinary world garish, or creating color clashes in environments designed for trichromatic vision? Our built environment assumes trichromacy, colors chosen, paint mixed, lights designed for 3-channel vision. Adding a fourth might reveal disharmonies we never noticed. For now, natural tetrachromats live among us, seeing a richer palette, experiencing color dimensions the rest of us lack. They're reminders that reality is larger than our perception of it, that the visible spectrum contains more information than we can access, and that the world we see is just one slice through a much richer perceptual space. The sunset is beautiful to us, but to a tetrachromat, it might be something even more, a symphony of hues we cannot name because we've never seen them, colors that exist but remain forever beyond our experience. Let's turn to the powerful geological forces that have shaped civilizations throughout human history. The Pacific Ring of Fire contains 75% of Earth's volcanoes, forming a near-perfect circle we're still learning to predict. This horseshoe of tectonic violence surrounds an ocean and concentrates most of the planet's seismic energy in one ominous arc. We've explored this before, but let's consider what it means to live within the ring, to build civilizations on land that shakes and burns. Billions of people inhabit the Ring of Fire: Japan, Indonesia, Philippines, Western Americas. They've learned to coexist with geological violence, to build earthquake-resistant structures, to develop warning systems, to prepare for inevitable disasters. And it's shaped cultures. Japanese architecture traditionally favored wood and flexible joints, allowing buildings to sway rather than collapse during earthquakes. Cultural practices, earthquake drills, tsunami evacuation routes, disaster supply kits, become part of life. Religion and mythology incorporate volcanic and seismic events, angry gods, cosmic serpents, explanations for why the earth moves and mountains explode. But preparation can only mitigate, not prevent, disaster. The 2011 Tohoku earthquake generated a tsunami that overwhelmed defenses designed for smaller waves. The Fukushima nuclear plant, built with earthquake protections, couldn't withstand the combined earthquake-tsunami disaster. Human planning has limits when facing the full power of tectonic forces, and prediction remains elusive. We know where earthquakes are likely, along fault lines, subduction zones, but not when. Seismologists can estimate probabilities over decades, but can't predict specific earthquakes days or weeks in advance with reliability. The Earth gives subtle signals: foreshocks, ground deformation, changes in groundwater, but these are ambiguous, sometimes present without major earthquakes, sometimes absent before devastating ones. Volcanic eruptions are slightly more predictable. Magma movement causes measurable changes: seismic swarms, ground swelling, gas emissions. Monitoring these signs allows warnings before eruptions, saving lives through evacuations. But predictions aren't perfect. Some eruptions occur with little warning. Others are preceded by months of activity that doesn't culminate in eruption. The Ring of Fire also creates. Volcanic soils are fertile, enriched with minerals. Islands exist because of subduction-driven volcanism. Japan, Indonesia, Philippines, Aleutians. Without the ring, they wouldn't be land at all, just ocean. Geothermal energy, mineral deposits, dramatic landscapes that attract tourism, all products of tectonic activity. So the ring is both destroyer and creator, threat and resource. It's a fundamental part of Earth's geological system, the mechanism by which heat escapes from the interior, by which crust is recycled, by which mountains build and continents drift. Life on Earth has always existed on a geologically active planet. The Ring of Fire is just the current configuration of that activity, the place where tectonic plates converge, subduct, melt, and rise as magma. And it will change. Tens of millions of years from now, plate movements will reconfigure boundaries. The Pacific plate is shrinking, subducting beneath surrounding plates. Eventually, it might close entirely, and the Ring of Fire will be replaced by different subduction zones, different volcanic arcs, a different arrangement of tectonic violence. The planet is dynamic, always shifting, always active. We happen to live during a period when the Ring of Fire exists in its current form, when the Pacific is encircled by volcanoes and fault lines, when billions live within its reach. And we adapt. Humans are remarkably good at inhabiting marginal environments, at accepting risks in exchange for resources or location. The Ring of Fire concentrates hazards, but it also concentrates opportunities. Fertile land, ocean access, strategic locations. So we build, we prepare, we accept that the ground might shake, that mountains might erupt, and we live our lives in the shadow of geological forces that dwarf human power. It's a humbling arrangement, a reminder that we're guests on a dynamic planet, and that the Earth will do what it does regardless of our presence. Let's return to the frontier of computation and quantum mechanics. Quantum computers can theoretically solve certain problems exponentially faster than classical computers, but we don't fully understand the limits. They harness superposition and entanglement to explore all possible solutions simultaneously, computing with the fabric of reality itself. We've touched on this before, but let's explore what it means to compute with probability. Classical computers manipulate definite states, bits that are either 0 or 1 unambiguously. Computation is deterministic. Given the same input and program, you get the same output. Randomness can be introduced, but it's layered on top of fundamentally deterministic operations. Quantum computers manipulate probability amplitudes. complex numbers whose squared magnitudes give probabilities. A qubit isn't 0 or 1, it's a superposition, both simultaneously, with specific amplitudes for each. When you have multiple qubits, they can exist in superpositions of all possible bit strings. 3 qubits can simultaneously represent 00, 01, 010, 011, 100, 101, 110, 111, all 8 states at once, each with its own amplitude. Quantum operations manipulate these amplitudes, allowing different computational paths to interfere. Some paths reinforce each other, constructive interference. Others cancel out, destructive interference. A well-designed quantum algorithm sets up amplitudes so that wrong answers interfere destructively and disappear, while the correct answer interferes constructively and dominates. When you measure, you get the correct answer with high probability. This is fundamentally different from classical parallelism. Classical parallel computers run multiple computations simultaneously on different processors, but each computation is definite, deterministic. Quantum computers run one computation that explores multiple paths simultaneously through superposition and interference. It's not just trying all possibilities at once. It's using wave-like properties of quantum states to guide the computation toward the answer through interference patterns. But quantum computers aren't universally faster. For many problems, simple calculations, database lookups, most everyday computing tasks, they offer no advantage. The power emerges for specific problems where interference can be exploited. Factoring large numbers, searching databases, simulating quantum systems, certain optimization and machine learning tasks. And building them is extraordinarily hard. Qubits must be isolated from the environment to maintain superposition. Any interaction causes decoherence, collapsing the quantum state and destroying the computation. Yet qubits must also be controllable. You need to manipulate them precisely, apply operations, and eventually measure them. This tension, isolation versus control, is the central challenge of quantum computing engineering. Current quantum computers are noisy, limited to tens or hundreds of qubits, and can run algorithms for only brief periods before decoherence overwhelms them. They're not yet useful for practical problems that classical computers can't handle. But progress is rapid, qubit counts increasing, error rates decreasing, algorithms improving. Within decades, quantum computers might be solving problems intractable classically, designing new materials by simulating their quantum properties, optimizing complex logistics, breaking current encryption, and enabling new quantum-secure alternatives. And there's a conceptual shift. Quantum computing forces us to think about computation differently, not as manipulating definite states through definite operations, but as guiding probability amplitudes through interference. It's computation as choreographing waves, as sculpting probability distributions, as using the universe's quantum substrate as a computational resource. This raises philosophical questions. What is computation? Is it fundamentally about manipulating information, or is it tied to physical processes? If quantum computers are harnessing superposition and entanglement, quantum properties of reality, are they revealing something deep about the relationship between computation and physics? Some physicists suggest the universe itself might be a quantum computer, that physical evolution is computation, that reality is fundamentally computational. These are speculative, borderline metaphysical. But quantum computing blurs the line between physics and information science, showing that computation isn't just an abstract mathematical process, but something deeply tied to how reality works at its most fundamental level. And as we build quantum computers, learn to control quantum states, harness superposition and entanglement, we're not just developing new technology, we're learning to speak the universe's native language, to compute the way reality computes, to use quantum mechanics, not just to observe, but to calculate. Let's return to human psychology and the way our minds construct meaning. The Baader-Meinhof phenomenon makes something seem ubiquitous once you notice it, revealing how attention sculpts our perceived reality. You buy a new car and suddenly see that model everywhere, not because it's more common, but because your brain is now primed to notice. We explored this earlier, but it's worth reflecting on how pervasive this effect is. It's not just cars, it's anything that enters your awareness. Learn a new word, and suddenly you hear it everywhere. Start thinking about a concept, and articles about it seem to appear constantly. Decide you're interested in a topic, and the universe seems to conspire to show you related content. This isn't the universe conspiring, it's your attention system updating. Your brain filters vast amounts of sensory information constantly, flagging what's relevant and ignoring the rest. Once something becomes relevant to you, you bought that car, you learned that word, you're interested in that topic. Your brain starts filtering for it, bringing instances to conscious awareness that it would have previously ignored. And confirmation bias compounds the effect. You notice and remember instances that fit the pattern, forget or don't notice instances that don't. If you're primed to see red cars, you'll notice every red car, but you won't consciously register all the blue, white, and black cars. The red cars seem disproportionately common because they're disproportionately remembered. This mechanism is usually adaptive. Paying attention to things relevant to your current goals, filtering out irrelevant noise. This is essential for functioning. You can't consciously process everything, so your brain prioritizes. The Baader-Meinhof phenomenon is this prioritization made visible, an edge case where the priming is recent enough and the phenomenon salient enough that you notice the change in your perception. But it can mislead. It creates illusions of frequency, of trends, of patterns that aren't there. This feeds into how we form beliefs, how we interpret evidence, how we decide what's important. If you're primed to notice negative news, the world seems to be getting worse, even if negative events are statistically stable. If you're primed to notice successes of a particular strategy, it seems more effective than it is. And in the age of social media and algorithmic feeds, the Baader-Meinhof phenomenon is amplified. Algorithms notice what you click on, engage with, linger over. They serve you more of the same. So your initial interest, your chance encounter with a topic, gets reinforced by the algorithm feeding you related content. Your attention and the algorithm create a feedback loop, making the phenomenon seem even more ubiquitous than your brain would naturally make it seem. Being aware of Baader-Meinhof is a form of cognitive hygiene. When you find yourself thinking, I keep seeing this everywhere, pause and ask, has it actually become more common, or have I just started noticing? Often it's the latter. The world hasn't changed. Your attention has. And recognizing that distinction helps you avoid false conclusions about trends, frequencies, importance. It's a small lesson in epistemic humility. Your perception of reality is constructed, filtered, biased by attention and memory. What seems objectively true about the world might be subjectively shaped by where your attention is directed. And understanding this, you can be more careful, more skeptical of your own perceptions, more aware that the world you experience is always partly a world your mind has made. Let's return to the astonishing endurance of life at its simplest. Some microbes have been revived after 250 million years in salt crystals, challenging our definitions of dormancy and death. These bacteria were buried before dinosaurs existed, waiting in suspended animation through the rise and fall of countless species. We've discussed this before, but let's reflect on what it means to wait that long. 250 million years is incomprehensible on human scales. Civilizations rise and fall in thousands of years. Species emerge and go extinct in millions. But these bacteria, if the extreme age claims are accurate, persisted through it all, metabolically silent, neither alive nor dead in the usual sense, just waiting. What is it like to be dormant for that long? Of course, there's no subjective experience. Bacteria don't have consciousness, don't experience time passing. For them, the 250 million years might as well be 250 seconds or 250 microseconds. They shut down, and when conditions permit, they start up again, with no sense of the intervening time. But from an external perspective, it's staggering. An organism that existed during the Permian, before dinosaurs, before flowering plants, before mammals diversified, lying dormant through all of Earth's subsequent history, and then reviving in a modern laboratory. It's like receiving a message from deep time, a biological fossil that isn't quite fossil. It's still viable, still capable of function, and it challenges our categories. Is a dormant bacterium alive? It's not metabolizing, not responding to stimuli, not reproducing. By most definitions, it's not exhibiting life processes, but it's not dead either. It retains the capacity to revive, to resume life when conditions permit. It exists in a liminal state, a biological pause, potential life held in suspension. This has implications for how we think about life in the universe. If organisms can survive hundreds of millions of years in dormancy, then life might spread between worlds more easily than we thought. Panspermia, life traveling on meteorites, becomes plausible if organisms can endure the journey. A rock ejected from Mars by an impact, carrying dormant microbes in ice or salt deposits, could drift through space for millions of years and arrive at Earth with still viable organisms. Life could seed itself across the solar system, even between star systems, given enough time. And it suggests that places we consider dead might harbor dormant life. Mars, cold and dry now, had surface water billions of years ago. If Martian life existed then, could it still be there, dormant in subsurface deposits, waiting for conditions to improve? Would we recognize it? Would our searches designed to detect active metabolism miss organisms in deep dormancy? On Earth, the discovery that bacteria can survive so long in salt crystals means there might be viable ancient organisms in many geological formations. Every ancient salt deposit, every ice core, every sediment layer millions of years old. These might contain dormant life from past eras, biological time capsules waiting to be opened. Of course, there's risk. Reviving ancient bacteria raises biosafety questions. Could ancient pathogens harm modern organisms? Unlikely. They evolved in a different microbial landscape, and modern immune systems probably wouldn't recognize them as threats, or they wouldn't be adapted to infect modern hosts. But caution is warranted when dealing with organisms from past epochs, and there's a poetic dimension. These bacteria, if genuinely ancient, are travelers from another world, not another planet, but another time, an Earth so different from today that it's almost alien. They're witnesses to epochs we only know through fossils, carriers of genetic information from ecosystems long vanished. Reviving them is a form of resurrection, bringing the past into the present, collapsing vast spans of time into a petri dish where ancient and modern microbes might coexist. Life's ability to wait, to pause for eons, and resume when conditions permit, is perhaps the ultimate survival strategy. Not toughness in facing adversity, but patience in avoiding it, dormancy that outlasts catastrophe. And these bacteria, if their age is confirmed, are masters of patience, having waited through the greatest mass extinctions, through climate changes, through continental drift, through the entire age of dinosaurs and everything after, preserved in salt, waiting for someone to crack open their crystal and give them water. And then they wake, as if no time has passed, and begin metabolizing again, indifferent to the eons they slept through. Let's return to a cosmological anomaly that seems too strange to be real. The axis of evil in the cosmic microwave background shows unexpected alignments that seem to point toward Earth's location. These patterns shouldn't exist in a truly random universe, suggesting either a cosmic conspiracy or flaws in our cosmological models. We touched on this earlier, but let's consider what it would mean if the alignment is real and not artifact. The cosmic microwave background is supposed to be statistically isotropic. No preferred direction, no special alignments. The universe doesn't care about Earth's orientation or motion. The cosmological principle, a foundation of modern cosmology, says the universe looks the same in all directions. But if the largest scale fluctuations in the CMB align with Earth's ecliptic plane, with our motion through space, with features of our local cosmic environment, that would be profoundly disturbing. It would suggest Earth or the solar system occupies a special location or orientation, which violates the Copernican principle that we're not special, not central, just one typical place among countless others. How could this happen? Several possibilities, none entirely satisfying. 1. It's statistical fluke. The patterns look significant because we searched for patterns and found some by chance. The look elsewhere effect, if you search enough possibilities, something will seem unlikely. But the alignments persist across different analyses, making pure chance less likely. 2. It's systematic error, foreground contamination from our galaxy, instrumental artifacts, data processing choices. Any of these could introduce apparent patterns that aren't cosmological. Researchers have tried to account for these, but perhaps not perfectly. The axis might be an artifact of how we observe, not a feature of reality. 3. Our models are incomplete. Maybe the universe isn't perfectly isotropic at the largest scales. Maybe there's a preferred direction, a remnant of some earlier phase, some topological feature or boundary condition we haven't accounted for. This would require new physics, but it wouldn't necessarily make Earth special. It would just mean the universe has structure we didn't expect. 4. we are special in some sense. Not because we're privileged or central, but because of selection effects or anthropic reasoning. Maybe observers can only arise in regions with certain properties, and those properties happen to correlate with large-scale CMB patterns. This feels unsatisfying, but is technically possible. Most cosmologists bet on explanation too. Artifact, not real. But the persistence of the axis of evil in the literature, despite attempts to explain it away, keeps it alive as a curiosity. It might be nothing, probably is nothing, but it's a reminder that our observations are always filtered through instruments, analysis choices, and assumptions. And sometimes those filters introduce patterns that seem real but aren't. And if it's real, if further observations and analyses confirm that the CMB has genuine large-scale alignments with our local reference frame, then we'd face a crisis in cosmology, a challenge to the cosmological principle, a need to rethink fundamental assumptions. It would be exciting and unsettling. Exciting because new physics awaits. Unsettling because it would suggest we don't understand the universe as well as we thought. For now, the axis of evil is an anomaly, a puzzle, a cautionary tale about interpreting data carefully. It reminds us that cosmology, despite its successes, operates at the limits of observation and theory, analyzing the entire universe from a single vantage point, Earth, and trying to infer global properties from local measurements. It's a remarkable achievement when it works, but it's also prone to subtle errors, to patterns that seem significant but aren't, to the universe trolling us with coincidences that look meaningful. And until we're sure, the axis remains, a strange alignment in the sky pointing at us, for reasons we don't fully understand. Let's return to the strange boundary states of consciousness. Some people experience sleep paralysis accompanied by a sensation of a malevolent presence, a phenomenon reported consistently across cultures. Your brain is awake, but your body remains in REM atonia, and the fear response activates, creating hallucinations of intruders or demons. We've explored this before, but let's consider what sleep paralysis reveals about the modularity of consciousness. We think of being asleep or awake as binary states. You're one or the other. But sleep paralysis shows these states can mix. Your brain can be conscious, aware, perceiving, experiencing, while your body remains in sleep mode, paralyzed, immobile, unresponsive to motor commands. This dissociation reveals that what we call states of consciousness are actually coordinated patterns across many brain systems. Wakefulness involves consciousness, mobility, responsiveness to environment. Sleep involves unconsciousness, paralysis during REM, disconnection from environment. But these components can desynchronize. Sleep paralysis is wakefulness plus REM paralysis, an unstable hybrid state that usually resolves quickly as the brain completes its transition. And the hallucinations, those consistent reports of presences, intruders, demons, reveal how the brain constructs explanations for anomalous experiences. You're awake but can't move. This is weird, threatening. Your amygdala activates, generating fear. Your brain searches for an explanation. Why can't I move? Why am I afraid? And it constructs one. There must be something here, something holding me down, something dangerous. The presence is an inference, a story the brain tells to make sense of the inexplicable combination of wakefulness, paralysis, and fear. The specific form of the presence, demon, alien, intruder, old hag, varies by culture, drawing on available narratives and archetypes, but the underlying experience is universal. Immobility plus fear plus the sensation of another entity. The brain fills in details using cultural material, but the core phenomenon transcends culture. And it's distressing. Even knowing intellectually that sleep paralysis is harmless, that the presence isn't real, doesn't fully mitigate the terror in the moment. The fear is physiological, generated by ancient brain systems that don't listen to rational explanations. You're trapped in a state where your emotional brain is screaming danger while your rational brain knows it's fine. A disconnect that's almost as disturbing as the hallucination itself. For those who experience it frequently, sleep paralysis can disrupt sleep and create anxiety around bedtime. But understanding helps. Knowing what it is, knowing it's temporary, learning techniques to break the paralysis or relax through it, these reduce distress. And for most people, episodes are rare enough that sleep paralysis is just an occasional oddity, a strange window into the complex machinery of sleep and waking. And it's a reminder that consciousness isn't a monolith. It's an assemblage of processes: wakefulness, body awareness, sensory processing, motor control, emotion, memory, normally synchronized, but capable of decoupling. Sleep paralysis decouples wakefulness from motor control. Dreams decouple consciousness from reality testing. Dissociation decouples awareness from body sensation. These edge cases reveal the structure of normal consciousness by showing what happens when it partially fragments. So sleep paralysis, frightening as it is, teaches us about minds, about how precarious the feeling of unified conscious control is, about how much of our experience is constructed by brain systems trying to make sense of inputs and states, sometimes creating entities and presences and narratives to explain anomalies. The demon on your chest isn't there, but your brain made it convincingly real, because that's what brains do. They tell stories, construct explanations, create coherent experiences from whatever data they have, even when the data is as strange as being awake in a paralyzed body in the middle of the night. Let's return to one of humanity's deepest questions. The Drake equation estimates the number of communicative civilizations in our galaxy, but requires guesses for values we have no way to measure. Depending on your assumptions, we're either surrounded by thousands of civilizations or utterly alone. The equation can't tell us which. We've explored this before, but let's sit with the uncertainty. The Drake equation is a framework, not an answer. It breaks the question, are we alone, into components. How many stars? How many planets? How many habitable? How often does life arise? How often does intelligence emerge? How often does civilization develop technology? How long do civilizations last? The early terms we can measure. We know star formation rates, planet frequencies, habitability zones. But the later terms, life, intelligence, civilization longevity, are unknown, and the uncertainties multiply. Even if life is common, intelligence might be rare. Even if intelligence is common, technological civilizations might be rare or short-lived. And the last term, L, the longevity of civilizations, might be the most critical. If civilizations typically last millions of years, the galaxy could be full of them, many much older than us. If civilizations typically last centuries, destroying themselves shortly after developing radio technology, then at any given time, the galaxy might contain only a handful, scattered too far apart to detect each other. We're one data point, Earth has had life for 3.5 billion years, but technological civilization for less than a century. Intelligence took almost the entire history of life on Earth to evolve. And even then, only one species developed technology. Does this suggest intelligence is rare? Or that we're early, that given time, intelligence evolves often, and we're just the first on Earth? We can't tell from one example. The Fermi paradox sharpens the question. If civilizations are common, where are they? Why don't we see evidence? Radio signals, megastructures, artifacts. Maybe they're out there, but we haven't looked carefully enough. Maybe they don't communicate the way we expect. Maybe they exist but avoid contact. Maybe the filter, whatever prevents civilizations from becoming visible, is ahead of us, and those that survive it become so advanced we can't recognize them. Or maybe the filter is behind us, and we're rare, lucky to have made it this far. Each possibility is profound. If we're alone, it places enormous responsibility on humanity. We might be the universe's only way of understanding itself, the only consciousness, the only meaning makers. If we're not alone, but civilizations are fragile, it suggests the universe is full of ruins, failed experiments, societies that couldn't survive their own power. If civilizations are common and enduring, it means we're juveniles, newcomers to a crowded galaxy, and first contact awaits us. We don't know. The Drake equation can't tell us. It can only frame the question, guide our thinking, suggest what we need to measure. And so we search, listening for radio signals, looking for technosignatures, seeking biosignatures on exoplanets. Each null result doesn't prove we're alone. It just means we haven't found them yet. Each candidate signal, like the wow signal, tantalizes but doesn't confirm. And maybe that uncertainty is where we'll stay for a long time. Maybe we'll detect microbial life on Mars or Enceladus, proving life arises elsewhere, but not finding intelligence. Maybe we'll listen for centuries and hear nothing, forcing us to conclude we're either alone or that communication across interstellar distances is harder than we thought. Or maybe tomorrow, a clear artificial signal will be detected, unmistakable and repeating, and everything changes. The question, are we alone, is one of the few questions where either answer, yes or no, would be equally astonishing. And the Drake equation, for all its uncertainties, keeps the question alive, reminds us of what we don't know, encourages us to keep searching. Because whether we're alone or not, we won't know until we look. And the universe, vast and silent, waits for us to find the answer. Let's turn to one of the most perplexing questions in theoretical physics. We don't know what happens to information that falls into a black hole, a puzzle called the information paradox. It challenges our understanding of whether the universe keeps a record of everything, or if some things can truly be erased. In quantum mechanics, information is never destroyed. It might become scrambled, spread out, hard to access, but fundamentally it's preserved. This is called unitarity, and it's a cornerstone of quantum theory. If you know a system's current state, you can in principle reconstruct its past or predict its future. Information isn't lost, it's conserved. But black holes challenge this. When something falls into a black hole, it crosses the event horizon and is lost from view. From outside, you can't see what's inside. And Stephen Hawking showed that black holes radiate. They emit thermal radiation and slowly evaporate. Eventually, a black hole disappears entirely, leaving only radiation. Here's the problem. Thermal radiation is random, carrying no information about what fell in. If a black hole evaporates completely into thermal radiation, the information about everything that fell in would be lost forever. The universe would forget. This violates quantum mechanics' requirement that information is conserved. So we have a paradox. Either quantum mechanics is wrong, information can be destroyed, unitarity fails, or general relativity is wrong. Something about how we understand black holes is incorrect. Or both theories are incomplete, and reconciling them requires new physics. Proposals to resolve the paradox abound. Maybe information is encoded in the Hawking radiation, in subtle correlations we haven't calculated yet. Maybe the event horizon isn't a smooth, featureless boundary, but a firewall where information is burned up but preserved in radiation. Maybe black holes have interior structure, fuzz or gravastars, where information is stored and eventually released. Maybe information escapes through quantum channels, wormholes, or higher dimensions we don't perceive. One prominent idea is the holographic principle, which we've discussed. Information about a black hole's interior is encoded on its event horizon, a two-dimensional surface. The interior is a hologram, a projection from boundary information. When the black hole evaporates, the horizon shrinks, and information is gradually released in Hawking radiation. Information is preserved, but in a non-local way we don't intuitively grasp. Another idea involves black hole complementarity. Different observers see different things. An observer falling into a black hole experiences smooth passage through the horizon, encountering no drama. An outside observer sees the information encoded on the horizon and eventually released in radiation. Both perspectives are valid, but they can't be compared directly because the infalling observer is lost beyond the horizon. Information is preserved from outside, but the inside perspective is inaccessible. But these are speculative. We don't have a complete theory of quantum gravity, so we can't definitively say what happens at event horizons or how black holes evaporate at the quantum level. The information paradox remains open, a signpost pointing toward missing physics. And it raises deep questions about the nature of information, reality, and time. Is information physical or abstract? If it's conserved by the laws of physics, does that make it fundamental, more fundamental than particles or forces or space-time itself? And if information can never be destroyed, does that mean the universe is deterministic at the deepest level? That every event is in principle reconstructible from the present state? These are questions at the intersection of physics, mathematics, and philosophy. The information paradox isn't just a technical puzzle about black holes. It's about the nature of physical law, the relationship between quantum mechanics and gravity, the structure of space-time, the meaning of information. And until we solve it, black holes remain mysterious, not just as astronomical objects, but as theoretical challenges, places where our best theories collide and produce contradictions we don't yet know how to resolve. For now, information falling into black holes is lost from our observable universe, disappearing beyond the event horizon into a region we can never access. Whether it's truly lost or preserved in ways we don't understand, that's the mystery. And solving it might require rethinking everything we thought we knew about space, time, and the nature of reality itself. Let's close this section with a phenomenon that shows nature exploiting quantum mechanics in surprising ways. Migrating birds can sense Earth's magnetic field through quantum processes in their eyes. Navigation through quantum biology. A protein called cryptochrome may use entangled electrons to detect field orientation, making birds living quantum sensors. We've explored this before, but let's consider the marvel of evolution, discovering quantum mechanics millions of years before humans. Birds needed a compass, a way to sense Earth's magnetic field for navigation. Natural selection, blind and opportunistic, explored chemical space, tested variations, preserved what worked. And somehow, this process arrived at a mechanism involving quantum entanglement. Radical pairs with entangled electron spins, sensitive to magnetic fields through quantum effects. This is remarkable because entanglement is fragile. It's destroyed by environmental interactions, heat, collisions, fields. Quantum computers require near absolute zero temperatures and extreme isolation to maintain entanglement for milliseconds. Yet bird eyes operate at body temperature, in wet, chemically active environments, and maintain entanglement long enough, tens of microseconds, for the radical pair mechanism to function. How? Likely through molecular engineering. The cryptochrome protein is structured precisely, shielding the radical pair from environmental noise just enough. It's not perfect isolation. That's impossible at body temperature, but it's good enough. Natural selection optimized the protein structure over millions of years, finding a configuration that balances sensitivity and robustness. And it works. Birds migrate thousands of miles using this quantum compass, navigating accurately across continents and oceans. The mechanism is functional, reliable, sufficient for survival. Evolution doesn't care about elegance or purity. It cares about what works. And quantum sensing works, so here it is, in bird eyes, guiding migrations. This has implications for technology. If birds can use quantum effects in warm, noisy environments, maybe we can too. Quantum sensors for navigation, medical imaging, geological surveying, all could benefit from robust room temperature quantum devices. Studying how cryptochrome achieves this might inspire biomimetic quantum sensors, technologies based on biological principles. And it suggests quantum biology might be more widespread than we thought. Life operates at the messy, warm, wet boundary between quantum and classical regimes. Most processes are classically describable, but occasionally quantum effects might play functional roles, enhancing efficiency, enabling otherwise impossible chemistry, providing sensory capabilities, photosynthesis, olfaction, enzyme catalysis, all are being investigated for possible quantum contributions. Whether quantum effects are common or rare in biology remains debated. Some researchers are skeptical, arguing that thermal noise overwhelms quantum coherence too quickly for biological relevance. Others point to accumulating evidence that life has learned to exploit quantum effects in specialized contexts. The truth probably lies between quantum biology is real, but limited to specific, well-engineered molecular systems where evolution has optimized for quantum functionality. For the bird, none of this is mysterious. It just sees the world, including magnetic field patterns, and flies accordingly. It doesn't know it's using quantum entanglement, any more than you know your eyes are using photon absorption by rhodopsin molecules. Perception is transparent. We experience results, not mechanisms. The bird experiences direction, and it flies toward winter grounds or summer nesting sites. guided by quantum processes in proteins, by entangled electrons responding to Earth's field, by physics at the smallest scales influencing behavior at the largest. And that's beautiful. The microscopic and the macroscopic connected, quantum mechanics enabling continent-spanning migrations. The universe's deepest physics, guiding birds across oceans. It's all one system, one integrated reality, where quantum and classical, small and large, abstract and concrete, all weave together into the fabric of nature. And birds, flying through it, carrying quantum sensors in their eyes, are living demonstrations that the boundary between physics and biology, between fundamental and applied, between weird and everyday, is permeable, crossed constantly by processes we're only beginning to understand. Let's begin this final section by returning to cosmic echoes. The universe's baryon acoustic oscillations, sound waves from the early universe, are frozen in the distribution of galaxies like cosmic fossils. We can read the echo of creation in how galaxies cluster, using sound waves from when the universe was 380,000 years old. We've touched on this before, but let's reflect on what it means to observe something so ancient still influencing the present. The sound waves that propagated through primordial plasma 13.8 billion years ago have left their imprint on the universe's structure. Every galaxy survey, every three-dimensional map of cosmic structure contains this fossil signal, a characteristic scale, a preferred separation distance between galaxies that traces back to the size of sound waves when the universe became transparent. It's as if the universe took a photograph of itself at 380,000 years old. And that photograph has been slowly developing ever since, its features growing from tiny density variations into the galaxies and voids we see today. The baryon acoustic oscillations are the grain of that photograph, the texture that reveals the image's origin. And we can use this to measure the universe itself. Because we know the physical size of the sound wave when it froze, we can calculate it from first principles, from the physics of the early universe. We can compare that known size to how large it appears in galaxy surveys. The apparent size depends on distance and on how space has expanded in the intervening time. By measuring the BAO scale at different redshifts, at different epochs in cosmic history, we trace the expansion history of the universe, map the influence of dark energy, test cosmological models. This is cosmology at its most powerful, using fossils from the universe's infancy to constrain its present and future. The sound waves are messengers from the early universe, carriers of information about cosmic conditions when the universe was too young for stars or galaxies, when it was just hydrogen and helium plasma radiating light that would become the cosmic microwave background. And the sound waves connected regions that are now separated by billions of light years. Regions that shared acoustic oscillations in the early universe are now distant, isolated by cosmic expansion. Yet they still bear the correlated imprint of those ancient vibrations. It's a kind of cosmic entanglement, not quantum, but gravitational and acoustic, a correlation across vast distances and times, preserved in structure. There's something poetic about the universe remembering its infancy through sound. We often think of light as the primary cosmic messenger, photons carrying information across space and time. But sound, pressure waves in plasma, also left records, frozen when the plasma became neutral gas, written into the initial conditions for galaxy formation. And those records persist, readable by anyone who maps galaxies carefully enough. A cosmic archive preserved in the arrangement of matter. As our galaxy surveys improve, measuring positions of millions, eventually billions of galaxies, the BAO signal becomes clearer, the constraints tighter. We're reading the universe's history with increasing precision, using echoes from its first moments to understand its composition, evolution, and fate. And those echoes, those ancient sound waves, are still there, still visible, still speaking to us across time, if we know how to listen. Let's return to the rich variations in human perception. Some people experience chromesthesia, a form of synesthesia where sounds automatically trigger seeing colors that others never perceive. For them, a trumpet might be orange, a violin purple, creating a constant internal light show accompanying all auditory experience. We've explored this phenomenon before, but let's consider what it reveals about the plasticity of perception. Synesthesia shows that sensory boundaries are not absolute, that the brain's modular organization, separate systems for vision, hearing, touch, can be bridged, creating unified experiences that blend modalities. For chromesthetes, music is inherently visual. Listening to a symphony isn't just an auditory experience, it's audiovisual, with colors appearing in rhythm with the sounds. Some describe it as enriching, as adding depth and beauty to music. Others find it distracting, especially in noisy environments where every sound triggers colors, creating overwhelming visual stimulation. And the colors are consistent. A given note or instrument produces the same color each time, not randomly changing. This consistency suggests the cross-activation between auditory and visual regions is stable, possibly reinforced during development, creating fixed mappings between sounds and colors. It's as if the brain has wired additional connections, or failed to prune them during development, leaving pathways that most people lose. The specific mappings vary between individuals. One chromesthete might experience middle C as red, another as blue. But there are statistical trends. Higher pitches tend to produce lighter, brighter colors. Lower pitches, darker colors. This suggests some mappings are more natural, perhaps based on shared properties, like frequency or intensity, that translate across modalities. And it raises the question, why doesn't everyone have synesthesia? Or conversely, why do some people have it? The difference might be small, a few extra connections, slightly different pruning during brain development, genetic variations affecting neural wiring. Synesthesia runs in families, suggesting genetic components, but it's not deterministic. Identical twins can differ in whether they're synesthetes, suggesting environmental or stochastic factors during development also matter. For the chromesthete, explaining their experience to non-synesthetes is challenging. How do you convey what it's like to see sounds when your audience has never experienced it? It's like trying to describe color to someone born blind. The words are there, but the qualia, the subjective experience, can't be fully communicated. Non-synesthetes can understand intellectually that chromesthetes see colors with sounds, but they can't experience what that's like. And this highlights the fundamental privacy of consciousness. Each person's experience is locked inside their skull, accessible only to them. We assume similarity, that your red resembles mine, that your pain feels like mine. But we can never truly know. Synesthesia makes this uncertainty explicit by showing that perceptual experiences can differ in fundamental ways between individuals, yet we use the same language, live in the same world, communicate successfully despite inhabiting different experiential spaces. For artists and musicians with chromesthesia, the condition can influence creativity. Duke Ellington chose band members partly based on the colors their instruments produced in his perception, creating color-coordinated arrangements only he could see. Pharrell Williams describes his music production as guided by colors, seeking color combinations that feel harmonious. Their art is shaped by a sensory dimension invisible to most audiences, yet the results resonate universally. And it's a reminder that human perception is diverse, that consciousness comes in variations, that what seems like a universal experience, hearing a trumpet, can be fundamentally different for different people. The chromesthete hears and sees the trumpet, experiencing richness and complexity most people miss, and they remind us that reality is always filtered through individual neurology, that perception is constructed and variable, and that the world we experience is just one version among many possible ways of being conscious. Let's venture once more into the abstract realm of theoretical physics. The holographic principle suggests our three-dimensional reality might be a projection from information encoded on a two-dimensional boundary. Everything you experience, depth, volume, space itself, might be like a hologram, calculated from data on a distant cosmic screen. We've explored this idea before, but let's consider its most radical implication. Space itself might be emergent, not fundamental. We take space for granted. It's the stage on which physics occurs, the container for objects and events. But the holographic principle suggests space is derived, a higher-level description that emerges from more fundamental informational dynamics on a lower dimensional boundary. If true, this would be a Copernican revolution in physics. Just as Copernicus showed Earth isn't the center of the universe, and Darwin showed humans aren't separate from nature, holography would show space isn't fundamental. It would be an effective description, useful for certain purposes, but not the deepest level of reality. What would be fundamental instead? Information, possibly, or quantum entanglement. The correlations between quantum systems might be what generates the geometry of space. Some proposals suggest space-time is woven from entanglement, that distance and geometry emerge from patterns of quantum correlations. In this view, asking how far apart are 2 points is a derived question. The fundamental question is, how entangled are they? This is speculative, unproven, possibly wrong, but it's taken seriously by leading theoretical physicists because it solves certain problems. Combining quantum mechanics and general relativity, creating a theory of quantum gravity, has been notoriously difficult. But if space-time is emergent, maybe the problem becomes simpler. Perhaps quantum gravity in our apparently three-dimensional universe is equivalent to a lower-dimensional quantum theory without gravity. Solve the simpler problem, and you've solved the harder one. The AD-S CFT correspondence demonstrates this works for certain spacetimes, and researchers are exploring whether similar principles apply to our universe, whether we live in a hologram, whether the universe's information is fundamentally two-dimensional, with three-dimensional space being a useful fiction. For everyday purposes, this wouldn't change anything. Objects would still have positions, distances would still be measurable, physics would proceed as usual, but conceptually, it would reshape our understanding of reality. We'd be living in a projection, an emergent structure, three-dimensional experience arising from two-dimensional data. And that raises philosophical questions. What does it mean for something to be real if it's emergent rather than fundamental? Is emergent reality less real than fundamental reality? Most physicists would say no. Emergence doesn't diminish reality. The temperature of a gas is emergent from molecular motion, but temperature is real, measurable, causally significant. Similarly, space might be emergent from holographic information, but space is real for us, the level at which we exist and interact. The holographic boundary might be more fundamental in a theoretical sense, but our three-dimensional experience is real in a practical sense. And it's a reminder that physics keeps peeling back layers, revealing that what we took as fundamental is often emergent from something deeper. Atoms aren't fundamental. They're made of particles. Particles aren't fundamental. They're excitations of fields. Fields might not be fundamental. They might emerge from strings or loops or quantum information. Each layer seems solid until we look closer and find it's built from something else, something stranger, something we didn't expect. The holographic principle might be the next layer in that descent, or it might be wrong, a theoretical dead end. But the possibility that we're living in a hologram, that our entire three-dimensional reality is computed from data on a cosmic surface, is a testament to how strange physics has become, how far from everyday intuition we've traveled, how comfortable physicists have become with ideas that sound like science fiction, but might be science fact. Let's return to the microbial world and its hidden sophistication. Some bacteria form electrical grids across distances, passing electrons through conductive filaments in what resembles a microbial power grid. These bacterial nanowires allow communities to share energy and coordinate behavior over distances thousands of times their body length. We've explored this before, but let's reflect on what this reveals about the collective capabilities of simple organisms. Bacteria are single cells, lacking nuclei, lacking organelles, lacking anything we'd call a brain. Yet they can form networks, divide labor, coordinate responses, build infrastructure, behaviors we associate with intelligence or social organization. This challenges our hierarchical view of life. We tend to think complexity requires multicellularity, that cooperation requires brains, that infrastructure requires planning. But bacteria achieve all of this through distributed processes, chemical signaling, evolutionary optimization. No bacterium has a global view of the network, yet the network functions, performs useful work, benefits the community. It's emergent intelligence, not in any bacterium individually, but in the collective, in the network itself. And it's not metaphorical. There's genuine information processing, decision-making distributed across the community. Cells sense local conditions, respond, send signals, adjust behavior. These local interactions aggregate into system-level phenomena: energy flow, waste removal, coordinated responses to environmental changes. And it's ancient. Bacteria have been forming communities, building structures, creating collective behaviors for billions of years. Stromatolites, fossilized bacterial mats, date back 3.5 billion years, among Earth's oldest evidence of life. Bacteria invented multicellular-like cooperation long before eukaryotes, multicellular organisms, or brains existed. They solved problems of coordination, division of labor, infrastructure, without any of the mechanisms we associate with those capabilities. The bacterial nanowires are just one example, discovered recently because we finally developed tools to see them. How many other microbial structures, behaviors, capabilities remain undiscovered? The microbial world is vast. Bacteria constitute most of Earth's biomass, occupy every environment, drive global biogeochemical cycles. Yet we've cultured only a small fraction of bacterial diversity. Most bacteria can't be grown with standard techniques, remain uncharacterized, their abilities unknown. And the implications extend beyond Earth. If bacteria can build nanowires, form networks, cooperate in sophisticated ways, then microbial life elsewhere, on Mars, Europa, Enceladus, exoplanets, might be similarly capable. We often think of alien life in terms of multicellular organisms, complex ecosystems, intelligence. But microbial life, invisible to the naked eye, might be abundant, sophisticated, capable of transforming environments, creating biosignatures we could detect, and it might form communities, networks, collective behaviors we wouldn't expect from simple, single-celled organisms. For the bacteria, this is just survival, exploiting available resources, cooperating when beneficial, competing when necessary. They don't plan, don't conceive of themselves as building grids or forming communities, but through evolutionary processes operating over vast timescales, they've arrived at behaviors and structures that solve complex problems, that resemble designed systems even though no designer is present. It's a reminder that life is inventive at all scales. Complexity doesn't require size or sophistication in the sense we usually mean. A bacterial community, connected by nanowires, sharing electrons, coordinating metabolism. This is complex, sophisticated, functional, even if it's microscopic, unconscious, emerged from billions of years of blind evolution, and it's everywhere, in sediments and soils and biofilms, invisible networks pulsing with activity, microbial civilizations we're only beginning to understand. Let's return to a troubling pattern in human cognition. The Flynn effect shows IQ scores have risen consistently worldwide for a century, and we don't fully understand why it might be reversing now. Each generation scored higher than the last, possibly from better nutrition or education, but recent data suggests the rise has stopped or reversed. We've discussed this before, but let's consider what it means if the reversal is real and persistent. For a century, humanity got smarter, at least by IQ measures, average scores rising 3 points per decade, a substantial cumulative increase. This was hopeful. It suggested environmental improvements could enhance cognition, that we weren't limited by fixed genetic ceilings, that progress was possible. But if the trend is reversing, it implies something has changed. Modern environments, despite material prosperity, might be less cognitively stimulating or more cognitively harmful than mid-20th century environments. The causes are speculative: screen time displacing reading, changes in education, environmental pollutants, lifestyle factors. But the pattern, if real, is concerning. Cognition matters. Individual intelligence correlates with life outcomes: education, income, health, longevity. At societal levels, average cognitive ability correlates with economic productivity, technological innovation, institutional quality. If populations are losing cognitive capacity, even slightly, It could impact long-term societal flourishing, ability to solve complex problems, capacity for innovation. But IQ is just one measure. It captures certain cognitive abilities: abstract reasoning, pattern recognition, verbal comprehension, but not others: creativity, social intelligence, practical wisdom, emotional regulation. Maybe the Flynn effect reversal reflects shifts in what skills are valued and developed, not overall intelligence decline. Maybe digital environments train different cognitive abilities, and IQ tests, designed for pre-digital contexts, don't capture them well. We don't have comprehensive measures of all cognitive capacities across time, so we can't definitively say whether we're getting smarter or less smart overall. We know IQ scores are changing, rising, then plateauing or falling, but interpreting what this means requires caution. What's clear is that cognition is malleable. Environments shape minds. Nutrition, education, toxins, stimulation, social interactions all influence cognitive development. We're not passive recipients of genetic endowments. We actively shape the next generation's cognitive capacities through how we structure society, education, environments. The Flynn effect rising was an unplanned achievement. Collective improvements in conditions that happen to enhance cognition. The reversal, if real, is an unplanned degradation. Changes in modern life that might be harming cognitive development. And addressing it requires understanding mechanisms, identifying factors that matter, making deliberate choices about education, environment, technology, lifestyle. It's also a reminder that progress isn't inevitable, that gains can be lost, that we can backslide even in domains where we thought we were advancing. The 20th century saw dramatic improvements in health, longevity, education, material conditions. We might have assumed these would continue indefinitely. But the Flynn effect reversal, along with other signs, rising mental health issues, declining physical activity, environmental degradation, suggests progress requires active maintenance, that improvements can erode if we're not careful. And there's an existential dimension. Humanity faces complex long-term challenges: climate change, ecosystem collapse, emerging technologies, existential risks. Solving these requires cognitive capacity, individual and collective intelligence, wisdom, foresight, cooperation. If we're losing cognitive ground, even marginally, it impacts our ability to navigate these challenges. Intelligence isn't everything. We also need values, institutions, cooperation, but it matters. And any trend that suggests we're becoming less capable of thinking clearly, solving problems, understanding complexity, that's worth attending to carefully. Let's return to the peculiar symmetries of particle physics. Some quantum particles are their own antiparticles, existing in a state of being both matter and antimatter simultaneously. The photon is its own antiparticle, and discovering others like the hypothetical Majorana fermion could revolutionize quantum computing. We've explored this before, but let's reflect on what it means for a particle to be its own opposite. In particle physics, every fermion, matter, particle has an antiparticle with opposite charge: electron and positron, quark and antiquark, neutrino and antineutrino. When they meet, they annihilate, converting mass to energy. It's a fundamental duality: matter and antimatter as opposites, mirror images, mutually destructive. But some particles lack this duality. Photons are their own antiparticles. A photon and an antiphoton are the same thing. There's no distinction because photons have no charge, no properties that need to be reversed. They're self-symmetric, self-contained. Majorana fermions, if they exist, would extend this self-symmetry to matter particles. A Majorana neutrino would be its own antiparticle, a fermion without the usual matter, antimatter duality. This is only possible for neutral particles. Charged particles must have opposites, because charge must be conserved. But neutrinos are neutral, so they could, in principle, be Majorana particles. Why does this matter? Partly because it would help explain why neutrinos have such tiny masses. The seesaw mechanism, a theoretical framework for neutrino masses, works naturally if neutrinos are Majorana particles. And it might connect to the universe's matter-antimatter asymmetry. If neutrinos are Majorana, and if they existed in the early universe with specific properties, they might have contributed to creating the excess of matter over antimatter that allowed the universe to exist, but also because Majorana quasi-particles, collective excitations in certain materials that behave like Majorana fermions, could enable topological quantum computing. We've discussed this. The idea is that Majorana modes could encode quantum information in ways protected by topology, resistant to decoherence, enabling stable quantum computation. It's a beautiful idea, using the strange self-symmetry of Majorana particles to protect information through geometry. And philosophically, Majorana particles embody a deep symmetry. Most things have opposites, matter and antimatter, positive and negative, particle and antiparticle. But Majorana particles are their own opposites, lacking that duality, existing in a state of self-symmetry. It's a reminder that nature explores all possibilities, including the possibility of being your own reflection, of collapsing the duality between thing and anti-thing into a single entity that contains both. Majorana, the physicist who proposed these particles, vanished in 1938, his fate unknown, and the particles bearing his name remain elusive, possibly detected as quasi-particles in condensed matter systems, possibly constituting neutrinos, but not definitively confirmed. It's fitting, perhaps. Mysterious particles proposed by a mysterious man, both dwelling at the boundaries of what we know, both reminders that physics still harbors deep secrets, that particles can be their own opposites, and that some mysteries persist across decades, waiting for resolution. Let's return to ancient enigmas carved into Earth itself. The Nazca lines in Peru include perfectly straight lines stretching for miles, created by removing rocks to expose lighter soil beneath. These geoglyphs from 500 BCE to 500 CE are best viewed from the air, yet were made by people who never flew. Their purpose remains debated. We've explored this before, but let's reflect on the human impulse to create at scales beyond individual perception. The Nazca made marks visible primarily from perspectives they couldn't access, from the air, from distant peaks, from viewpoints not naturally available to ground-level humans. Why? Perhaps it's about transcendence, the desire to communicate with or create for beings beyond human scale. Gods, ancestors, cosmic forces, entities imagined as looking down from the sky, from mountains, from realms above the ordinary. The geoglyphs would be offerings, declarations, messages visible to the transcendent. Or perhaps it's about conceptual understanding. The Nazca understood geometry well enough to conceive of large-scale patterns even without seeing them completed. They could work from plans, scale up designs, trust their measurements. The fact that the geoglyphs look best from above might be incidental, a consequence of their scale, not the primary intention. But whatever the purpose, the Nazca lines endure. The desert preserves them. Dry climate, stable ground, minimal erosion. They've survived 1,500 to 2,500 years, outlasting the culture that created them. And they've become something their makers couldn't have anticipated. Mysteries for future civilizations, archaeological puzzles, tourist destinations, images viewed from space. There's something poignant about this. The Nazca created these lines with specific intentions, embedded in their culture, their cosmology, their ritual life. But those intentions are lost. We see the lines, measure them, map them, speculate about them, but we don't fully know what they meant to their creators. The meaning has been erased by time, leaving only the physical marks, lines in the desert, images of animals and geometric shapes, enduring but enigmatic. And this is common in archaeology. Ancient peoples leave structures, artifacts, marks, material culture that survives. But the intangible culture, beliefs, practices, meanings, stories, mostly disappears. We reconstruct what we can from material remains, texts when available, comparative ethnography. But there are always gaps, always ambiguities, always multiple possible interpretations. The Nazca lines are one such ambiguity, clear in form, mysterious in meaning. We know the how, remove surface rocks to expose lighter soil, creating contrast visible from above. We know the when, radiocarbon dating, ceramic associations, archaeological context. But the why, that remains uncertain, debated, possibly unknowable. And maybe that's okay. Not every ancient creation needs to be fully explained, decoded, understood. Some mysteries can remain, reminders that past peoples were different from us, thought differently, valued differently, experienced the world through frameworks we can only partially reconstruct. The Nazca lines are there, real and measurable, but their meaning recedes into the past, accessible only through speculation and imagination. They remind us that humans create meaning through marks, that we alter landscapes, build monuments, leave traces, and that those traces outlast their meanings, becoming new things, art, archaeology, mysteries, for future peoples to contemplate. The Nazca couldn't have known their lines would be photographed from aircraft, analyzed with computers, viewed by millions through internet images. But they created them anyway, for reasons meaningful to them. And those marks endure, speaking to us across time in a language we've partially forgotten. Let's return to a phenomenon revealing consciousness's architecture. Some people with blind sight can navigate obstacles despite having no conscious visual experience, their brain processing images they can't see. Damage to the visual cortex leaves them subjectively blind, yet subconscious pathways guide their actions around objects they insist they cannot perceive. We've explored this before, but let's consider what blind sight teaches about the relationship between processing and experience. Your brain processes vast amounts of information continuously. Sensory inputs, motor commands, memory retrieval, prediction, regulation of body systems. But only a fraction of this processing reaches consciousness. Most remains unconscious, operating beneath awareness, guiding behavior without producing subjective experience. Blind sight is an extreme case where the dissociation is obvious. Visual processing occurs, guides action, but produces no visual experience. The patient is blind by introspection. They report seeing nothing, experience only darkness. But they're not functionally blind in the damaged region. They can navigate, reach for objects, detect motion, even identify emotional expressions, all without conscious visual awareness. This shows that consciousness isn't necessary for sophisticated information processing. Function and experience can be separated. Processing can guide behavior without producing qualia, without creating the subjective, what it's like, that characterizes conscious experience. So what makes some processing conscious and other processing unconscious? This is the hard problem in a specific form. Blindsight suggests that processing in subcortical pathways, superior colliculus, pulvinar, others, doesn't produce consciousness, while processing in cortex, especially primary visual cortex V1, does. But why? What's special about cortical processing that generates experience? One proposal is global availability. Cortical processing broadcasts information widely across the brain, making it accessible to many systems: memory, language, planning, executive function. This global availability might constitute or create consciousness. Blindsight involves local processing, information processed in subcortical areas, but not broadcast globally, used only for specific motor outputs, never entering the global workspace. Another proposal focuses on recurrent processing, feedback loops where information cycles through cortical areas repeatedly, creating sustained activity. Subcortical pathways lack this recurrence, processing information in a feed-forward manner. Perhaps recurrent processing is necessary for consciousness, for creating the stable, integrated experiences we recognize as awareness. But these are proposals, not proven explanations. Consciousness remains mysterious. Blindsight reveals the mystery by showing that processing and experience can dissociate, that information can guide behavior without being consciously perceived, that your brain knows things you don't. It's humbling and strange. The realization that much of what guides your behavior happens beneath awareness, in processes you'll never directly experience, in neural systems operating autonomously. For the blindsight patient, the experience is disconcerting, trusting actions guided by information they can't access consciously, feeling their hand reach accurately for objects they can't see, knowing intellectually that some vision persists even though subjectively they're blind. It's a lived example of the unconscious mind at work, a daily reminder that consciousness is just part of the story, that beneath it lies processing, computation, control systems operating silently, invisibly, essential but inaccessible to introspection. Let's return to one of cosmology's deepest questions. The universe's matter-antimatter asymmetry might involve CP violation, a subtle difference in how particles and antiparticles decay that we're still measuring. This tiny asymmetry, if confirmed, explains why you exist instead of annihilating into pure energy with your antimatter twin. We've explored this before, but let's sit with the profound contingency of existence. If CP symmetry were perfect, if matter and antimatter were exact mirrors, behaving identically except for charge sign, the universe would be empty. Every particle born in the Big Bang would have found its antiparticle. They'd have annihilated, and only radiation would remain. No atoms, no chemistry, no stars, no life, no consciousness, just photons cooling and redshifting into infinity. But CP symmetry is violated. Matter and antimatter aren't perfect mirrors. They decay at slightly different rates, through slightly different pathways. This asymmetry is tiny, one part in billions, but it was enough. After the cosmic annihilation, a tiny surplus of matter remained, one particle for every billion that annihilated. That surplus, that tiny excess, became everything. And we don't fully understand it. The CP violation observed in particle physics points in the right direction, but might not be large enough. This suggests missing pieces, new sources of CP violation, new particles or interactions active in the early universe, but inaccessible in our low-energy experiments. Finding these missing pieces is one of particle physics' major goals. There's something profound about this. The universe's most basic property, that it contains matter at all, depends on a tiny violation of symmetry, a slight favoritism toward matter over antimatter that we can barely measure and don't fully explain. Existence required breaking perfect symmetry. Perfect balance would have been sterile. The asymmetry, the imperfection, the violation. These made everything possible. It's a reminder that reality isn't built on perfect principles, perfectly obeyed. It's built on principles with small violations, symmetries with small breaks, balances tipped just slightly. And those small imperfections, rather than destroying order, create it. They allow complexity, structure, diversity. Perfect symmetry is simple but empty. Broken symmetry is messier but fertile. And it raises deep questions. Why is CP violated? Is there a deeper reason, or is it a contingent fact, something that could have been different? If CP violation had been slightly larger or smaller, would the universe be dramatically different? Are there universes with different CP violation, some empty because the asymmetry was too small, others dominated by antimatter because the asymmetry favored it instead? If so, we necessarily find ourselves in one where the asymmetry was just right for matter to survive, an anthropic selection from a larger landscape of possibilities. We don't know. We measure, we calculate, we theorize, but the ultimate explanation for CP violation remains elusive. And maybe it's appropriate that one of the universe's most fundamental properties, why there's something rather than nothing, is mysterious, a question at the edge of what we can understand. It reminds us that for all our knowledge, we're still asking the deepest questions, still probing the origins, still seeking to understand why the universe is the way it is. And you, sitting here, reading this, existing as a pattern of matter, you're a consequence of that ancient asymmetry, that tiny violation of symmetry in the first instance after creation. Every atom in your body is part of the surplus, the remnant that survived the cosmic annihilation. You exist because reality is slightly imperfect, slightly asymmetric, slightly tilted in favor of matter. And that tilt, that tiny deviation from perfect balance, made all the difference. Let's close with a simple phenomenon that humbles our understanding. The Mpemba effect shows that hot water can freeze faster than cold water under certain conditions, violating our intuitive physics. Even Aristotle noticed this phenomenon, but physicists still debate exactly why it happens. Convection, evaporation, or something else entirely. We've explored this before, but let's reflect on what it means that something so simple remains unexplained. Water, the most familiar substance, essential to life, ubiquitous on Earth, still surprises us. Freezing water, one of the most common phase transitions, still holds mysteries. Despite centuries of study, thousands of experiments, sophisticated theories, we can't definitively predict when hot water will freeze faster than cold. This isn't because we lack general understanding. We know thermodynamics, heat transfer, phase transitions. But water is complex. High surface tension, unusual density maximum, intricate hydrogen bonding, anomalous properties at every turn. And freezing involves multiple mechanisms: evaporation changing mass, convection affecting heat distribution, supercooling delaying nucleation, dissolved gases influencing crystal formation. These mechanisms interact nonlinearly, context-dependently, making the outcome sensitive to details. The Mpemba effect sits at the intersection of these complexities. It's real, observed, replicated, but elusive, not universal, not always present, dependent on container, initial conditions, environment. It's a phenomenon emerging from the interplay of multiple effects, not reducible to a single clean explanation. And that's frustrating for physicists trained to find simple principles underlying complexity. But it's also instructive. Nature is messy. Real-world phenomena don't always fit textbook idealizations. Simple questions can have complex answers. Does hot water freeze faster than cold? Sometimes yes, sometimes no, depending on dozens of variables we'd need to specify precisely to predict outcomes reliably. And that's okay. That's how reality works, not through simple universal laws applied directly, but through simple laws interacting in complex contexts, producing outcomes that require careful, detailed analysis to understand. The Mpemba effect is a reminder to stay humble, to keep questioning, to not assume we understand even familiar things completely. It's a reminder that mystery lurks in the mundane as much as in the exotic, that everyday phenomena can harbor surprises, that water, boring, ordinary, everywhere water, still teaches us things, still defies our complete understanding, still freezes in ways we can't entirely predict. And maybe that's fitting for the final mystery in this collection. We've traveled from the cosmos to consciousness, from quantum mechanics to ancient civilizations, from the nature of time to the structure of reality itself. We've explored 100 mysteries, 100 edges of knowledge, 100 places where science meets uncertainty, and we're reminded how much we don't know. And at the end, we return to water freezing, simple, familiar, ordinary. A reminder that mysteries exist at every scale, in every domain, from the most abstract physics to the most concrete, everyday phenomena. The universe is full of questions, full of phenomena we observe, but can't fully explain, full of patterns that challenge our theories and humble our certainties. And that's beautiful, isn't it? A universe that still surprises us, still holds secrets, still rewards curiosity with new questions, even as it answers old ones. We've learned so much about particles and planets, about life and light, about the cosmos and consciousness. But for every answer, new questions emerge, deeper and stranger, pulling us forward into mystery. The Mpemba effect, like all the mysteries we've explored, invites us to wonder, to question, to remain curious. It reminds us that science isn't about having all the answers. It's about asking better questions, about observing carefully, about remaining humble before complexity. And it suggests that no matter how much we learn, there will always be more to discover, more to wonder about, more mysteries waiting at the edges of knowledge. So let the hot water freeze, faster or slower, depending on conditions we're still working out. Let the universe keep its secrets, reveal them slowly, reward our patience and curiosity. Let mystery remain, because mystery is what drives us forward, What makes exploration worthwhile? What reminds us that reality is richer and stranger than we've imagined? And as you drift towards sleep, perhaps you can carry with you this sense of wonder, this appreciation for the unknown, this comfort in uncertainty that characterizes the scientific spirit, always questioning, always curious, always ready to be surprised by the universe's inexhaustible capacity for mystery. And so we've reached the end of our journey through 100 mysteries that baffle scientists. From the sound waves frozen in galaxy distributions to water that defies our simple predictions about freezing, we've wandered through the edges of human knowledge. Those places where understanding gives way to wonder. Each of these mysteries is an invitation, not to frustration or anxiety, but to curiosity, to the quiet appreciation that the universe still holds secrets, that reality is richer than our theories, that even the most familiar things can surprise us. Science isn't about having all the answers. It's about asking better questions, observing carefully, and remaining humble before the vast complexity of existence. As you drift towards sleep now, perhaps you can carry with you this sense of wonder. The universe is still revealing itself, still unfolding mysteries, still rewarding those who look closely and think deeply. And tomorrow, somewhere in a laboratory or observatory or field station, someone will observe something unexpected, measure something that doesn't quite fit, discover a new edge of the unknown. The mysteries continue, endless and beautiful, reminding us that there's always more to learn, more to explore, more to wonder about. Sleep well, and may your dreams be filled with questions as interesting as the answers we seek. Good night.